In this presentation we discuss electrostatics and dielectric materials. We begin by examining the electrostatic field in a charged parallel plate capacitor filled with an insulating medium between its plates, where we define the relative permittivity of dielectric materials. We then discuss the electric polarization induced in insulating materials by electrostatic fields and introduce the polarization vector, which describes the degree of polarization in the dielectric medium. Using the polarization vector, we generalize Gauss's law for dielectric materials and define the electric displacement vector and the electric susceptibility of dielectrics. We apply these concepts and the generalized Gauss's law to study electrostatic fields in dielectric materials for various geometries, including homogeneous and isotropic dielectric media between charged infinite parallel plates and surrounding charged conducting spheres. In this context, we also discuss the phenomenon of depolarization. We study the behavior of the electrostatic field across the interface between two dissimilar dielectric media and derive the boundary conditions for the electric field strength and electric displacement vectors at the interface. We also examine the polarizability of atoms and molecules by determining the local electric field in dielectric materials, defining atomic polarizability, and studying the polarization of gaseous substances. Next, we derive the energy density of the electrostatic field in dielectric materials by considering a charged parallel plate capacitor filled with a homogeneous and isotropic dielectric. We determine how the energy density changes under conditions of constant charge and constant voltage. Furthermore, we examine the forces acting on charged bodies in dielectric media by presenting several experiments and deriving the forces exerted on point charges and charged parallel plates surrounded by dielectric materials. Finally, we discuss ferroelectricity by presenting the behavior of ferroelectric materials, examining the piezoelectric and pyroelectric effects exhibited by them, and introducing electrodes. The behavior of dielectric materials in an electrostatic field was already studied by Faraday. In 1837 he showed in his experiments that if the space between the plates of a capacitor is filled with some insulating material instead of vacuum or air, then the electric capacitance of the capacitor increases. That is, if C0 is the capacitance measured for a parallel plate capacitor with a vacuum or air between its plates, when the charges plus Q0 and minus Q0 on its plates produce the electric field E0 in the capacitor, then the capacitance C measured for the same capacitor storing the same amount of charge but with insulating material between its two plates that produces the electric field E, is greater than the capacitance C0. Electrical insulators or dielectrics are materials that do not conduct electrical current, but such ideal insulators do not exist in nature. All substances conduct electricity even if to a negligible extent. In general, metals conduct electricity 10 to 15 to 10 to 20 times better than the materials called dielectrics. When we introduce the concepts of electrical conductors and insulators, we mention some examples for electrical conductors in everyday life, such as metals, the human body and the ground. For electrical insulators, we mention glass, ebonite and amber. The list of substances insulating electricity is of course more extensive. Besides glass or ebonite, we can talk about rubber in a more general sense, plastic, wax, wood, air, ceramic, styrofoam, and so on. We already had a discussion on the quantized nature of electric charge, and established that electrons and ions are charge carriers. Hence it is easy to see that the properties of electrical conduction and insulation are the result of electron mobility in materials. Conductors contain abundant valence electrons in their chemical bonds that can move easily from one atom to another when voltage is applied, producing an electric current in the material. As opposed to conductors, insulators have electrons tightly bound to a single atom and impede from free flow of electrons from atom to atom. These fundamental differences in the atomic or molecular structures of different substances indicate that the effectiveness of electrical insulation depends on the inherent properties of the material. At the same time, it also depends on the voltage applied on the substance and environmental factors like temperature, moisture, contamination, aging and so on. All of these factors can degrade the performance of dielectric materials and cause electric breakdown. As already mentioned in the discussion on capacitors, only the maximum breakdown voltage can be applied on a capacitor without causing an electric breakdown of the dielectric material between its plates. This phenomenon also indicates that if a dielectric is introduced into the electric field of a charged capacitor, changes usually occur both in the electric field and in the dielectric itself. Motivated by these findings, let us first examine how the capacitance and the electric field of a capacitor change as a result of placing a dielectric into the electric field of the capacitor, under the condition that the charge or voltage of the capacitor is constant. Let us start with the experiment examining how the capacitance and the electric field of a parallel place capacitor alter as a result of a dielectric placed in the electric field of the capacitor, under the condition that the charge of the capacitor is constant. First, we connect an electrometer to the plates of the parallel plate capacitor with a vacuum or air between the plates, and bring the charges plus Q0 and minus Q0 to its plates. This given amount of charge produces the electric field E0 in the capacitor, and the voltage V0 is indicated by the electrometer. If we insert a paraffin block between the metal plates of the capacitor, then the electric field must change between the plates of the capacitor denoted by the letter E, since we find that the electrometer measures a voltage V that is less than the initial value V0. After removing the paraffin block, the initial voltage V0 is measured between the plates of the capacitor again. Considering that the amount of the charge Q0 on the plates remains the same during the experiment, the electric capacitance of the capacitor can be expressed in two forms according to whether there is a vacuum or air, or an insulating material between the plates. In the case of a vacuum or air, the capacitance C0 of the parallel plate capacitor is equal to the ratio of the charge Q0 to the voltage V0. For the capacitor with a dielectric between its plates, the capacitance C is given by the ratio of the charge Q0 to the voltage V. Since the experiment shows that V0 is greater than V, we conclude from the comparison of the two equations that the capacitance C is greater than the capacity C0, that is, the capacitance of the parallel plate capacitor is increased by inserting an insulating material between its plates. According to the measurements, if the insulating material completely fills the space between the plates of the capacitor, the ratio epsilon R of the capacitance C to the capacitance C0 is independent of the type and size of the capacitor and only depends on the given insulating material. The ratio epsilon R, which is greater than 1, is called the relative dielectric constant or the relative permittivity of the material. So this is a mere number that gives how many times the capacitance of a capacitor filled with dielectric is greater than the capacitance of a capacitor with a vacuum or air between its plates. By definition, epsilon R is equal to 1 for vacuum. The following table shows the relative dielectric constants of some substances. It can be seen from the table that atmospheric gases and gases in normal state in general have a relative permittivity close to 1. This explains why the gases in normal state hardly affect the electrostatic phenomena that occur in a vacuum. As we have already stated, the capacitance of a capacitor with a dielectric material is epsilon R times greater than its capacitance with a vacuum between the plates. We will also derive analogous relations between the voltages V and V0 and the electric field strength E and E0 with and without insulating material between the plates of the capacitor. Based on the condition of a constant amount of electric charge in the experiment, we can take into account the equations written for the capacitances, use the relation stating the capacitance is given by the ratio of the charge of the capacitor to its voltage, and express the relative dielectric constant by the quotient of the voltages of the capacitor. That is, epsilon R is equal to the ratio of the voltage V0 measured for a vacuum or air, to the voltage V measured for the dielectric. If E0 and E represent the electric field strengths between the plates of the parallel plate capacitor in the case of a vacuum and an insulating material, and D is the distance between the parallel plates of the capacitor, then the voltage V0 can be expressed by the product of the magnitude of the electric field strength E0 and the distance D, and the voltage V is equal to the magnitude of the field strength E times the distance D. These equations are derived from the fact that the electric field is uniform between the plates. As a result, the relative dielectric constant epsilon R can be written as the ratio of the magnitude of the electric field strength E0 to the magnitude of the electric field strength E. This formula indicates that if the charge on the plates of the parallel plate capacitor creates an electric field with the field strength E0 in the space between the plates in a vacuum or air, then the same amount of charge creates a weaker electric field with the magnitude E in the dielectric, that is, a field strength is epsilon R times smaller than the field strength in a vacuum. This result obtained for the field strength in the case of this experiment with special conditions is also true in general. That is, the electric field strength due to any system of charges placed in a vacuum decreases everywhere if the space is filled with a homogeneous and isotropic dielectric of the same dielectric constant, while leaving the charges unchanged. Because in the formulas describing electromagnetic laws, epsilon R occurs in a product with the vacuum permittivity epsilon naught, it is reasonable to introduce the absolute dielectric constant or absolute permittivity epsilon as the product of the two quantities. Since the relative permittivity is just a number, the unit for absolute permittivity is the same as the unit for vacuum permittivity, which is Coulomb squared per Newton meter squared. Now we modify the conditions of the experiment in such a way that a constant potential difference V0 is maintained between the plates of the parallel plate capacitor with the help of a battery, while the electrometer is switched into the mode measuring electric current, that is the rate of the flow of electric charge described by the time derivative of the charge. In the case of the capacitor with the paraffin block, that is a dielectric between its plates, the charge Q of the capacitor is given by the capacitance C of the capacitor times the voltage V0 maintained between its plates. In the previous experiment with a constant electric charge of the capacitor, we found that the capacitance C of the capacitor is equal to the relative permittivity epsilon R of the insulating material filling the space between the plates, times the capacitance C0 of the capacitor with a vacuum or air between its plates. In this experiment the voltage V0 through the capacitor is kept constant while the amount of charge on the plates of the capacitor is different in the two cases. For the capacitor with a vacuum or air between its plates the charge Q0 is given by the product of the capacitance C0 and the voltage V0, whereas we can express the capacitance C in the formula of the charge Q of the capacitor filled with a dielectric between its plates as the relative permittivity epsilon R of the dielectric, times the capacitance C0. Then the charge Q is equal to the relative permittivity epsilon R times the charge Q0, where epsilon R is greater than 1. This formula shows that the charge of the capacitor increases from Q0 to Q by filling the space between its plates with an insulating material. The measurements in the experiment confirm this result. When the dielectric is inserted between the plates of the capacitor, the electrometer indicates a transient electric current in the circuit. If the time of the transient flow of electric charge during which the paraffin block is inserted between the plates is known, then the change in the charge of the capacitor from Q0 to Q can be determined. We will find that the electric charge of the capacitor after inserting the paraffin block between the plates is epsilon R times greater than the charge of the capacitor with a vacuum or air between its plates. Because the voltage is constant during the experiments, the electric field strength E0 does not change between the plates of the capacitor even in the presence of a dielectric material. Then the magnitude of the uniform field E0 is given by the voltage V0 times the distance d between the plates, and we can write that the magnitude of the electric field strength E is equal to the magnitude of the electric field strength E0. The relationships obtained for the electric charge and the electric field strength express that if a given amount of charge of a parallel plate capacitor produces an electric field strength in a vacuum or air, then the same field strength in a dielectric between the plates of the capacitor can be produced by epsilon R times greater amount of charge on the plates of the capacitor. Experiments show that the capacitance of any type of capacitor with a dielectric between its plates is epsilon R times greater than that of the capacitor with a vacuum or air between its plates. Specifically, the capacitance of a parallel plate capacitor, when the space between the plates is filled by an insulating material with a dielectric constant epsilon R, is described by the product of epsilon R and the capacitance C0 of the capacitor with a vacuum or air between its plates. The latter is equal to the dielectric constant epsilon naught of a vacuum, times the ratio of the surface area A of each plate of the capacitor to the distance d between the plates. It is generally true that the capacitance C of an arbitrary type of capacitor can be written as the vacuum permittivity epsilon naught times the relative permittivity epsilon R of the dielectric material filling the space between the plates of the capacitor, times a factor L with a unit of length depending on the geometry of the capacitor. That is, the capacitance C of the capacitor is equal to the absolute permittivity epsilon of the dielectric material used for the capacitor, times the geometric factor L of the capacitor. When we classified the different substances as electrical conductors and insulators, we did so in reference to the atomic or molecular structure of materials. Therefore, the interpretation of the result of the previous experiments using a charged capacitor with a vacuum or a dielectric between the plates, is based on the atomic and molecular nature of insulating materials. In order to give the interpretation of the behavior of dielectrics in an electric field, we start with more general results obtained from the empirical data related to the electrical insulators. These results tell us that the majority of dielectrics can be classified into two different groups, according to whether the atoms and molecules that make them up have an electric dipole moment or not without an external electric field. Some of the dielectrics are called nonpolar dielectrics since they consist of nonpolar molecules in which the time-averaged centers of gravity of the positive and negative charges coincide without an external electric field. That is, these type of insulating materials do not have an electric dipole moment. However, in an external electric field the positive charges are shifted in the direction of the field, and the negative charges are shifted in the opposite direction within these nonpolar molecules. As a result of the displacement of the two types of charge in opposite directions, they become an electric dipole, that is, the molecules acquire an induced dipole moment. Other dielectrics are known as polar dielectrics since they are made up of polar molecules that have a permanent electric dipole moment even without an external electric field, as a consequence of their internal structure. In the absence of an external electric field, these polar or dipole molecules with a constant dipole moment are completely disoriented due to their thermal motion. However, Under the influence of an external field, they align their axis in the direction of the electric field to a lesser or greater extent. We can also give some examples for both nonpolar and polar dielectrics. The most common examples for nonpolar dielectrics are hydrogen or oxygen, or more generally symmetric diatomic gases or hydrocarbons, but we can also mention rubber, Teflon and paraffin wax. The key examples for polar dielectrics include water, hydrogen chloride, alcohol, and polyvinyl chloride. We note that there are some insulators that are polarized in a different way than polar and nonpolar dielectrics. For example, in the case of a salt crystal, two lattices of positive sodium ions and negative chloride ions are shifted relative to each other by half a unit cell dimension along a crystal axis, and form the crystal lattice of sodium chloride. Then the polarization of a salt crystal can be interpreted as the two lattices become slightly displaced from their equilibrium positions relative to one another in an external electric field. The polarization of insulators is similar to the influence in conductors, but there is a significant difference between them. While in the case of influence, the two types of charge can be separated by dividing the conductor into two parts, this is not possible for polarized insulators, because any infinitesimal volume element of an insulator contains an equal amount of the two types of charges. Based on this explanation of the behavior of insulating materials, the same conclusion is reached for both the types of dielectrics applied in the experiment for a charged capacitor. The dielectric placed in the electric field E0 due to the charges plus Q and minus Q on the metal plates of the capacitor remains neutral as a whole, but dipole chains form inside the insulating material and polarization charges appear on its surface. The negative charges minus Q' are induced on the surface of the dielectric adjacent to the plate with the charge of plus Q, whereas the positive charges plus Q' are induced on the surface of the dielectric adjacent to the plate with the charge of minus Q. The volume electric charge density is zero everywhere inside the polarized homogeneous dielectric, because the algebraic sum of the opposite charges in the dipoles chains vanishes. Due to the presence of induced or polarization charges, some amount of the field lines of the electric field E0 start from the induced charges plus Q' and end on the induced charges minus Q'. As a result of polarization, the density of the electric field lines or the electric field strength will be less inside the dielectric material than in a vacuum between the plates with the same charges plus Q and minus Q. At the same time, the lower field strength corresponds to a lower voltage and a greater capacitance of the capacitor, in agreement with the result obtained in the first experiment. The electric field strength E inside the dielectric can be considered as the vector sum of the electric field strength E0 due to the charges plus Q and minus Q on the plates of the capacitor, and the electric field strength E' due to the charges plus Q' and minus Q' induced on the boundary surfaces of the dielectric. Since the vector E' points in the opposite direction to the vector E0, the magnitude of the vector E is equal to the difference between the magnitudes of the vectors E0 and E'. As shown in the previous experiments with a charged capacitor, the magnitude of the field strength E is given by the ratio of the magnitude of the field strength E0 to the relative permittivity εr of the dielectric inserted between the plates of the capacitor. If we substitute this expression into the left-hand side of the equation, then we can express the magnitude of the electric field strength E' by the magnitude of the electric field strength E0, times 1 minus 1 over εr. Because the relative dielectric constant εr is always greater than 1 and it has a finite value, these equations express the fact that the electric field strength inside dielectrics is always less than the electric field strength of a capacitor with a vacuum or air between the plates, and it is always greater than 0. The charges plus Q' and minus Q' induced on the surface of the polarized insulating material that produces the electric field E' are also known as polarization charges, whereas the charges plus Q and minus Q producing the electric field E0 between the plates of the capacitor are called real charges. The difference between the real and polarization charges producing the electric field E and the dielectric are called free charges as well. We can also derive the relation between the polarization charges Q' induced on the surface of the dielectric and the real charges Q, and find that Q' is equal to Q times 1 minus 1 over εr. If sigma is the surface charge density of the real charge Q over the plates of the capacitor with the area A, then the polarization surface charge density sigma prime of the polarization charge Q' is simply equal to sigma times 1 minus 1 over εr. When we studied charged conducting surfaces, we found that the electric surface charge density sigma of two uniformly charged parallel infinite conducting planes is equal to the product of the vacuum permittivity ε0, and the magnitude of the electric field E0 due to the surface charge distributed over the planes. Here we can apply this finding since it is a good approximation for the uniform electric field between the plates of a capacitor. We also saw that the magnitude of the electric field E0 for a vacuum or air between the plates is given by the relative permittivity epsilon r of the dielectric between the plates, times the magnitude of the electric field E for the dielectric between the plates. By inserting this result into the equation describing the polarization surface charge density, we can write sigma prime as the vacuum permittivity epsilon naught, times the relative permittivity epsilon r minus 1, times the magnitude of the electric field E between the plates of the capacitor. We saw that in a dielectric that has become polarized in an external electric field, atoms or molecules develop or align their electric dipole moment in the direction of the field. The degree of the polarization of an insulating material in an electric field is characterized by the electric dipole moment of the material per unit volume, and it is called the electric polarization P of the dielectric. If an isotropic dielectric is placed in the uniform electric field of a parallel plate capacitor, then it becomes uniformly polarized, where the polarization charges plus Q' and minus Q' induced on the surfaces of the dielectric at a distance d from each other produce a dipole moment of the dielectric. The electric dipole moment P' of the polarized insulating material completely filling the space between the plates of the capacitor, is given by the product of the polarization charge Q' and the distance d of the two surfaces of the material at the plates. Here we express the polarization charge Q' by the polarization surface charge density sigma prime times the area A of the plates of the capacitor. Because the product of the area A of the plates and the distance d gives the volume V of the dielectric inserted in the space between the plates, we can write the dipole moment P' as the product of the surface charge density sigma prime and the volume V. Hence the polarization P of the dielectric defined by the ratio of the dipole moment P' of the insulating material to its volume V, is equal to the polarization surface charge density sigma prime of the dielectric. This result shows that the polarization has the same unit as the surface charge density, and it measured in Coulomb per square meter if we use SI units. If we consider the electrical polarization P as a vector pointing from the negative polarization charge minus Q' to the positive polarization charge plus Q', then we can write the electrical polarization P of a dielectric as the polarization dipole moment P' of the dielectric divided by its volume V. If the electric field is not uniform or the dielectric is inhomogeneous, then the polarization P of the dielectric will be different at different points of the dielectric. In this case we need to consider a volume element delta V of the dielectric at any given point that is small enough to allow us to assume that any macroscopic property of the insulating material, such as density, temperature, or electric field strength, is constant in the volume element. At the same time, delta V must be big enough to contain many molecules with electric dipole moment. We can add these dipole moments P'i for all the n molecules in the volume element and divide this sum by delta V, which gives the electric polarization P at the given point of the dielectric polarized in an electric field. If the volume element delta V becomes an infinitesimally small volume element, then we can formally define the polarization P of a dielectric with the electric dipole moment P' by the derivative of the electric dipole moment P' with respect to the volume V. We however saw that there is a finite number of electric dipoles in any volume element, that is, the dipole moment in a polarized insulator has a discrete nature. The derivative of such a quantity can still be determined in a macroscopic approach, where we consider the electric dipole moment as a quasi-continuous vector field in dielectrics. We already saw that the magnitude of the polarization in a dielectric filling the space between the plates of a charged parallel plate capacitor is equal to the polarization surface charge density of the insulating material. Now we examine the relationship between polarization and polarization surface charge density in a more general situation. Let us place an oblique rectangular prism made of a homogeneous isotropic dielectric into a uniform electric field parallel with the lateral faces of the prism, as seen in the figure. Here the length of the lateral edges is denoted by L, and A is the area of the bases of the oblique prism parallel to each other. In the electric field, polarization charges appear over the boundaries of the bases that can be described by the sigma prime surface charge density. Since the displacement of charges inside the dielectric occurs parallel with the lateral faces of the oblique prism, no polarization charges are induced over the surface boundaries of these faces. The dielectric acquires a dipole moment due to polarization, which is equal to the amount of polarization charges on the boundary of the bases, times the distance between the two bases measured along the direction of the displacement of the charges in the dielectric, that is along the lateral faces of the oblique prism. Then the dipole moment P' of the dielectric is equal to the product of the polarization surface density sigma prime and the area A of each base, times the distance vector d with the length L of the lateral edges pointing from the negative polarization charges to the positive ones. By applying these notations, we can write the polarization P of the dielectric given by the dipole moment P' over the volume V of the dielectric, as sigma prime times A over V, times the vector d. If n is the unit normal vector to the base with positive induced charges pointing outward, then the volume V of the oblique prism can be expressed by the dot product of the vectors d and n, times the area A of the base. By substituting this formula into the equation obtained for the polarization P, the latter reduces to sigma prime over the dot product of the vectors d and n, times the vector d. Now we take the dot product of the result with the unit normal n, which gives the polarization surface charge density sigma over the bases of the oblique prism as the dot product of the polarization P of the dielectric, and the outward pointing unit normal n to the base with positive induced charges. That is, sigma prime is equal to the normal component of the polarization P of the dielectric with respect to the surface of the dielectric. If the dielectric material has a shape of a cuboid, then the polarization and the normal vector to the base become parallel, and we regain the equation stating that the polarized surface charge density is given by the magnitude of the polarization. The expression derived above also holds for the opposite base of the oblique prism with negative charges, since then the unit normal n to that base points in the opposite direction, and thus the normal component of the polarization P is negative. This expression is also valid for the lateral faces of the oblique prism where the polarization surface charge density vanishes, because the normal vectors to the lateral faces are perpendicular to the polarization vector of the dielectric. As a result, we have obtained a general formula describing the polarization surface charge density of dielectrics. According to this equation, the normal component of the polarization P represents the amount of charge that is displaced across the unit surface area in the direction of the unit normal n. This interpretation can also be applied in the case of inhomogeneous polarization, where the magnitude and the direction of the vector P vary at different points in the dielectric. In order to be convinced of this statement, it is enough to think that the dielectric is divided to small volumes within which the polarization can be considered homogeneous. We also mention that the quantities related to electric polarization, such as the polarization surface charge density sigma prime describing the distribution of the polarization charge Q prime, are normally distinguished by the subscript p instead of using the superscript prime. Then we can write that sigma p is equal to the dot product of the polarization P and the unit surface normal n. This more frequent notation will be applied here as we talk polarization charges distributed in a spatial volume. In the case of inhomogeneous polarization, polarization charges appear not only on the surface of the dielectric but they are also distributed throughout the volume of the insulating material. In order to determine the density of the volume polarization charges in the dielectric, we consider an arbitrary volume V within it enclosed by the surface S. The amount of charge that is displaced across the surface element ds of the boundary surface S in the direction opposite to the outward pointing unit normal n to the surface element, is given by the negative dot product of the polarization P and the volume V and the unit normal n, times the surface area ds. This expression can also be written as the negative dot product of the polarization P and the surface element vector ds with the area of the surface element and the direction of the unit normal n. If we integrate this expression over the whole boundary surface, then we obtain the total amount of polarization charges Qp displaced across the boundary surface S of the volume V, that is Qp is given by the negative surface integral of the normal component of the polarization P over the surface S, or the negative surface integral of the dot product of the polarization P and the surface element vector ds over the surface S. Here the minus sign indicates that the polarization charges are displaced from outside into the volume V in the direction opposite to the surface normal n. Now we introduce the polarization volume charge density ρp such that its volume integral over the volume V gives the total amount of the polarization charge Qp displaced into the volume V. By comparing the two equations describing the volumetric polarization charge with each other, we can write that the volume integral of the polarization volume charge density ρp over the volume V is equal to the negative surface integral of the polarization P over the boundary surface S of the volume V. If we apply Gauss's divergence theorem, then the surface integral in the right-hand side of the equation can be transformed into the volume integral of the divergence of the polarization P over the volume V. Because this equation holds for any arbitrarily volume V in the dielectric, it must be valid at any point in the insulating material, and we conclude that the polarization volume charge density ρp in a dielectric is equal to the negative divergence of its polarization P. For a uniformly polarized dielectric, we immediately see the divergence of the polarization vanishes and the polarization volume charge density ρp is equal to 0, that is, there is no polarization charge inside the insulating material, as we expected. This result indicates that together, the polarization surface charge density and the polarization volume charge density represent the polarization charges induced in dielectrics. Hence, three equations describe the polarization vector field in an insulating material under the influence of an external electric field. The first one tells us that the polarization surface charge density sigma p at any point of the boundary of the dielectric is equal to the dot product of the polarization capital P and the unit surface normal n at the given point. The second one states that the volume charge density at any point inside the dielectric is given by the negative divergence of the polarization capital P. The last one is the obvious requirement for the vanishing polarization P outside the insulating material. We note that the three equations do not uniquely determine the polarization vector field in the dielectric, since they do not specify the non-curl-free part of the Helmholtz decomposition of the vector field capital P in the matter at all. We can compare the divergence equation of the polarization with the fundamental equation of electrostatic in a vacuum stating that the electric charge density ρ at a given point in space divided by the vacuum permittivity epsilon naught is equal to the divergence of the electric field strength E at that point. This comparison shows that the polarization volume charge density ρp is the source of the electric field in a polarized dielectric with the polarization capital P, just as the volume density ρ of electric charges is the source of the electric field E in a vacuum. It follows from these findings that the polarization in dielectrics must be taken into account in the equations of electrostatics derived from the condition where the electric charge is only present in conductors or in a vacuum. In order to describe the more general cases in electrostatics where insulating matter may be present in an electric field, we need to include the description of polarization in the fundamental equation of electrostatics. If we examine any phenomenon related to an electrostatic field in the presence of dielectrics, it is useful to distinguish between bound and extraneous or free electric charges. Bound charges are the charges in the atoms and molecules of dielectrics, as well as the ionic charges in dielectrics with an ionic lattice crystal. As discussed earlier, these charges are displaced only slightly from their equilibrium position under the influence of an electric field, and they cannot leave the atoms or the molecules containing them and move throughout the material. Consequently, bound charges represent the internal dipoles induced in the polarization of dielectrics contributing to the overall polarization charge density, but they do not produce a conduction current of charges in the material. Apart from bound charges, all other charges are called extraneous or free charges, that is, charges that are not attached to specific atoms or molecules, allowing them to move freely. Extraneous charges are, for example, the charges of the conduction electrons of metals, the charges of ions and electrolytes and gases, and the excess charges transferred to conductive or non-conductive bodies. All these types of charge move in response to an external electric field, and they are responsible for electrical conductivity, and the electric current in a conductive material is produced by these moving free charges. In a dielectric, the electric field strength is determined by the superposition of the field strength E produced by extraneous charges and the field strength EB due to bound charges. The resulting field strength EM is called microscopic or real field strength. The microscopic field strength varies in a great extent within the distances between atoms or molecules. However, this variation cannot be observed in macroscopic scale, so the electric field is characterized by the value of the microscopic electric field averaged over an infinitesimally small volume. Then the electric field E is the superposition of the averaged electric fields due to extraneous charges and bound charges. In the absence of any dielectric that is in a vacuum, the macroscopic electric field strength is reduced to the average of the free charges. The volume charge density ρ describing the spatial distribution of free charges is the source of such an electric field in the fundamental equation stating that the charge density ρ divided by the vacuum permittivity is equal to the divergence of the electric field E. We also note that if the free charges represented by the charge density ρ are constant in time, then the electric field given by this equation has the same properties as an electrostatic field in a vacuum. As already stated in the discussion on the polarization of insulating materials, we need incorporate its effects in vacuum electrostatics to provide a general description of electrostatic fields in dielectrics. This will be achieved by introducing a quantity called electric displacement representing the electric field due to free charges and excluding bound charges. In order to do so, let us consider an experiment where we suppose that the space between the plates of a charged parallel plate capacitor is filled with an isotropic insulating material that has the relative dielectric constant epsilon r. We already saw that the capacitor with the electric charges plus Q and minus Q on its plates has a uniform electric field E between the plates, and the polarization charges plus Q and minus Q induced on the boundary surfaces of the dielectric adjacent with the plates produce a uniform electric field E prime pointing in the opposite direction. We also established that the uniform vector field P describes the polarization of the isotropic dielectric pointing from the negative polarization charges to the positive ones. As a Gaussian surface S, we can consider a box with the cross-section indicated by the yellow line in the figure enclosing the positive charge Q on the plate of the capacitor and the negative charge Q' on the boundary of the dielectric. By applying Gauss's law for this closed surface, we can find that the surface integral of the electric field over the surface S is equal to the total charge inside the surface given by the sum of Q and negative Q' over the vacuum permittivity epsilon naught. We already described the polarization charges plus and minus Q' by the product of the charge Q and 1 minus 1 over the relative permittivity epsilon R of the dielectric. If we substitute this expression in the right-hand side of the equation, then the latter can be written as Q over epsilon naught times epsilon R. According to this result, the form of Gauss' law derived for a vacuum can also be applied to a dielectric with the modification that the charge Q is replaced by Q minus Q', that is Q over epsilon R, due to the fact that the field strength E is epsilon R times smaller in the dielectric than in a vacuum. Or with the modification where we write epsilon R times E instead of the field strength E prevailing in the dielectric. Now we consider the general case of the non-uniform polarization of a dielectric. Then the equation following from the application of Gauss's law states that the surface integral of the electric field E over any closed surface is equal to the sum of the free charges Q and the polarization or bound charges QP within that surface, over the vacuum permittivity epsilon naught. We already showed that the polarization charge Q induced in a given volume of a dielectric is equal to the negative surface integral of the polarization P over the boundary surface of the volume. If the Gaussian surface encloses this volume, then we can substitute this surface integral into Gauss's law, and we obtain the equation stating that the surface integral of the sum of the vacuum dielectric constant epsilon naught times the electric field strength E and the polarization P over the Gaussian surface is equal to the total amount of the free charges Q within the surface. Now we introduce the vector field of the electric displacement D of an insulating material by the sum of vacuum permittivity epsilon naught times the electric field strength E in the dielectric, and the polarization P of the dielectric. This quantity is also called electric flux density, and it has the same SI unit as the polarization, that is Coulomb per square meter. As its definition shows, electric displacement is called the displacement field because it differs from the product of the vacuum permittivity and the electric field strength due to the displacement of the bound charges in atoms and molecules that make up materials when they are polarized in an electric field. In other words, electric displacement separating free charges from bound charges measures the free charge per unit area that is displaced across any material when an electric field is applied, as the name electric flux density indicates. For electric displacement, we can apply the so-called hydraulic analogy between a charged capacitor with a dielectric between its plates, and a pipe with a membrane that is completely filled with water. In this analogy, the electric field E between the plates with positive and negative charges is equivalent to the pressure gradient in the water, or the difference delta P between the pressures P1 and P2 of the two chambers in the pipe separated by the membrane. The electric polarization P in the dielectrics due to the electric field E representing the displacement of bound charges is equivalent to the actual deformation of the membrane stretched by the incompressible fluid. The latter means that a given amount of water is displaced in both sides of the membrane, and the volume of the displaced liquid is proportional to the difference delta P in the pressure, as in the case of the capacitor where the polarization and the electric displacement are proportional to the potential difference between the plates. The hydraulic analogy between electricity and pipes and chambers filled with water is a more general method, and as we will see, it is also applied to study electric current produced by moving charge carriers and conductors. Hence electric circuits can be modeled by hydraulic circuits. By introducing the electric displacement field D, we can substitute its definition into Gauss's law derived for polarized dielectrics, and write Gauss's law for the general case in a simple form stating that the surface integral of the electric displacement D over an arbitrary closed surface is equal to the free charge Q enclosed within that surface. Then Gauss's law for dielectrics tells us that the displacement flux passing through an arbitrary closed surface is equal to the free charges or their algebraic sum within the surface. This equation indicates that the force lines of the displacement field originate and end only on free charges, and the electric displacement therefore depends only on free charges and not bound charges. As a result, we can ignore the specific properties of dielectric materials with polarization charges, which simplifies the calculations. In the specific case of a polarized insulating material between the plates of a capacitor with a constant charge, the electric displacement is independent of the nature of the dielectric. The situation is different for a capacitor with a constant voltage, where the amount of free charges on its plates depend on the dielectric material inserted into the space between the plates. Because the free charges per unit area on the plates can be different for different dielectrics, besides the constant voltage applied to the capacitor, the properties of the insulating material also determines the electric displacement field between the plates. In the figure, the insulating material does not fill the whole space between the plates of the charged capacitor, and there are gaps between its plates and the adjacent boundary surfaces of the dielectric. The density of the force lines of the electric field indicates that the electric field strength E0 due to the free charges plus and minus Q on the plates is greater in the gaps than in the insulating material, as already shown. In a vacuum or in the air filling the gaps, the polarization vector P vanishes and the displacement D is simply given by epsilon naught times the field strength E0. If the dielectric is isotropic and the electric field is uniform in the dielectric, then the electric field strength E, the electric displacement D, and the polarization P point in the same direction, and they have constant magnitudes. The vector field D is the same both in the gap and the insulating material, since the presence of the polarization field P in the dielectric reduces the field strength from E0 to E there. The fact that the displacement field is only related to free charges can also be illustrated by the force lines of the field starting from the positive free charges Q and terminating at the negative ones on the plates of the capacitor. Here the polarization charges at the boundary of the dielectric have no any role whatsoever. Conversely, the polarization field P is only related to the bound charges, and its force lines originate at the positive polarization charges Q' and end at the negative ones. Only the electric field E have a direct relation to both types of charges, where the difference in the density of its force line indicates the presence of these charges, as seen in the first figure. We can express the total amount of free charges Q within any volume V by the volume integral of the volume charge density ρ of the free charges over the volume V, and apply Gauss's divergence theorem for the integral form of Gauss's law. Then we immediately obtain the differential form of Gauss's law, stating that the divergence of the electric displacement vector D at any point is equal to the volume charge density ρ of the free charges at that point. This formula indicates that free charges are the direct sources of the electric displacement field, that is, the electric flux density at any point is given by the density of the free charges at that point. Again, the presence of bound charges in the dielectric does not play any role as a direct source for the displacement. However, polarization influences displacement indirectly, and it can be shown that the spatial variation in the polarization field has a contribution to the displacement field in dielectrics as well. In fact, the integral or differential form of Gauss's law describing the relation between electric displacement and free charges constitutes one of the fundamental equations of electrodynamics called Maxwell equations. As already explained, the electric field lines always originate and end on free or polarized charges. Hence, there are no closed electric field lines and the field is non-rotational even within dielectrics. Consequently, the other fundamental law of electrostatics derived for a vacuum also applies to dielectrics, according to which the line integral of the field strength E along any closed curve is equal to 0. This means that the electrostatic field E is curl-free not only in a vacuum but also in dielectrics, which constitutes another Maxwell equation in electrostatics. If we calculate the curl of the displacement field D for a dielectric in an electrostatic field and apply the non-rotational property of the latter, then we can see that it is equal to the curl of the polarization P in the dielectric. This result indicates that the spatial variation in polarization has an influence on the displacement field, and as already stated, it is due to the non-curl-free part in the Helmholtz decomposition of the vector field of polarization. If we want to illustrate a general situation in electrostatic, then we can consider an arbitrary set of conducting bodies with free electric charge described by the volume charge density ρ producing the electric field E or the displacement field D, and some dielectric material placed in this field with the polarization described by the vector field P, where the surface and volume distribution of the polarization charges are given by the densities sigma P and ρP. We note that in the case of conductors, free charges can only be found on the boundary surfaces of the bodies, and the volume charge density ρ is the general form of their singular surface charge distribution. Then the general form of the fundamental equations in electrostatic consists of the two Maxwell equations stating that the divergence of the electric displacement D is equal to the volume charge density ρ of the free charges, and that the electric field E is always curl-free. Here the relation between the vector fields E and D is described by the equation stating that the displacement vector D is equal to the product of the vacuum permittivity epsilon naught and the electric field strength vector E, plus the polarization vector P. We need to supplement the two Maxwell equations with the other three equations describing the polarization field, where the first equation states that the surface charge density sigma p of the polarization charges is equal to the dot product of the polarization vector p and the surface normal n of any polarized dielectric pointing outward from its boundary surface. The second equation states that the volume charge density ρ p is given by the negative divergence of the polarization vector field p, and the third equation states that the polarization field p must vanish outside any dielectric. This set of equations contains three scalar fields such as the volume charge density ρ of free electric charges, the volume charge density ρ p of polarization or bound charges, and the surface charge density sigma p of polarization charges. We note that the later can be included as a singular charge density distribution in the volume charge density of polarization charges, as the volume charge density of free charges includes the distribution of free charges over the boundary surfaces of conductors. Although these scalar fields are the sources of the vector fields appearing in the Maxwell equations, the vector fields also have influence of the spatial and surface distribution of free and polarization charges. These equations contain only two vector fields that can be considered as independent quantities, the electric field strength E, and the polarization field P, or alternatively the displacement field D. This shows that while we only need the vector of the electric field strength E to describe the electrostatic field in a vacuum, it is also necessary to know the vector of the polarization P or the electric displacement D to describe electric fields in matter, and the two fundamental equations must be supplemented with another vector equation. In order to provide that vector equation, we basically need to determine the polarization vector from the properties of the polarized dielectric material. If the atomic structure of matter is known, then in principle it is possible to calculate the displacement of electrons and nuclei when an insulating material is placed into an electric field. Obviously, in this way we obtain different and very complicated descriptions for the polarization depending on the specific cases. There is no universal relationship between polarization and electric field that applies to all materials, and we have to rely on experiments to determine the missing equation mentioned above. For a significant part of dielectrics and a wide range of phenomena, experiments show that the relationship between the vectors of polarization and electric field strength is linear and homogeneous. Such a law can be explained by the fact that the macroscopic field strength is usually very small compared to the internal microscopic field strength of atoms and molecules. If the medium is isotropic, then the vectors of the polarization in the medium and the electric field applied to the medium are unidirectional, and the relationship between them is described by the equation stating that the polarization P is equal to a dimensionless constant chi times the vacuum permittivity epsilon naught times the electric field strength E. Chi is called the electric susceptibility of the medium, and it is the quantitative measure of the extent to which an electric field applied to a dielectric material causes polarization. This table shows the electric susceptibility and the relative permittivity for a vacuum and some substances from air with the lowest values to water with the highest ones. Here we can see that these values span several orders of magnitude, indicating their strong dependence on the atomic or molecular structures of different substances. We define the electric displacement vector D by the sum of epsilon naught times the vector E and the vector P. By substituting the relation between the vectors P and E into this equation, we can write the vector D as epsilon naught times 1 plus chi E times the vector E. We already saw that Gauss's law for isotropic dielectric states that the surface integral of the electric field E over a closed surface is equal to the free charge Q enclosed by the surface over the product of the vacuum permittivity epsilon naught and the relative permittivity epsilon R of the dielectric within the closed surface. It was also shown that Gauss's law can be written in the form stating that the surface integral of the electric displacement D over a closed surface gives the free charge Q enclosed by that surface. If we substitute the expression obtained for the electric displacement D into the second integral equation and compare the result with the first equation, then we find that the electric displacement D of linear dielectrics, in which the polarization is directly proportional to the electric field, is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon R of the dielectric, times the electric field strength E. As a result, we can express the relative permittivity epsilon R as 1 plus the electric susceptibility chi E of the dielectric. This relationship between epsilon R and chi E R can be seen in the table as well. Maxwell equations in electrostatic must be supplemented with any of the vector equations derived here for either the polarization or the displacement field describing a material's response to an electric field applied on a body made of the given material. We established that isotropic dielectric materials have a linear response for external electric fields, that is, the relationship between the displacement field in a dielectric is directly proportional to the electric field applied to the medium. However, There are also anisotropic materials such as crystals, layered substances and structural or composite materials, where the relationship between polarization and electric field is more complicated and its mathematical expression must be generalized. In a more general description for polarization in anisotropic dielectrics, each component of the polarization vector is given by the linear combination of the components of the electric field strength. Then in a Cartesian coordinate system, the x component of the polarization vector P can be written as the vacuum permittivity epsilon naught times the sum of the constant chi sub x times the x component of the electric field strength E, the constant chi sub xy times the y component of the electric field strength E, and the constant chi sub xz times the z component of the electric field strength E. We have a similar equation for the y component of the polarization P with the constant coefficients chi sub yx, chi sub yy and chi sub zy, whereas the constant coefficients in the equation for the z component of the vector P are denoted by chi sub zx, chi sub zy, and chi sub zz. Hence, we can write the ith component of the polarization P, where the index I denotes the coordinates x, y, and z, as the vacuum permittivity epsilon naught times the sum of chi sub ig times the j'th component of the electric field strength for the index j running through the coordinates x, y, and z. As an example for anisotropic dielectrics, we show the toy model of the unit cell of the alpha quartz crystal made up of silicon and oxygen atoms. The model illustrates the internal structure created by the chemical bonds between the atoms, where the physical properties of the crystal differ depending on the direction of the measurement. If the unit vectors Ex, Ey, and Ez are oriented along the faces of the unit cell as seen in the figure, then the polarization vector and the electric field strength can be expanded in this basis, and we obtain the component equations shown in the left-hand side. These equations represent a single vector equation with a matrix vector multiplication, where the polarization vector P is equal to epsilon naught times a matrix with the elements of the coefficients chi sub ij, times the vector of the electric field strength E. In fact, the elements in the matrix can be interpreted as the components of a second-rank tensor, and we can introduce the electric susceptibility tensor chi-e as a linear map transforming vectors into vectors, where its scalar multiplication with the vacuum permittivity maps the electric field strength E onto the polarization vector P at any point of a dielectric. Then the evaluation of this second-rank tensor in a specific Cartesian basis gives the elements chi sub ij of the matrix representation of the tensor in that basis. Because the form of the components equations is invariant under basis transformations, the matrix vector product in the vector equation can be interpreted as the contraction of a second-rank tensor with a vector. In other words, the polarization vector P in an anisotropic material is given by the vacuum permittivity epsilon naught times the contraction of the electric susceptibility tensor chi-e of the material with the vector of the electric field strength E applied to the material. Based on this interpretation, we can also generalize the relative permittivity of an anisotropic dielectric, and consider it as a second-rank tensor denoted by epsilon. That is, epsilon is a linear map between three-dimensional vectors, and the vacuum permittivity epsilon naught times the relative permittivity tensor epsilon transforms the electric field strength E into the electric displacement D. Thus the electric displacement field D is equal to the vacuum permittivity epsilon naught times the contraction of the relative permittivity tensor epsilon of the anisotropic dielectric and the electric field strength E applied to the dielectric. This tensor equation can also be expanded in a given Cartesian basis, providing the component equations of the displacement vector D. As a consequence of the tensor interpretation of the relative permittivity and the electric susceptibility for anisotropic materials, we can also generalize the relationship between them and state that the relative permittivity tensor epsilon is equal to the sum of the second-rank unit tensor I and the electric susceptibility tensor chi-e. Or in a basis expansion, the components epsilon sub ij of the relative permittivity tensor are given by the sum of the Kronecker delta representing the components of the unit tensor, and the components chi sub ij of the electric susceptibility tensor. Since the choice of the Cartesian basis is arbitrary, one can adapt this basis to the symmetries in the structure of the unit cell. Here we can see the hexagonal structure of the alpha quartz crystal projected onto its basal plane. This projections reveals that the crystal has a principal axis of threefold symmetry called C-axis, that is the rotation by 120 degrees or 240 degrees around this axis results in an identical structure. There are other three equivalent two-fold diagonal axes called A-axes that are perpendicular to the C-axis and separated by 120 degrees from each other. We can choose the Cartesian basis vectors so that they form the trigonal system of the crystal, where the xy plane is the plane of isotropy spanned by the diagonal axes, and the z-axis points in the direction of anisotropy determined by the c-axis. For example, the basis vector Ex can point in the direction of the axis A1, where the y-axis lies in the plane of isotropy with the vectors Ex and Ey perpendicular to each other, and the vector Ez points in the direction the c-axis. In the trigonal system of the alpha quartz crystal, the matrix representing the electric susceptibility tensor of the crystal becomes diagonal with the two-fold degenerate eigenvalue denoted by chi-perp, that is the principal value of the susceptibility in the plane of isotropy, and the eigenvalue denoted by chi-parallel, that is the principal value of susceptibility in the direction of anisotropy. By adapting the coordinate system to the symmetries of an anisotropic dielectric, we can therefore reduce the matrix representation of the electric susceptibility of the insulating material to the set of its eigenvalues in the principal axis system of the anisotropy, which simplifies the calculations involving susceptibility. We can also diagonalize the matrix representing the relative permittivity tensor of the alpha quartz crystal in its trigonal system, and use the eigenvalues epsilon perp and epsilon parallel in calculations. We have derived the vector equations describing the relationship between polarization and the external electric field, producing it in both isotropic and anisotropic dielectrics. However, in most cases insulating materials exhibit nonlinear properties, and only a tensorial expansion with respect to the components of the electric field strength can characterize the vectors of the polarization and the displacement due to an external electric field properly. In such a case, the components of the vectors P and D are given by the following infinite sums with a cutoff for a given accuracy, where we show the first and second order terms of the expansions. In the first order terms of the expansions, we recognize the matrix representations of the tensors chi sub ij and epsilon sub ij of rank 2 for electric susceptibility and relative permittivity. Their 3 times 3, that is 9 components, describe the anisotropy of the nonlinear material in the first order. The second order terms contains the third rank tensors chi sub ijk and epsilon sub ijk, represented by 3 times 3 matrices, that is 27 components. These terms are responsible for nonlinear optical effects related to the propagation of electromagnetic waves in matter. The fast increase in the number of parameters as the higher order terms are also taken into account in the expansion, indicates that the description of the behavior of a nonlinear dielectric in an electric field is a challenging task, and we need both experimental data and theoretical models based on the molecular structures of materials. It is also interesting to determine the condition for a non-vanishing volume density of polarization or boundary charges, that is when such charges are present in dielectric materials. For the sake of brevity, we restrict our attention on the behavior of isotropic insulating materials with first-order effects when an electric field is applied to them. In the polarization volume charge density ρP expressed as the negative gradient of the polarization P, we can replace the polarization with the product of the vacuum permittivity epsilon naught and the electric susceptibility chi E of the isotropic dielectric, times the electric field strength E applied to the medium. Here epsilon naught is a constant, and the divergence of the product is equal to epsilon naught times the sum of the dot product of the vector E and the gradient of chi E, and chi E times the divergence of the vector E. Considering the fact that polarization or bound charges are just as much the source of electric field as free charges, Gauss's law can be written in a form where the divergence of the electric field E is equal to the sum of the free and the polarized volume charge densities ρ and ρP over the vacuum permittivity epsilon naught. If we substitute this expression into the right-hand side of the equation for ρP, then we obtain minus epsilon naught times the sum of the directional derivative of chi E along the vector E and chi E times ρ, minus chi E times ρP. By solving this equation for ρP, the polarization volume charge density can be written as -1/1 plus the electric susceptibility chi E, times the sum of the vacuum permittivity epsilon naught times the directional derivative of chi E in the direction of the electric field strength E, and chi E times the charge density ρ. This result tells us that the volume density of polarization charges can differ from 0 in 2 cases. If the insulating material is non-homogeneous where the gradient of the susceptibility is not equal to 0, or the volume density of free charges at a given point in the dielectric differs from 0. If there are no free charges in the dielectric, then the volume density of the bound charges can be reduced to negative epsilon naught over 1 plus chi E, times the directional derivative of chi E along the vector E. The figure shows the level curves of the electric susceptibility chi E in an inhomogeneous dielectric, where the directional derivative is represented by the projection of the gradient vector of chi E onto the vector E at the point P. This illustrates the fact that polarization charges are present at the point P in the dielectric if the gradient of the electric susceptibility is not perpendicular to the electric field applied to the insulating material. After the discussion on the polarization of dielectrics in a uniform electric field of a charged parallel plate capacitor, we consider other examples to study the electric field in insulating materials. We start with the case of two parallel infinite plates with the constant charge densities positive and negative sigma prime. We already proved that if there is only a vacuum or air between the infinite parallel planes, then the electric field E0 due to the opposite charges distributed uniformly over the planar surfaces is a uniform vector field pointing from the positively charged plane to the negatively charged one, and its magnitude between the plates is given by the surface charge density sigma over the dielectric constant epsilon naught of a vacuum. The electric field strength E0 vanishes elsewhere. In this example, the electric field is characterized by both the field strength E0 and the electric displacement D0 that is equal to the vacuum permittivity times the field strength E0. If a homogeneous and isotropic dielectric is introduced into the electric field E0, then the insulating material becomes polarized due to this field, and bound or polarized charges appear on the surface of the dielectric with the negative and positive surface charge density sigma prime. These bound charges produce a field strength E prime inside the dielectric with the magnitude of sigma prime over epsilon naught. Outside the dielectric, the field strength E prime is equal to 0. Since E0 and E prime are in opposite directions, the magnitude of the resultant field strength E inside the dielectric is equal to the difference between the magnitudes of E0 and E prime. If we substitute the expressions obtained for the magnitudes of E0 and E prime into the right-hand side, then the magnitude of the electric field E can be written as 1 over the vacuum permittivity epsilon naught, times the difference between the surface charge densities sigma and sigma prime. Outside the dielectric, the magnitude of the electric field E is equal to the magnitude of the electric field E0. Because the polarization field produced in the dielectric by the resultant electric field is perpendicular to the boundary surface of the dielectric, the normal component of the electric field is equal to its magnitude. We already saw that the polarization P in a linear and isotropic dielectric is equal to the vacuum permittivity epsilon naught, times the electric susceptibility chi-e of the dielectric, times the electric field strength E. We also proved that the polarization surface charge density sigma prime at the boundary of a dielectric is given by the component of the polarization field P in the direction of the normal vector pointing outward from the surface of the insulating material. Then the polarization surface charge density sigma prime can be written as epsilon naught times chi-e, times the magnitude of the electric field strength E. By substituting this result into the equation obtained for the magnitude of the electric field E, we can write the later as the difference between the magnitude of E0 and chi-e times the magnitude of the electric field E. If we solve this equation for E, then we can state that the magnitude of the net electric field E in a polarized dielectric is equal to the magnitude of the external electric field E0 applied to the dielectric, over 1 plus the electric susceptibility chi-e of the insulating material, or the magnitude of E0 over the relative permittivity epsilon r of the dielectric. The relationship between E and E0 shows that relative permittivity measures how much the electric field is weakened in a homogeneous and isotropic dielectric with an infinite extension inserted into the space between two uniformly charged infinite planes. In order to determine the electric displacement field inside and outside the dielectric, we consider the relationship between the electric field strength and the insulating material and a vacuum or air, stating that the magnitude of the field strength E is equal to the magnitude of the field strength E0 divided by the relative permittivity epsilon r of the dielectric. Now we multiply this equation by epsilon naught times epsilon r, where the left-hand side becomes epsilon naught times epsilon r times the magnitude of E, and the right-hand side is equal to epsilon naught times the magnitude of E0. In the left-hand side of this equation we can recognize the magnitude of the electric displacement D, whereas the right-hand side can be identified as the magnitude of the electric displacement D0 outside the dielectric. This result indicates that the electric displacement inside the dielectric between the infinite parallel surfaces is the same as the electric displacement of the external field produced by the homogeneous surface charge distribution over those surfaces. Since the magnitude of D given by epsilon naught times the magnitude of the electric field E0, where E0 is equal to the surface charge density sigma over epsilon naught, we conclude that the magnitude of the electric displacement D of the field, which is also the electric flux density of the field, is equal to the surface density sigma of the free charges uniformly distributed over the two infinite planar surfaces. In the case under consideration, the homogeneous and isotropic dielectric completely fills the part of the space where the electric field produced by the free charges is different from zero. This is the situation if there are no gaps between the infinite planes and the boundary surfaces of the dielectric seen in the figure. Then the magnitude of E is equal to the magnitude of E0 over epsilon r, and the vectors E, E0, E' and D are parallel with each other. A similar result is obtained if the homogeneous and isotropic dielectric does not completely occupy the space between the two parallel planes where E0 does not vanish, but only a part of this space that is determined by the equipotential surfaces of the electric field due to the free charges. In the figure, the vertical boundary surfaces of the dielectric are also equipotential surfaces of the electric field. In fact, we already obtained these results for charged parallel plate capacitors with a dielectric between their plates, where we assume that the electric field is approximately uniform between the plates if the distance between the plates is much smaller than their dimensions. These results, however, do not hold in the case when the homogeneous and isotropic dielectric does not completely fill the space defined by the electric field of free charges, or the volume enclosed by the corresponding equipotential surfaces. Then the vectors d and epsilon naught times E naught are not coincident, and the field strength E inside the dielectric is therefore not equal to the field strength E naught produced by the free charges divided by epsilon naught. This figure shows the electric field in a dielectric layer that is inclined with respect to the parallel plates carrying the free charges. As indicated by the field lines, the vector E' is perpendicular to the surface of the dielectric, hence the vectors E and E naught are not parallel with each other. The direction of the vector d is the same as that of the vector E, since the polarization vector P is proportional to the vector E for homogeneous and isotropic dielectrics. Consequently, the directions of the displacement vectors are different outside and inside the dielectric. It can be shown that they have different magnitudes as well if the boundary conditions are established for the vectors E and d on the surface of the dielectric. We will study such boundary conditions after presenting some examples for the electric field in bodies made of insulating materials. In the first example, let us consider a conducting sphere of radius R with a positive electric charge Q that is surrounded by an infinitely large homogeneous and isotropic insulating medium of electric susceptibility chi-e and relative permittivity εr. We already proved that a charged conducting sphere produces an electric field in a vacuum or air as if all of its net charge were concentrated at its geometric center. Thus, at a point P at a distance r from the center of the sphere, the magnitude of the electric field strength E naught is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge Q over the square of the distance r. We also saw that the field strength vanishes inside the conducting sphere. Under the influence of the field of the charged sphere, the dielectric is polarized and the bound charges Q' appear with the opposite sign to Q over its surface in contact with the sphere, which can be described by the polarization surface charge density sigma prime. The later is equal to the electric susceptibility chi-e of the dielectric, times the vacuum permittivity epsilon naught, times the net electric field E over the surface of the sphere evaluated at the radius R of the sphere. The total amount of polarization charge Q' over the surface of the sphere is equal to the polarization surface charge density sigma prime, times the surface area of the sphere, that is 4 pi times the square of the radius R. If we substitute the expression for sigma prime into this equation, the polarization charge can be written as 4 pi times R squared, times chi-e times epsilon naught, times the magnitude of the net electric field E evaluated at R. The magnitude of the electric field strength E' at the point P due to the polarization charges Q' distributed over the surface of the sphere is equal to 1 over 4 pi epsilon naught, times the amount Q' of the polarization charges over the square of the distance r. By substituting the expression obtained for the polarization charge Q' into this equation, we can write the magnitude of E' as chi-e times the ratio of R squared to r squared, times the magnitude of E evaluated at R. Here the magnitude of the net electric field E given by the difference between the magnitudes of E naught and E' is equal to 1 over 4 pi epsilon naught, times the amount Q of the charges carried by the sphere over the square of the distance r, minus chi-e times the ratio of R squared to r squared, times the magnitude of E evaluated at R. Since the fields E naught and E' decrease in inverse proportion to the square of the distance from the center of the sphere even in the dielectric, this must be the case for their superposition, that is the net field E as well. Then we can write that the ratio of the magnitude of the electric field E evaluated at the radius R to its magnitude evaluated at the radius r, is equal to the ratio of r squared to R squared. As a result, we can express the magnitude of E evaluated at r as the ratio of R squared to r squared, times the magnitude of E evaluated at R. We can recognize the right-hand side of this equation in the second term an expression obtained for the magnitude of the net electric field E evaluated at r, and write it as the difference between the magnitude of the electric field E naught and the electric susceptibility chi-e times the magnitude of the electric field E evaluated at r. If we solve this equation for E naught, then the magnitude of the electric field produced by the free charges Q on the surface of the conducting sphere can be written as 1 plus the electric susceptibility chi-e of the dielectric, times the magnitude of the net electric field E. Or the magnitude of the net electric field E is given by the magnitude of the electric field E naught over 1 plus chi-e. That is the magnitude of E naught over the relative permittivity epsilon r of the dielectric. Consequently, the magnitude of the electric displacement d given by epsilon naught times epsilon r times the magnitude of E is equal to epsilon naught times the magnitude of E naught, which is equal to the magnitude of the electric displacement d naught produced by the free charges q. As in the case of the dielectric layer inserted between the charged infinite planes, the insulating medium completely fills the region of the space where the electric field E naught due to the free charges does not vanish. The equations also show that the electric fields E, E naught and E prime, and the electric displacement field d are parallel with each other. Then these results are exactly the same as those obtained for the polarized dielectric between the oppositely charged infinite parallel planes. In the next example we determine the electric field in thick spherical dielectric shells enclosing a charged conducting sphere. Here we consider a conducting sphere of radius R with the positive charge Q that is surrounded by two thick spherical shells made of homogeneous and isotropic insulating materials with the relative permittivity epsilon sub R1 and epsilon sub R2. The outer radii of the shells are denoted by R1 and R2. In a vacuum the charged sphere produces the spherically symmetric electric field E naught pointing outward outside the sphere. Inside the conducting sphere the electric field and the electric displacement vanish. The electric field polarizes the dielectric shells that produces the surface charge densities sigma prime 1 and sigma prime 2 over the boundaries of the thick shells. If we apply Gauss's law for a spherical Gaussian surface enclosing the sphere and the shells, then we can write that the surface integral of the electric displacement field d over any such closed surface is equal to the free charge q within that surface. Since the displacement field is spherically symmetric, the surface integral is given by the magnitude of the displacement field d over the Gaussian surface, times the area of the surface, that is 2 pi times the square of the radius r of the sphere that is greater than the outer radius r2 of the outer shell. But we already saw that the electric displacement is independent of the properties of dielectric materials and their presence can be ignored. Hence this equation holds everywhere outside the charged sphere, and we can express the magnitude of the electric displacement d at any point p outside the sphere as 1 over 4 pi, times the charge q over the square of the distance r of the point from the center of the sphere. This equation does not contain any constant describing the properties of the dielectric shells, and the displacement field d in the shells is equal to the displacement field d naught in a vacuum. The formula also shows that the magnitude of the displacement d at the radius R of the conducting sphere gives the ratio of the free charge q to the surface area of the sphere, that is the surface charge density sigma of the free charges. The relationship between the net electric field and the inner dielectric shell is given by the formula stating that the displacement vector d is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon sub r1, times the net electric field E in the shell. If the absolute dielectric constant of the insulating material in the shell that is the product of epsilon naught and epsilon sub r1 is denoted by epsilon 1, then the magnitude of the displacement d can be written as the absolute permittivity epsilon 1 times the magnitude of the electric field E in the shell. As a result, the magnitude of the electric field E at any point p in the inner shell made of dielectric material is given by 1 over 4 pi times the absolute permittivity epsilon 1 of the dielectric, times q over the square of the distance r of the point p from the center. The net electric field E in the shell is obviously the superposition of the field E naught due to the free charges q and the electric field E prime due to the polarization surface charges sigma prime over the boundary of the inner shell at the surface of the conductive sphere. We can write a similar expression for the relationship between the displacement and the electric field in the outer shell, and state that the magnitude of the displacement d is equal to the absolute permittivity epsilon 2 of the dielectric material in the shell, times the magnitude of the electric field E in the shell. Then the magnitude of the electric field strength E has the same expression as in the case of the inner shell where the absolute permittivity epsilon sub R2 appears in the multiplication factor instead of epsilon sub R1. The net electric field in the outer shell is the superposition of the electric field E naught, the electric field E prime and the electric field E prime 1 due to the polarization surface charge density sigma prime 1 over the boundary between the two shells at the radius R1. Outside the shells the displacement d is equal to epsilon naught times the electric field strength E. Hence, the magnitude of E at any point p outside the outer shell is given by 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge q over the square of the distance r between the point p and the center. Evidently, the superposition of the electric fields E prime and E prime 1 with the field E prime 2 due to the polarization surface charge density sigma prime 2 over the boundary at the radius R2 vanishes, and the net electric field is equal to E naught due to the free charges q. That is, the electric field in this region is the same as the field of the point charge in a vacuum. Here we show the field of the electric displacement d for the whole space that is produced by the conducting sphere of radius r carrying the positive charge q. As already mentioned, the field vanishes inside the conducting sphere. Outside the sphere it is a spherically symmetric field pointing outward with the magnitude inversely proportional to the square of the distance from the center of the conducting sphere. Its direction at any point P is determined by the position vector r of the point with respect to the center. The dielectric shells have no any role for the displacement field around the charged sphere whatsoever. The case is different for the electric field due to the free charges of the conducting sphere. Although the field also vanishes in the conductor, it is described by a different expression in each region outside the sphere. The electric field outside the conductor is still spherically symmetric and its magnitude is inversely proportional to the square of the distance from the center. However, it is discontinuous not only over the boundary between the conducting sphere and the inner shell, but also over the boundary between the two shells and the outer boundary of the outer shell. This fact is the direct consequence of the presence of the different dielectric constants in the expressions shown for each region. The ratio between the magnitudes of the electric field for the two sides of the boundaries is given by the inverse ratio between the dielectric constants at the two sides of the interfaces between the different media. In the previous examples, the electric field produced by the bound charges differs from zero only within the dielectric due to the shape of the polarized dielectric material. However, in general the electric field E' does not vanish outside the polarized dielectric. In the next example, we consider a dielectric rod which a uniform electric field E0 is applied to such that the symmetry axis of the rod is parallel with the field lines. Due to the polarization of the dielectric material in the body, opposite electric charges will appear at the two ends of the rod. Outside the rod, the electric field E' produced by these polarization charges is the same as the field of an electric dipole. As the figure shows, the resultant electric field strength E is greater than the external field strength E0 in the vicinity of the two ends of the rod. In the middle region around the rod, the net electric field E is weaker than the electric field E0 applied to the dielectric. Some of the electric field lines originating from and terminating at the polarization charges on the base faces at the two ends of the rod run inside the dielectric, where the electric fields E' and E0 have opposite directions. As a result, the net electric field E is also weaker than the external field E0 in the dielectric. The effect where the electric field due to polarization reduces the strength of the electric field applied to the dielectric is also called polarization screening or depolarization. The resulting field strength is usually not uniform outside or inside the body. The electric field produced by a polarized dielectric acting against the field polarizing the dielectric obviously depends on the orientation and the shape of the dielectric material. Consequently, we need to introduce a second-rank tensor called depolarization tensor to characterize this effect, which is defined by the equation stating that the electric field E' due to polarization is equal to -1 over the vacuum permittivity epsilon naught, times the contraction of the depolarization tensor n with a polarization field P in the dielectric. This equation can be expanded in any Cartesian basis adapted to the symmetry of the problem, stating that the I component of the electric field E' is given by -1 over epsilon naught, times the sum of the tensor component n sub ij times the j component of the polarization vector P, where the indices I and j are x, y, and z. As a special case, we consider an ellipsoid made of an isotropic and homogeneous dielectric material, and apply a uniform electric field E0 to it that is parallel with one of the principal axes of the ellipsoid. Then the matrix representation of the depolarization tensor can be diagonalized in the principal axis system of the ellipsoid, and it is enough to use only its three principal values to determine the components of the electric field E'. If any of the coordinate axes is directed along the polarization vector and the corresponding principal axis of the ellipsoid, then we obtain a simple vector equation stating that the electric field E' is equal to -1 over epsilon naught times the product of the corresponding principal value of the depolarization tensor n and the polarization vector P. In this case, the principal value n is called the depolarization factor of the dielectric ellipsoid. For a homogeneous and isotropic insulating material where the polarization vector P is proportional to the uniform electric field E0 applied to the ellipsoid in the direction of one of its principal axes, this result tells us that the net electric field E due to depolarization is also uniform in the ellipsoid, and opposite to the field E0. Consequently, in the case of a homogeneous and isotropic dielectric ellipsoid aligned with the external field E0, the net electric field E given by the superposition of the fields E0 and E' can be written as E0 minus 1 over epsilon naught times n times P. For a linear dielectric, the polarization vector P is given by the vacuum permittivity epsilon naught times the electric susceptibility chi E of the dielectric times the net field strength E in the dielectric. Then in the right-hand side of the equation we have E naught minus chi E times N times E. We can express the net electric field E from this equation as the electric field E naught divided by 1 plus the depolarization factor N times the electric susceptibility chi E. We also know that the relative permittivity epsilon R of the dielectric is equal to 1 plus the electric susceptibility chi E, which gives E naught over 1 plus N times epsilon R minus 1. In the special case of a dielectric sphere, all the principal values of the depolarization tensor are equal to 1 over 3, that is the depolarization factor N in the last equation is given by 1 over 3. Then for a sphere we can write the net electric field E as 3 times over epsilon R plus 2, times the electric field E naught. This formula is also valid if the uniform electric field E naught exists in a medium with a dielectric constant epsilon 1 instead of a vacuum, that surrounds a sphere with a dielectric constant epsilon 2. We only need to write the ratio of epsilon 1 to epsilon 2 instead of epsilon R in the formula. If this ratio is greater than 1, the resultant electric field E is weaker than the electric field E naught applied to the medium and the sphere, otherwise E is greater than E naught. The figures illustrate the two cases with the distribution of the electric field lines in the dielectric sphere and the medium surrounding it. When we studied the electric field and displacement inside and outside dielectric materials, we mentioned that the boundary conditions on these field quantities over surfaces and interfaces are important to provide the complete description of these fields. If two homogeneous and isotropic media with different dielectric constants are in contact with each other over an interface which can be considered flat in a small environment, then we assume that the vectors of the electric field E and the electric displacement d change at the interface when we cross the interface. Let E1 and E2 denote the vectors of the electric field in the two media with the absolute dielectric constants epsilon1 and epsilon2 with a boundary interface separating them. Similarly, we denote the vectors of the electric displacement by D1 and D2 in the two dissimilar dielectrics. At a given point of the boundary interface with the surface normal n, we can decompose the electric field strength and the displacement vector into tangential and normal components with respect to a plane approximating the boundary in a small vicinity about the normal vector n. The task is to determine the boundary conditions for the tangential and normal components of these vector fields over this small flat boundary surface area. In order to do this, we apply the second Maxwell equation in electrostatics telling us that the electric field is curl-free, that is the line integral of the field strength E of an electrostatics field along any closed contour is equal to 0. Now we determine the line integral of the electric field E along a closed contour defined by the rectangle with the corner points A1, B1, B2, and A2 enclosing the boundary interface between the dissimilar dielectrics such that its longer sides are parallel with the interface in a small vicinity where the boundary can be considered flat. Then the line integral of the field strength E along the rectangle can be broken up to 4 line integrals along the sides of the rectangle, that is the line integrals along the straight sections between the points A1 and B1, between the points B1 and B2, between the points B2 and A2, and between the points A2 and A1. For the curl-free electrostatics field, the algebraic sum of these line integrals of the field must vanish. Since the closed contour along which we determine the line integral of the field strength is arbitrary, we can deform the rectangle such that its height tends to 0. That is the corner points A1 and A2 of the rectangle will approach the point A of intersection between the vertical left-hand side of the rectangle and the horizontal boundary interface, whereas the points B1 and B2 will approach the point of intersection B in the right-hand side. As a result, the length of the straight section between the points A1 and A2 along which the field strength E is integrated tends to 0. Similarly, the straight section between the points B1 and B2 along which the field strength E is integrated, also shrinks to a point. Because the electric field E is assumed to be a finite physical quantity, the limits of the second and the fourth line integrals of the field strength along the sections of 0 length are also equal to 0. Then we only need to evaluate the first and the third line integrals on both sides of the boundary interface in this limit, which gives the following equation. The line integral of the field strength E1 at the side of the dielectric media of absolute permittivity epsilon1 along the straight section between the points A and B, plus the line integral of the field strength E2 at the side of the insulating material of absolute permittivity epsilon2 along the straight section between the points B and A, must vanish. Here the line integrals are calculated along two sections that are parallel with the boundary interface, that is we integrate the tangential components of the electric field strength on both sides of the interface. Consequently, the line integrals can be reduced to the integral of the difference between the tangential components of the electric fields E1 and E2 with respect to the distance L measured along the section connecting the points A and B. This integral is equal to 0, and for arbitrary points A and B over the flat interface the integrand must vanish. Then we conclude that the tangential components of the electric fields E1 and E2 on the two sides of the boundary interface must be equal to each other, that is, the tangential components of the electric field are continuous across the boundary interface between two dissimilar dielectric materials. This matching condition can also be formulated by stating that the difference between the electric fields on the two sides of the interface must be parallel with the normal vector n to the boundary at any point of the interface, that is, the cross product of the normal vector n and the vector subtraction of the electric field strength E2 from the electric field strength E1 vanishes. We already saw that for homogeneous and isotropic dielectric media the electric displacement d is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon r of the dielectric, times the electric field strength E in the dielectric. The right-hand side of this equation can also be written as the absolute permittivity epsilon of the dielectric times the field strength E. Then the matching condition of the tangential components of the electric field across the boundary interface gives the equation stating that the tangential components of the displacement d1 at the side of the dielectric of absolute permittivity epsilon 1 divided by epsilon 1 is equal to the tangential components of the displacement d2 at the side of the dielectric of absolute permittivity epsilon 2 divided by epsilon 2. In other words, the ratio of the tangential component of the displacement d1 to the tangential component of the displacement d2 is equal to the ratio of the dielectric constant epsilon 1 to the dielectric constant epsilon 2. This result gives another matching condition across the boundary stating that the tangential components of the displacement field are discontinuous across the boundary interface between two dissimilar dielectric materials. Here the ratio between the dielectric constants of the two dissimilar dielectrics is the measure of this discontinuity or jump in the displacement field across the interface. We saw as well that the electrostatic field E always vanishes in perfect conductors, which means its tangential component is equal to zero at the boundary surface of conducting materials. Then it follows from the matching condition for the tangential component of the electric field over the boundary surface, that the tangential component of the electric field must also vanish outside the conductor in the close vicinity of its boundary. Hence, the electric field lines always originate or terminate perpendicularly to the boundary surface of the conductor, as expected in electrostatic. Now we determine the boundary conditions imposed on the normal components of the field quantities over the boundary interface between the two dissimilar dielectric media. In order to do so, we apply the first Maxwell equation in electrostatic telling us that free electric charges are the source of the electric displacement field, that is the surface integral of the displacement field d over any closed Gaussian surface is equal to the free charge q within the surface. Since the Gaussian surface is arbitrary, we can determine the surface integral of the displacement field d over a cylinder of height h enclosing the interface between the dissimilar dielectrics with the circular bases b1 and b2 in its bottom and its top and the curved surface C. Here the circular bases of the cylinder are parallel with the plane approximating the boundary interface in the vicinity where the normal vector n is erected to the interface. Then the surface integral of the displacement d can be broken up to three surface integrals over the bases b1 and b2, and the curved surface C of the cylinder, where the surface elements ds in the integrals point outward from each surface. As in the case of the contour integral, we can also deform the Gaussian surface such that its height h tends to 0 while it will still enclose the same amount of free charges over the boundary interface. This means that the circular bases b1 and b2 approach the surface S defined by the intersection of the boundary interface and the circular surface of the cylinder with a height shrinking to 0. At the same time, the area of the curved surface C given by the product of the height h and the finite circumference of the cylinder also tends to 0. Consequently, the surface integral of the finite physical vector field d over the surface C of vanishing area is equal to 0 as the height h tends to 0, and we only need to evaluate the first and the second surface integrals on the two sides of the boundary interface in this limit. The surface element vector ds over the base surface b2 at the top of the cylinder is simply given by the normal vector n times the area element ds, whereas the same quantity for the base surface b1 at the bottom is given by the negative normal vector n times the same area element ds. As a result, the right-hand side of the equation can be written as the negative surface integral of the dot product of the displacement field d1 at the side of the dielectric medium of absolute permittivity epsilon 1 and the normal vector n over the flat surface S, plus the surface integral of the dot product of the displacement field d2 at the side of the dielectric medium of absolute permittivity epsilon 2 and the normal vector n over the flat surface S. This expression must be equal to the free charge q over the surface S. Then we can write that the integral of the difference between the normal components of the vector fields d2 and d1 over the area of the flat surface S is given by the free charge q over that surface. If sigma is the surface density of the free charge Q distributed over the surface S, then the right-hand side of this equation can be written as the integral of the surface charge density sigma over the area of the surface S. Because the choice of the cylinder, that is the surface S of its intersection with the plane approximating the boundary interface in a small vicinity is arbitrary, the integrands in the two sides of the equations must be equal to each other. Then we conclude that the difference between the normal components of the electric displacement fields d2 and d1 on the opposite sides of the boundary interface must be equal to the surface charge density sigma over the interface, that is the normal components of the displacement field are discontinuous across the boundary interface between two dissimilar dielectric materials, and the surface charge density is the measure of this discontinuity or jump in the displacement field across the interface. Evidently, without any free charge on the boundary interface, that is when the surface charge density over the interface vanishes, the normal components of the displacement field become continuous across the boundary interface. This matching condition can also be formulated by stating that the dot product of the normal vector n to the boundary interface at any point and the vector subtraction of the displacement field d1 from the displacement field d2 at that point is equal to the surface charge density sigma at that point. For homogeneous and isotropic dielectric media we can apply the relationship between the displacement vector and the electric field strength again, stating that the displacement D is equal to the absolute permittivity of the corresponding dielectric times the field strength E. Then the boundary condition gives an equation stating that the absolute dielectric constant epsilon 2 times the normal component of the field strength E2, minus the absolute dielectric constant epsilon 1 times the normal component of the field strength E1, is equal to the surface charge density sigma. This result indicates that the normal components of the electric field are also discontinuous across the boundary interface in the general case. If the two dielectric media with different dielectric constant are perfect insulators, then there is usually no free electric charge at the interface between them that can be transported from somewhere else. As already stated, for a vanishing surface density sigma of free charges over the boundary interface, the normal components of the displacement are continuous across the interface. Hence, the absolute dielectric constant epsilon 1 times the normal component of the field strength E1, is equal to the absolute dielectric constant epsilon 2 times the normal component of the field strength E2. Consequently, the ratio of the normal component of the field strength E1 to the normal component of the field strength E2, is given by the ratio of the absolute permittivity epsilon 2 to the absolute permittivity epsilon 1. This means that the normal components of the electric field are always discontinuous across the interface between dissimilar dielectrics, regardless of the presence of free charges over the interface. As in the case of the tangential components of the displacement field, the ratio of the dielectric constants of the two media is the measure of the discontinuity or the jump between the normal components of the electric field across the boundary interface. If there are free charges at the interface, the condition for the discontinuity also depends on the surface charge density sigma over the interface. As already mentioned in the case of the boundary condition imposed on the tangential component of the electric field vanishes inside a perfect conductor. If we suppose that one of the media separated by the boundary interface is a perfect conductor, for example the one with the dielectric constant epsilon 1, then both the normal and the tangential components of the electric field are equal to 0 within that material. The matching condition tells us that the normal component of the electric field E1 is given by the ratio of epsilon 2 to epsilon 1, times the normal component of the electric field E2 outside the conductor. Here the normal component of the field E1 inside the conductor vanishes. Since the field lines of the electric field and the dielectric medium are perpendicular to the surface of the conductor, its normal component is a finite non-zero quantity. Then the product in the right-hand side of the equation is equal to 0 only if the ratio of the dielectric constants vanishes. The absolute permittivity epsilon 2 of the insulating material outside the conductor is a finite non-zero quantity, and the ratio will vanish if the dielectric constant epsilon 1 is infinite. Therefore, in electrostatics perfect or ideal conductors are often treated as dielectric materials with infinite permittivity. After determining the matching conditions all the components of the field strength and the displacement field we summarize the results in the general case. The boundary conditions imposed on the field quantities across a boundary interface of an arbitrary shape between two homogeneous and isotropic dielectric media at any point on the interface with free surface charges gives the following set of equations. The first equation states that the projection of the discontinuity between the displacement fields d1 and d2 across the interface to the local normal n to the interface is given by the local surface density sigma of free charges over the interface. That is, the displacement field is only continuous in the normal direction if no free charges are present over the interface. The second equation is the consequence of the first one, where the displacement field is expressed in terms of the absolute permittivities epsilon1 and epsilon2 of the two dielectric materials and the field strengths E1 and E2 in them. This condition shows that the electric field always have a discontinuity in the normal direction with respect to the boundary interface, even if the surface density sigma of free charges vanishes over the interface. The discontinuity is determined by the dielectric constants of the two media, and the surface charge density sigma if free charges are present. Both of these equations impose constraints only on the normal components of the electric field strength and the displacement field, and we need other two equations for the boundary conditions of the tangential components of the field quantities. The third equation states that the electric field is always continuous across the boundary interface in the tangential direction with respect to the interface, as the vanishing cross product indicates that the discontinuity in the electric fields E1 and E2 is parallel with the normal vector n. For the last equation we express the vectors of the field strength in terms of the dielectric constants epsilon1 and epsilon2 and the displacement fields d1 and d2 in the third equation. As a result, we obtain a condition for the displacement field stating that it is always a discontinuity in the tangential direction with respect to the boundary interface. The jump in the tangential components across the interface depends on the ratio of the dielectric constants of the two media. This is the second set of boundary conditions imposed on the tangential components of the field strength and the displacement field across the boundary interface between two dissimilar dielectrics. As already discussed, these conditions are still valid if one of the media is a perfect conductor with an infinite dielectric constant. They also hold for a vacuum, where the absolute dielectric constant can be reduced to the vacuum permittivity on the side of the boundary where the space is empty. However, these boundary conditions are the consequence of the Maxwell equations describing the field quantities in electrostatics. If the electric field is time-dependent, then the same conditions must be derived from the full set of the time-dependent Maxwell equations describing the time evolution of the complete electromagnetic field in the two media separated with the boundary interface. It involves some modifications of the original equations due to the time evolution of the electric field generating a magnetic field. The equations derived for the electric field must also be supplemented with the equations of the boundary conditions for the quantities describing the magnetic field. As the consequence of the boundary conditions imposed on the field quantities across the boundary interface between two dissimilar dielectrics, we can prove the law of refraction for the field lines of the electric field and the displacement field at the interface. For the electric fields E1 and E2 at the boundary interface between the insulating media with the dielectric constants epsilon1 and epsilon2, let θ1 and θ2 denote the angles between the vectors of the electric field and the normal vector n to the interface. Then we have the following trigonometric relationships between the angles and the components of the electric field strength. The tangent of the angle θ1 is equal to the ratio of the tangential component of the electric field strength E1 to its normal component. Similarly, the tangent of the angle θ2 is given by the ratio of the tangential component of the electric field strength E2 to its normal component. For the linear dielectric materials considered here, the displacement field is proportional to the electric field strength, where the constant of proportion is the absolute dielectric constant of the medium. As a result, the electric field strength and the displacement field point in the same direction at any point of the dielectric media, and their components with respect to the normal vector have the same directions as well. Hence, the tangent of the angle θ1 can also be written as the ratio of the tangential component of the electric displacement field d1 to its normal component. Similarly, the tangent of the angle θ2 is equal to the ratio of the tangential component of the electric displacement field d2 to its normal component. As already seen, the boundary conditions derived for the field quantities with respect to the local orientation of the boundary interface between the two media provides the following relationships for the components of the field quantities in the media. The tangential components of the electric field strengths E1 and E2 are equal to each other across the interface, whereas the ratio between the tangential components of the displacement vectors d1 and d2 across the interface is given by the ratio of the absolute permittivity epsilon1 to the absolute permittivity epsilon2. For the normal components we obtain the following equations. The difference between the normal components of the displacement vectors d2 and d1 across the interface is equal to the surface density sigma of the free charges over the interface. Similarly, the difference between the product of the dielectric constant epsilon2 and the normal component of the field strength E2, and the product of the dielectric constant epsilon1 and the normal component of the field strength E1 across the interface, is given by the surface charge density sigma. Here we restrict our attention to the case where there are no free charges over the boundary interface, that is when the electric surface charge density sigma vanishes. Then we can reduce the boundary condition for the normal components of the displacement to the equation stating that the normal components of the displacement fields d1 and d2 are equal to each other across the interface. Similarly, the boundary condition for the normal components of the electric field strength will tell us that the ratio between the normal components of the field strengths E1 and E2 across the interface is given by the ratio of the absolute permittivity epsilon 2 to the absolute permittivity epsilon 1. By considering the trigonometric equations written for the angles theta 1 and theta 2, we can express the ratio of tangent theta 1 to tangent theta 2 as the ratio of the tangential component of the field strength E1 to its normal component, times the ratio of the normal component of the field strength E2 to its tangential component. If we apply the first boundary condition in the right-hand side of this equation, then we can reduce it to the ratio between the normal components of the field strengths E2 and E1. Now we use the fourth boundary condition, which gives the ratio of the dielectric constant epsilon 1 to the dielectric constant epsilon 2. We will obtain the same result for the displacement fields, if we express tangent theta 1 over tangent theta 2 as the ratio of the tangential component of the displacement vector d1 to its normal component, times the ratio of the normal component of the displacement vector d2 to its tangential component. Now we can use the third boundary condition in the right-hand side of the equation, which gives the ratio between the tangential components of the displacement vectors d1 and d2. Then we apply the second boundary condition and obtain epsilon 1 over epsilon 2, as in the case of the electric field strength. As a result, we have established the law of refraction for the field quantities at the boundary interface between two dissimilar but homogeneous and isotropic dielectric media, stating that the tangent of the angle theta 1 between the normal to the interface and the direction of the electric field and the displacement field in the medium with the absolute permittivity epsilon 1, divided by the tangent of the angle theta 2 between the normal to the interface and the direction of the field quantities in the medium with the absolute permittivity epsilon 2, is equal to the ratio of the dielectric constant epsilon 1 to the dielectric constant epsilon 2. The law of refraction tells us when an electric field and electric displacement cross an interface from a medium with lower permittivity to a medium with higher permittivity, then the angle with the normal increases, that is, the field lines bend away from the normal to the boundary interface. Consequently, the density of the field lines is greater in the medium with higher permittivity. This situation is illustrated in the figure with a homogeneous and isotropic dielectric slab with the absolute permittivity epsilon 2 introduced into a uniform electric field E, where the media surrounding the slab has a dielectric constant epsilon 1 that is less than epsilon 2. This effect can also be studied well if a ring-shaped dielectric with a high dielectric constant is placed in an electric field. Due to the refraction of the electric field lines, most of the lines of force are concentrated in the wall of the dielectric ring, and the density of the field lines becomes less in the space enclosed by the ring. The dielectric ring thus exerts a shielding effect similar to metal cavities. The shielding effect will not be perfect, but the greater the permittivity of the dielectric, the stronger the shielding effect. Evidently, only conductors which are considered as dielectric materials with infinite permittivity can produce perfect electric shielding. We already established that the electric field at any point in insulating materials is determined by averaging the microscopic electric field E sub m over a small volume enclosing that point, which is the superposition of the electric fields E sub E and E sub B due to the extraneous or free charges and the bound charges in the dielectric medium. Since these electric fields are microscopic in nature, we use their averages over very small volumes to describe the macroscopic electric field in dielectrics. However, if we want to determine the local electric field strength acting on an arbitrary molecule inside the dielectric, it is not longer enough to calculate the effect of these macroscopic fields on that molecule. In general, the local field strength at an arbitrary point in the dielectric, for example at the location of a molecule, is determined by the field E naught due to external sources and the field strength of the molecules in the dielectric with dipole moment. In order to determine the electric field due to polarized molecules in an insulating material, Hendrik Lorentz, the famous Dutch physicist, applied a method using the so-called Lorentz cavity or Lorentz sphere to calculate the local field acting on a molecule by separating local dipoles from distant ones. In this method we consider an imaginary sphere around an arbitrary molecule in a dielectric medium under the influence of a uniform electric field E naught, whose radius r should be small enough compared with the physical dimensions L of the polarized dielectric, but large enough compared with the distances d between the molecules in the medium. Then the electric field acting on the molecule in the center of the Lorentz sphere that is due to the polarized molecules outside the cavity can be considered as the superposition of two different fields. The electric field E' due to the polarization charges over the outer boundary surface of the dielectric material, and the electric field E1 due to the polarization charges over the boundary interface between the Lorentz sphere and the dielectric medium excluding the molecules inside the cavity. The effect of the molecules inside the sphere on the molecule at the center of the sphere is described by the electric field E2 depending on the atomic structure of the dielectric inside the cavity. As a result, the electric fields E1 and E2 has local contributions to the effects of the electric field strengths E0 and E' on the molecule. Now we determine these contributions for specific type dielectric materials in the case of uniform polarization. We start with the electric field E1 due to the polarization charges over the boundary surface of the Lorentz cavity, where the polarization surface charge density sigma prime at any point of the boundary surface of the cavity can be written as the dot product of the polarization P of the dielectric surrounding the cavity and the inward pointing surface normal n at the point. In this case the normal vector points outward from the insulating material surrounding the cavity. If the dielectric medium is homogeneous and isotropic, then the polarization P produced by the uniform electric field E0 is uniform as well. Therefore, the vector field P has a fixed direction, and we can introduce the angle theta between the unit normal n at any point on the cavity surface and the direction of the polarization field P. Then the polarization surface charge density sigma prime is given by the magnitude of the polarization field P times the cosine of the angle theta. Now we calculate the electric field due to this surface charge distribution over the Lorentz sphere at the center of the sphere. The magnitude of an infinitesimal field dE at the center of the sphere produced by the infinitesimal amount of polarization charge dq' at any point on the sphere is equal to 1 over pi times the vacuum permittivity epsilon naught, times the charge dq' over the square of the radius r of sphere. The infinitesimal polarization charge can be written as the polarization charge density sigma prime, times the surface element ds at the given point on the sphere, where sigma prime is equal to the magnitude of the polarization P times cosine theta. We need to integrate this quantity over the whole surface of the cavity to determine the net electric field due to the total amount of polarization charges over the surface of the cavity. However, the component of the electric field perpendicular to the polarization field vanishes for such an integration over the sphere in a uniform polarization field. Hence, we only consider the tangential component of the field strength due to each charge element, which is given by the magnitude of the electric field dE times cosine theta. Then we can express the infinitesimal field dE1 as 1 over pi times epsilon naught, times the ratio of the magnitude of the polarization P to the square of the radius r of sphere, times the square of cosine theta, times the surface element ds. Now we integrate the infinitesimal element of the field strength over the surface of the Lorentz sphere to obtain the electric field E1 at the center of the sphere, and substitute the expression obtained for dE1 into the integral. Here the surface element ds can be written as the square of the radius r of the sphere, times the sine of the angle theta times the differential of the angle theta, times the differential of the azimuthal angle phi in the spherical coordinate system attached to the center of the sphere such that the polar axis of the coordinate system is parallel with the polarization field P. As a result, the magnitude of the electric field E1 is equal to P over 4 pi times epsilon naught, times the double integral of the square of cosine theta times sine theta with respect to the polar angle theta and the azimuthal angle phi, where the boundaries of integration cover the whole Lorentz sphere. Since the integrand does not depend on the angle phi, the integral with respect to phi from 0 to 2 pi gives 2 pi, and we can reduce the right-hand side to P over 2 times epsilon naught, times the integral of the square of cosine theta times sine theta with respect to theta from 0 to pi. By introducing the variable x for cosine theta, we can write dx as minus sine theta times d theta, and transform the integral to the negative integral of x squared with respect to x from plus 1 to minus 1. The primitive function of this integral is x cubed over 3, and its evaluation on the limits gives 2 over 3. Then the magnitude of the electric field strength E1 due to the polarization charges over the surface of the Lorentz cavity is equal to the magnitude of the polarization P over 3 times the vacuum permittivity epsilon naught. In the second step we determine the electric field E2 due to the dipole molecules within the Lorentz cavity that act on the molecule at the center of the cavity. We suppose that the dielectric material is homogeneous and isotropic, that is the molecules inside the medium has the same dipole momentum in a uniform electric field pointing in the same direction. Now we also assume that these molecules are ordered in a cubic crystal lattice since this symmetry helps us to reduce the complexity of the problem in a great extent. When we studied electric dipoles we determined the electric field due to the system of electric dipoles at a given point where the position of the ith electric dipole is described by the position vector Ri pointing from the given point to the dipole. Here all the molecules have the same dipole moment p, and we can write the electric field as the sum of the difference between 3 times the dot product of the dipole moment p and the position vector Ri of the ith molecule times the position vector Ri, and the square of the length of Ri times the dipole moment p, over the length of Ri raised to the 5th power, where the index I runs through all the molecules inside the cavity expect the one at the center. If we attach a Cartesian coordinate system to the center such that its z-axis points to the direction of the polarization field P that is of the axes of the dipoles, then the electric field E2 due to the polarized molecules is only a non-vanishing z component. Consequently, it is enough to calculate the z component of the field strength, where the dot product has only one term for the product of the dipole moment p and the coordinate zi, and the z component of the dipole moment p is simply the magnitude of the dipole moment p. Then the magnitude of the dipole moment p can be factored out from the sum, and the square of the length of the position vector Ri can be written as the sum of xi squared, yi squared, and zi squared. If we consider the symmetry of the cubic lattice structure of the dipoles and the symmetric arrangement of the Lorentz sphere, then the directions along the Cartesian axes are equivalent, and the sum of square of the x, y, and z coordinates over the length of the position vector Ri to the 5th power are equal to each other for the complete sum of the molecules within the sphere. As a result, xi squared and yi squared can be replaced by zi squared in the fraction, and the total sum gives 0, stating that the contribution of the polarized molecules within the Lorentz cavity to the local electric field at the center vanishes in a medium where the molecules are arranged in a cubic crystal lattice. It can be shown that this field also vanishes in isotropic materials and in any media with a random distribution of molecules. The resultant microscopic electric field E sub m is the local field acting on a molecule in any insulating material, usually denoted by E loc. Whereas the net external electric field E acting on a given molecule is the superposition of the external field E naught and the electric field E prime due to the polarization charges over the outer boundary surface of the dielectric medium. Then the local electric field E loc in any dielectrics can be written as the sum of the net external field E acting at a given point in a material, and the polarization vector field P over 3 times the vacuum permittivity epsilon naught. This resultant field is called the Lorentz field in homogeneous and isotropic dielectric media. We already saw that the polarization field in a dielectrics is approximated by the volume average sum of the electric dipole moments of the molecules. We also assumed that the polarization field can be expressed in terms of electric susceptibility of the dielectric and the electric field strength polarizing the dielectric in a linear form for a homogeneous and isotropic insulating material. Then we can introduce a similar expression for a single molecule in such materials, and we can define the polarizability of one atom or molecule such that the dipole moment p of the atom or the molecule is given by the molecular polarizability alpha, times the local electric field strength E loc acting on the atom or the molecule. Since the SI unit of the dipole moment is Coulomb times meter and the SI unit of the electric field strength is volt per meter, the SI unit of the molecular polarizability is Coulomb times square meter per volt. Then polarizability is the measure of how easily an electron cloud or the charge distribution in an atom or a molecule can be distorted by an external electric field, creating an induced dipole moment. It represents the ability of a material to form dipoles, which determines the total dielectric polarization of the medium. The anisotropic version of molecular polarizability is its generalized form called molecular polarizability tensor, which is a symmetric second-rank tensor mapping the vector field of the local electric field strength at any point within the dielectric to the electric dipole moment of a molecule at that point due to polarization. That is, the dipole moment p of the molecule is given by the contraction of the molecular polarizability tensor alpha of the dielectric with the local electric field E loc acting on the molecule. In a Cartesian coordinate system attached to the molecule at the given point, the I components of the dipole momentum p of the molecule is equal to the sum of the components alpha sub ij of the molecular polarizability tensor, times the j component of the local electric field E loc for the indices I and j denoting the Cartesian indices x, y, and z. This equation shows that the local electric field often causes the induced dipole to differ in direction from the field, and in many cases we can diagonalize the matrix representing the polarizability tensor in a principal axis system determined by the symmetries of the molecular structure of the dielectric. Then the molecular polarizability of the insulating material can be represented by the 3 principal values of the polarizability tensor. In fact, the total polarization of a material is usually the sum of 3 main mechanisms based on charge displacement: electronic displacement or electronic polarization, ionic displacement or ionic polarization, and orientation displacement or orientation polarization. When we classified dielectrics into the groups of nonpolar dielectrics and polar dielectrics, we explained how electric dipole moments are induced by the shift of opposite charges in an atom or a molecule in the opposite directions. Electronic polarization is the process by which an atom's electron cloud is distorted under the influence of an external electric field. When an electric field is applied, the negatively charged electron shifts slightly opposite to the field, while the positively charged nucleus shifts in the direction of the field, but this shift is very little due to its much larger mass. This separation of charge creates an induced electric dipole moment within the atom. The process of electron cloud deformation is independent of temperature and happens rapidly in the order of 10 to -14 or -15 seconds. The magnitude of this induced dipole is proportional to the applied field and is characterized by the electronic polarizability. Ionic polarization occurs in materials like ionic crystals, where positive and negative ions are arranged in a regular lattice structure. When an electric field is applied, positive ions shift slightly in the direction of the field while negative ions move in the opposite direction, creating many induced dipoles. This collective displacement produces a strong overall polarization in the crystal. Unlike electronic polarization, ionic polarization involves the movement of entire ions, making it slower due to their larger mass and the restoring forces of the lattice. This mechanism, characterized by the ionic polarizability, only exists in materials with distinct charged ions, and it is absent in covalent solids where such ion displacement cannot occur. These two types of displacement polarization occur only in materials with nonpolar molecules, where the molecules polarized in an electric field behave as elastic dipoles held together at their ends of opposite charges by elastic forces. Orientational polarization occurs in materials made of polar molecules which possess permanent electric dipole moments. When an electric field is applied on these dipoles that are randomly oriented due to thermal motion resulting in no net polarization, it exerts a torque on the dipoles attempting to align them with the field direction. Although complete alignment is not achieved, a partial average alignment produces a net polarization. This mechanism differs from electronic and ionic polarization because it does not create dipoles but reorients existing ones. The process is strongly influenced by the competition between the aligning effect of the electric field and the randomizing effect of thermal energy. As temperature increases, thermal motion dominates and reduces the degree of alignment. Consequently, orientational polarization decreases with increasing temperature, typically varying inversely with temperature. In some cases, such as in solid ice, molecular rotation is restricted, preventing dipole alignment and effectively eliminating orientational polarization. The total polarizability of a dielectric medium is the sum of these contributions determined by the molecular structure of the matter, that is the sum of the scalars or the tensors representing each type of molecular polarizability. As already mentioned, we approximated the polarization field in a dielectric material as the average sum of the electric dipole moments of the molecules over a small volume enclosing some molecules. Instead of averaging over the volume, we can also express the polarization vector in terms of the concentration of atoms or molecules, that is their number density measured in the number of atoms or molecules per unit volume. Then the polarization P in an insulating material composed of a mixture of different types of atoms or molecules, is equal to the sum of the atomic or molecular concentration Ni of the atoms or the molecules of the type I, times the electric dipole moment Pi of the atoms or molecules of the type I, where the index I runs through all the n different types of atoms or molecules in the material. If the substance contains only one type of atoms or molecules, then the polarization field P at the position of an atom or a molecule is given by the number density n of the atoms or the molecules in the medium, times the electric dipole moment P of the atoms or molecules. For the sake of simplicity, we consider atoms as monatomic molecules and we will only talk about dielectric materials composed of molecules. The polarization field can also be written as the molecular concentration N times the molecular polarizability alpha of the molecules, times the local electric field E log acting on the molecules. The equations of polarization expressed in terms of molecular concentration are very convenient in the study of the polarization of gases, since they help us to determine the relationship between the electric susceptibility or the dielectric constant and the molecular polarizability for gases. Because the average distances between the molecules are relatively large in dilute gases, the difference between the local and macroscopic field strengths given by the superposition of the internal electric fields E1 and E2 can be neglected for both polar and nonpolar gases. Hence, the macroscopic electric field E is a good approximation for the local electric field E log, and we will use this approximation for both polar and nonpolar gases at low pressure. For gases composed of nonpolar molecules, such as noble gases like helium, neon, and argon, or diatomic gases like hydrogen, oxygen, and nitrogen, the polarization P of the gaseous substance can be written as the atomic or molecular concentration N, times the molecular polarizability alpha of the molecules, times the electric field strength E. Now we compare this equation with the one stating that the polarization vector P is equal to the electric susceptibility chi-E of the gaseous substance, times the vacuum permittivity epsilon naught, times the electric field strength E. Then we conclude that the electric susceptibility chi-E given by the relative dielectric constant epsilon R of the gas minus 1, is equal to the product of the number density N of the molecules and the molecular susceptibility alpha of the gas, over the vacuum permittivity epsilon naught. In the case of gases composed of polar molecules like carbon monoxide, ammonia or hydrogen chloride, we must take the effect into account that attempts to change the orientation of the molecules with a permanent dipole moment in an external electric field align them with the field. As already mentioned, the dipoles in any substance composed of polar molecules are randomly oriented due to thermal motion. The torque produced by the electric field aligns the dipoles in the direction of the field, minimizing their potential energy. However, the thermal excitation of the polar molecules tends to disrupt this alignment, acting against the torque produced by the electric field. Due to the net effect of the competition between the thermal motion and the torque, the randomness of the orientation of the dipoles can only be reduced but cannot be eliminated completely. This fact must be taken into account when the polarization of the gas is determined by averaging the electric dipole moments of the polar molecules under the influence of an external electric field. When we studied electric dipoles, we found that the potential energy U of a dipole in a uniform electric field E is given by the negative projection of the dipole moment P of the dipole onto the electric field strength E. Then U can be written as the negative product of the magnitudes of the dipole moment P and the field strength E, times the cosine of the angle phi between the direction of the axis of the dipole and the electric field. For the polarized molecules of a polar gas, the magnitude of the permanent dipole moment P is constant, whereas the orientation angle phi of the dipole is a random variable that have a value between 0 and 360 degrees. However, only the component of the dipole moment along the field contributes to the polarization, which is given by the constant magnitude of the dipole moment P times cosine phi. Then it is enough to compute the average of cosine phi in this product, and we consider cosine phi as a random variable x covering the range between -1 and 1. If we want to calculate the average value of a discrete random variable x, we need to calculate the sum of the products of each possible outcome and its corresponding probability. Here the statistical weight Wi describes the probability of the outcome xi for the variable x, and the average of x can be written as the sum of the weight Wi times the value xi of the variable x for the index I running through all the possible n outcomes. This sum is divided by the sum of the weight Wi from I equals 1 to n to provide a normalization for the statistical weights. For example, in the case of a standard 6-side dice, the random variable is the different outcomes of its rolling described by the integers from 1 to 6, and its statistical weight must be the same for each outcome. With the normalization, their values are given by 1 over 6, and the average of the random variable x is equal to 3.5 for the outcome of rolling the dice. Because the random variable x given by the cosine of the orientation angle phi of a dipole is a continuous one, the statistical average written in terms of sums must be generalized to an expression written in terms of integrals. Then the average of x is given by as the integral of the statistical weight w as a function of x times the random variable x with respect to x, divided by the integral of the statistical weight w with respect to x. The upper and lower limits of the integrals must cover all the possible values of the random variable x, which is the interval between -1 and 1 in this case. In statistical mechanics, it can be shown that the statistical weight W for gas molecules in thermal equilibrium is described by the Boltzmann distribution function. That is, the weight W is proportional to the exponential function of minus the potential energy U of the gas divided by the product of the Boltzmann constant K and the absolute temperature T of the gas. For one dipole in a given statistical state defined by its orientation, we can substitute the explicit form of the potential energy U of the dipole into this expression, and write the right-hand side as the exponential of a ratio of P times E times cosine phi to K times T. Here cosine phi can be written as the random variable x, and by introducing the parameter a for the ratio of P times E to K times T, we can state that the statistical weight W is proportional to the exponential of ax. Then the integral of the statistical weight W with respect to the random variable x is proportional to the integral of the exponential of ax with respect to x from -1 to 1. The primitive function of the integrand is equal to e to ax over a, which can be evaluated at the lower and upper limits. As a result, we obtain the exponential of -a over a, minus exponential a over a, that is -2 times sin a over a. The integral of w times x with respect to x is proportional to the integral of the exponential of ax times x with respect to x from -1 to 1. When integrating this expression by parts, we evaluate the exponential of ax times x over a at the limits -1 and 1, and subtract 1 over a times the integral of exponential of ax with respect to x from -1 to 1. This gives the negative exponential of minus a over a, plus exponential a over a, plus 2 times sin a over a squared. Then the result can be written as -2 times cos a over a, plus 2 times sin a over a squared. If we substitute the expressions derived for the two integrals into the formula for the averaging of the continuous random variable x given by cosine phi, the proportionality factor of the statistical weight emitted here cancels out in the numerator and the denominator of the fraction. After simplifying the fraction with -2 times sin a over a, we obtain coth a minus 1 over a. The left-hand side of this equation is called the Langevin function L with the argument a, which is used to describe the alignment of both electric and magnetic dipoles in a polar dielectric or a paramagnetic material under an applied electric or magnetic field. This result can be substituted into the averaged permanent electric dipole moment of polar molecules of a gas under the influence of an external electric field, which provides a contribution to the polarization field in the gas given by the magnitude of the permanent dipole moment p of the gas molecules, times the Langevin function L evaluated at the product of the magnitudes of the dipole moment p and the external electric field E over the product of the Boltzmann constant K and the gas temperature T. In the relevant cases the electric field E applied to the gas is weak and the temperature T of the gas is high. Then the ratio of P times E to K times T is much smaller than 1, and the Langevin function of the variable x can be approximated by x over 3. Consequently, the average permanent dipole moment P of the gas molecules in the external electric field E can be written as the square of the magnitude P of the dipole moment over the product of 3 times the Boltzmann constant K and the gas temperature T, times the field strength E. Although the dipoles are not perfectly aligned with the field, their average can be approximated in this way for weak fields and high temperatures. Since the polarization in a polar gas is due to both the electron polarization of the gas molecules and the orientation polarization of their dipole moments, we can write the polarization P as the number density n of the molecules, times the sum of the induced polarization and the averaged permanent dipole moments in the gas. Here the sum can be written as the sum of the molecular polarization alpha of the gas times the electric field strength E, and the ratio of P squared over 3 times K times T, times the vector E. Then the polarization is given by n times the sum of alpha and the ratio of P squared to 3 times K times T, times the field strength E. As already seen, the polarization vector P is also equal to the vacuum permittivity epsilon naught, times the electric susceptibility chi-e of the gaseous substance, times the field strength E, where chi-e is given by the relative permittivity epsilon r of the gas minus 1. If we compare these two expressions describing the polarization, then we conclude that the electric susceptibility chi-e of the gas or its relative permittivity epsilon r minus 1, can be written as the concentration n of the gas molecules over the vacuum permittivity epsilon naught, times the sum of the molecular polarizability alpha of the gas and the square of the magnitude of the electric dipole moment P of the molecules over 3 times the Boltzmann constant K, times the temperature T of the gas. By comparing this result with the corresponding formula obtained for nonpolar gases, we can recognize the first term in the parentheses describing the electron polarization of the gas, which is present in the case of both nonpolar and polar gases. Here the second term in the parentheses is the contribution from the orientation polarization of the molecules with permanent electric dipole moments in polar gases. We can provide a more accurate description of the polarization of nonpolar gases if we do not neglect the Lorentz field induced in the gas when an electric field E is applied on its molecules. Then the polarization field P given by the number density n of the gas times the induced dipole moments of the molecules is equal to the concentration n times the molecular polarizability alpha of the gas, times the sum of the electric field strength E and the polarization vector P over 3 times the vacuum permittivity epsilon naught. If we solve this equation for the vector P, we can write the polarization as n times alpha, times the reciprocal of 1 minus n times alpha over 3 times epsilon naught, times the vector E. Now we compare this equation with the one seen above where P is expressed by epsilon naught, times epsilon r minus 1, times E, and we state that n times alpha times the reciprocal of 1 minus n times alpha over 3 times epsilon naught, is equal to epsilon naught, times epsilon r minus 1. By introducing the shorthand notation b for n times alpha over 3 times epsilon naught, we can write this equation in a simple form, stating that 3 times b over 1 minus b is equal to epsilon r minus 1. If we multiply this equation by 1 minus b, then its right-hand side becomes epsilon r minus 1, minus epsilon r times b plus b. After simplifying this equation, we can write that the product of epsilon r plus 2 and b is equal to epsilon r minus 1. Finally, we divide this equation by epsilon r plus 2 and substitute the original expression into b. As a result, we obtain the Clausius-Masati equation stating that the relative permittivity epsilon r of a nonpolar gas minus 1 over epsilon r plus 2 is given by the number density n of the gas molecules times the molecular polarizability alpha of the gas over 3 times the vacuum permittivity epsilon naught. The equation was named after two scientists. The first one is Rudolf Clausius, one of the founders of thermodynamics, who in his study on the interaction of electric fields with matter introduced ideas about how individual molecules contribute to polarization, and recognized that the field acting on a molecule differs from the externally applied field. The second one is Ottaviano Fabrizio Masodi, who determined a relation between the dielectric constant of a material and the properties of its constituent particles while he worked on dielectric materials and drew analogies between electrostatics and elasticity. Their contributions are manifested in the Clausius-Masati equation, providing the first important connection between microscopic properties of matter like molecular polarizability, and its macroscopic properties like dielectric constant. We have the following remarks on the Clausius-Masati equation. For dielectrics belonging to the group of nonpolar and weakly polar fluids such as vegetable and mineral oils, benzene, and toluene, which have small relative dielectric constants between 2 and 2.5, electronic polarization is the dominant effect. In this case, the Clausius-Masati equation adequately describes the relationship between the polarizability and the dielectric constant of such fluids. In polar liquids there are usually very strong electric fields due to the interaction of polar molecules located close to each other. The Clausius-Masati equation is no longer applicable here, and other theoretical models serve to describe the relationship between the microscopic and macroscopic properties of the fluids that is in a good agreement with the experimental data. If the only dominant mechanism in the polarization of a solid dielectric is electronic polarization and its relative permittivity is small, then the Clausius-Masati formula is valid for the given insulating material. Since the internal electric field in ionic crystals with a cubic structure is described by the Lorentz field, the Clausius-Masati equation can be applied in this case as well. In general, determining the relationship between polarizability and dielectric constant is not an easy task. If we consider gases composed of polar molecules where the Lorentz field is taken into account, then the polarization field P given by the number density n of the gas molecules times the sum of their induced dipole moment and the average of their permanent dipole moment, is equal to the concentration n times the sum of the molecular polarizability alpha of the gas molecules and the square of the magnitude of the permanent dipole moment P over 3 times the Boltzmann constant K times the temperature T of the gas, times the vector sum of the external electric field strength E and the polarization vector P over 3 times the vacuum permittivity epsilon naught. In this case, we need to modify the Clausius-Masati equation by replacing the molecular polarizability alpha with the sum of alpha and the ratio of P squared to 3 times K times T. This formula is called Clausius-Masoti-Debye equation, since the physicist and chemist Peter Debye introduced the concept of orientation polarization and determined its explicit form based on the statistical mechanical calculations presented here before. Hence, this equation describes not only electronic polarization due to the electron shell deformation in molecules but also orientation polarization due to the alignment of their permanent dipole moment. It is useful to define the molar polarization Pm of any substance by the ratio of its relative dielectric constant epsilon r minus 1 to epsilon r plus 2, times the molar mass m of the substance over its density ρ. As its SI unit given by cubic meter per mole shows, this quantity measures the total electric polarization produced in 1 mole of a substance when placed in an external electric field. In the case of gases, the number density n of the gas molecules is equal to the Avogadro's number Na times the density ρ over the molar mass m. If we substitute this expression into the Clausius-Masoti-Debye equation, we can see that the ratio of epsilon r minus 1 to epsilon r plus 2, times m over ρ, is given by Na over 3 times epsilon naught, times the sum of alpha and P squared over 3 times K times T. Because we have the molar polarization Pm in the left-hand side of the equation, we can express Pm as a constant A, plus the ratio of another constant B to the temperature T of the gas. Here the constant A contains only the molecular polarizability alpha characterizing the physical properties of the gas molecules, whereas the constant B contains only the permanent dipole moment P of the molecules. Then, The molar polarization PM written in this form reinstates the fact that polarizability is due to two mechanisms: electronic polarizability, which is independent of the temperature of the medium, and orientation polarizability, which depends on the temperature. One of the experimental methods for determining the permanent dipole momentum and molar polarizability is based on the Clausius-Massoudi-Debye equation expressed in terms of molar polarization. For example, if we measure the relative dielectric constant epsilon r and the density ρ of a gas at different temperatures T, then we can compute the molar polarization PM and plot it as a function of 1 over the temperature T. As a result, we obtain a line whose directional tangent B gives the permanent dipole moment P, and we can calculate the molecular polarization alpha from the intersection A of this line with the ordinate axis. Here such measurements is shown for water vapor, ammonia and hydrogen chloride. If the values of the intercept A and the slope B are determined from the experimental data, then the values of the molecular polarizability alpha and the permanent dipole moment P of the gas molecules can be computed from these formulae. The knowledge of these quantities is crucial for our understanding of the structure of molecules. Besides the molecular polarizability alpha, we also use the polarizability volume alpha prime defined by alpha over 4 pi times the vacuum permittivity epsilon naught, which is interpreted as the volume of a conducting sphere that has the same polarizability as the atom or molecule in question. For example, from the measurements performed for hydrogen chloride, the intercept A in its plot is equal to about 2.6 cubic centimeter per mole, which gives a polarizability volume of 2.6 angstrom cubed for a hydrogen chloride molecule. Similarly, the slope B of the line fitted over the data points of hydrogen chloride is equal to about 650 cubic centimeter Kelvin per mole, which gives a permanent dipole moment of 3.44 times 10 to minus 28 coulomb centimeter. The values of both quantities determined experimentally by applying this method show excellent agreement with the values derived from quantum mechanical computations. Finally, we note that if we take both types of displacement polarizability into account, that is, we also consider ionic polarizability, then we need to write the molecular polarizability alpha in the Clausius-Massoudi-Debye equation as the sum of the molecular polarizability alpha E due to electronic polarizability, and the molecular polarizability alpha I due to ionic polarizability. Then we obtain the most general form of this equation. In order to determine the energy density of an electrostatic field in a dielectric material, we start with the simple example of a charged parallel plate capacitor with dielectric. Let us consider a parallel plate capacitor with a homogeneous and isotropic insulating material of relative permittivity epsilon r that completely fills the space between its plates. Here A denotes the area of each plate and D is the distance between the two plates. Then the volume V of the dielectric medium between the plates is given by the product of the area A and the distance D. If the plates have the opposite charges plus and minus Q, then the electric field E is uniform between the plates. When we derive the capacitance C of a parallel plate capacitor, we found that it is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon r of the dielectric between the plates, times the area A of each plate over the distance D between the plates. By definition, the proportionality constant C describes the relationship between the charge Q on the plates of the capacitor and the voltage Vc through the capacitor, that is the potential difference between the plates. We already saw that the energy U of a charged parallel plate capacitor is given by 1 over 2 times the capacitance C of the capacitor times the square of the potential difference Vc between its plates. For the uniform electric field E between the plates of the capacitor, the voltage Vc can be written as the magnitude of the electric field strength E times the distance D between the plates. If we substitute this relation together with the expression for the capacitance C into the right-hand side of the equation, then we obtain 1 over 2 times epsilon naught times epsilon r, times the volume V of the space between the plates, times the square of the magnitude of the electric field strength E. Since the energy density U of the uniform electric field within the volume V is simply the energy U divided by the volume, we obtain 1 over 2 times epsilon naught times epsilon r, times E squared. In the right-hand side of this equation we can recognize the magnitude of the electric displacement D in the dielectric given by epsilon naught times epsilon r times the magnitude of the electric field strength E. Then the energy density U is simply equal to 1 over 2 times the product of the magnitudes of the electric field strength E and the displacement D in the insulating material between the plates of the capacitor. We can also express U in terms of the magnitude of the displacement D, stating that it is equal to 1 over 2 times D squared over the product of epsilon naught and epsilon r. Because the electric field strength E and the displacement field D have the same direction in an isotropic medium, the dot product of these vectors is given by the product of their magnitudes. Then the energy density U in an isotropic dielectric can be written as 1 over 2 times the dot product of the electric field strength E and the displacement vector d at any point in the medium. In fact, the displacement field d is defined by the sum of the vacuum permittivity epsilon naught times the electric field strength E and the polarization field P in the dielectric. If we insert this definition into the dot product in the energy density U, then we can express the later as 1 over 2 times the vacuum permittivity epsilon naught times the square of the magnitude of the electric field strength E, plus 1 over 2 times the dot product of the electric field strength E and the polarization P. Here we see that the energy density of a charged capacitor has contribution from two terms which we interpret as follows. In the term 1 over 2 times epsilon naught times E squared we recognize the energy density U naught of the electric field E in a vacuum. Then the energy density U of the capacitor can be written as the sum of the energy density U naught and another term UP related to the polarization of the medium between the charged plates of the capacitor. Indeed, the energy density UP, that is the difference between the energy density U of the capacitor and the energy density U naught, is given by 1 over 2 times the dot product of the electric field strength E and the polarization P. For a linear and isotropic medium the polarization vector P is equal to epsilon naught times epsilon or minus 1 times the electric field strength E. Then the energy density UP is equal to 1 over epsilon naught times epsilon or minus 1 times E squared, depending on both the magnitude of the electric field between the plates and the relative dielectric constant epsilon r of the medium between the plates. We will show that the energy density UP defined here is simply the energy required to polarize a dielectric material per unit volume. Firstly, we recall that the polarization of a dielectric occurs when the electric field causes the charges within its molecules to become displaced. Then we assume that the charge distribution in the molecules enclosed by a volume V of the insulating material can be described by the position vectors Ri of a system of n-point charges Qi within the molecules with respect to an arbitrary point O. When an external electric field E acts on the molecules within the volume V, the electric charges in the molecules change their positions due to either induced polarization where opposite charges are displaced in or opposite to the direction of the field, or orientation polarization where the charges change their positions as the polar molecules change their orientations in the field. In both cases the infinitesimal displacement of these charges can be described by the differential of the position vector Ri of each point charge Qi. The infinitesimal work dWi required to move the point charge Qi through the infinitesimal distance described by the vector dRi, is given by the dot product of the force Fi of the external electric field E acting on the point charge and the displacement vector dRi. By definition, the electrostatic force Fi acting on the point charge Qi is equal to the charge Qi times the electric field strength E, and the infinitesimal work done on the point charge can be written as Qi times the dot product of the field strength and the vector of the infinitesimal displacement of the point charge. Then dW denoting the infinitesimal work per unit volume done by the external electric field E to produce the infinitesimal displacements dRi for all the point charges Qi, is equal to 1 over the volume V enclosing the molecules, times the sum of the infinitesimal work dWi from I equals 1 to n for each point charge within the volume V. Hence, the infinitesimal work per unit volume is given by 1 over V, times the sum of Qi times the dot product of the vectors E and dRi from I equals 1 to n. Because the external field E is uniform in space, we can write the right-hand side as the dot product of the field strength E and the differential of a quantity given by 1 over the volume V, times the sum of the charge Qi times the position vector Ri of the point charge Qi from I equals 1 to n. Here the product of the charge Qi times the position vector Ri of the point charge Qi gives the electric dipole moment Pi of the point charge, and its sum averaged over the volume V gives the approximation of the polarization field P in that volume. As a result, the infinitesimal work per unit volume denoted by dW is equal to the dot product of the electric field strength E and the differential of the polarization vector P. If we apply the formula stating that the polarization P is given by the vacuum permittivity epsilon naught times the electric susceptibility chi-e of the linear dielectric slab between the plates of the capacitor, then the right-hand side of the equation can be written as epsilon naught times chi-e times the dot product of the vector E and the differential of the vector E. This expression is also equal to the differential of 1 over 2 times epsilon naught times chi-e times the square of the magnitude of the vector E, where E squared is simply equal to the dot product of the vector E with itself. By substituting the polarization P back into this equation, we can write the infinitesimal work per unit volume as the differential of 1 over 2 times the dot product of the vectors E and P. If we compare this result with the definition of the energy density UP, we can see that the later is equal to dW, that is the infinitesimal work per unit volume. If we integrate this expression, then we obtain the work W required to polarize the dielectric per unit volume, which is equal to 1/2 times the dot product of the field strength E and the polarization P. Then we prove that this work per unit volume is equal to the energy density UP defined by the difference between the total energy density of the charged capacitor and the energy density of the electric field produced by the free charges on its plates. We note that the differential of the work per unit volume presented here is frequently written in an integral form, where one determines the work W per unit volume done to change the polarization of a dielectric from 0 to a value P in an external electric field E. Then W is equal to the integral of the field strength E with respect to the polarization P' from 0 to the vector P. In order to calculate the integral, we need to express the electric field E in terms of the polarization P, like the linear relation between the vectors P and E with the coefficients epsilon naught times chi E used here to manipulate the differential form of W. If we expand these vectors in a Cartesian coordinate system attached to the insulating medium, then the integral of the vector E with respect to the vector P' is equal to the sum of the integrals of the component I of the vector E with respect to the component I of the vector P' from 0 to the component I of the vector P, where the index I runs through the Cartesian coordinates x, y, and z. We have shown here that the integration for a linear dielectric in a uniform electric field gives 1/2 times the dot product of the vectors E and P, but the question arises whether the energy density or the work per unit volume can still be written in a simple form in a more general case. Now we generalize this case and consider a problem, where we determine the energy density in a polarized and homogeneous dielectric under the influence of a non-uniform external electric field. This means that the electric field strength E and the displacement field D describing the net electric field in the insulating material depend on the position in the medium. So is the relative permittivity of the linear but inhomogeneous dielectric material in the equation stating that the displacement D is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon r times the field strength E. In order to determine the potential energy in such a case, we start with the first Maxwell equation in electrostatics telling us that the divergence of the displacement field D is equal to the free electric charge density ρ. We also recall that the total potential energy U of the charge distribution ρ is given by 1/2 times the volume integral of the product of the charge density ρ and the electrostatic potential phi over the whole space where the scalar fields ρ and phi do not vanish. Now we apply the variation of the Maxwell equation, which states that the divergence of the variation delta D of the displacement is equal to the variation delta ρ of the density of the free charges. Similarly, we can write the variation delta U of the potential energy as 1/2 times the volume integral of the variation of the product of ρ and phi. Here we use the fact that the variation operator delta acting on a vector field and the nabla operator acting on that field commute, which also true for the operator delta and the volume integration applied on scalar fields. For the variation of the product of ρ and phi in the volume integral describing the variation of the potential energy, we can apply the product rule for variation and we obtain phi times delta ρ, plus ρ times delta phi in the integrand. We already saw that the electrostatic potential phi at the position r produced by an electric charge distribution ρ can be written as 1/4 pi times epsilon naught, times the volume integral of the charge density ρ at the position r' over the magnitude of the difference between the position vectors r and r', where the prime applied on the volume element of the integration indicates that the position vector r' points to the position of the volume element. The variation of the potential phi gives a formula where the variation of the electric charge density ρ will appear in the integrand of the volume integral. We can substitute this expression into the volume integral of ρ times delta phi and exchange the order of integrations. Then we can exchange ρ evaluated at the position r with delta ρ evaluated at the position r' as well. As a result, the inner integral gives the potential phi evaluated the position r', and we obtain the product of delta phi and ρ in the integrand. Since all the quantities are primed in the integral, we can drop the prime and substitute this result into the variation of the potential energy U, and the later can be written as the volume integral of the product of the potential phi and the variation of the charge density ρ. Now we apply the variation of the Maxwell equation in the volume integral describing the variation of the potential energy U, and replace the variation of the charge density ρ by the divergence of the variation of the displacement field D. By using the product rule for the nabla operator, the product in the integrand can be written as the divergence of the product of phi and delta D, minus the dot product of the gradient of phi and the vector delta D. Here we split the integral of the difference into two integrals and apply the divergence theorem for the first term, converting it into a surface integral of phi times d over an arbitrary boundary surface enclosing the domain where the potential and the displacement field do not vanish. If the boundary is at infinity, then the boundary integral vanishes as the integrand falls off faster than 1 over the square of the distance measured from the localized charge distribution in the dielectric medium. Hence, the variation of the potential energy U is equal to the volume integral of the dot product of the negative gradient of the potential phi, and the variation of the displacement field d. By definition, the negative gradient of the electrostatic potential phi is equal to the electric field strength E, which can be substituted into the volume integral, and the integrand becomes the dot product of the vectors E and delta d. At the same time, the variation of the potential energy U can also be expressed as the volume integral of the variation of the energy density U of the electrostatic field. By comparing the two forms of the variation of the potential energy U, we can state that the variation of the energy density U is equal to the dot product of the electric field strength E and the variation of the displacement vector d. Because the variation operator involves only an infinitesimal change in the physical fields, this equation can be reformulated in the form where the differential of the energy density U is given by the dot product of the electric field strength E and the differential of the displacement vector d. In order to obtain the energy density U itself, we need to integrate this equation as we did in the case of the work per unit volume done to polarize a dielectric. Then the energy density required to change the electric displacement in the dielectric from 0 to the value d is equal to the integral of the electric field strength E with respect to the displacement vector d prime from 0 to the vector d. We already saw that such a type of integral can be calculated in a Cartesian coordinate system attached to the insulating medium. Then the energy density U can be written as the sum of the integral of the component I of the field strength E with respect to the component I of the displacement d prime from 0 to the component I of the displacement d, where the index I denotes the Cartesian coordinates x, y, and z. Here the component I of the displacement d is equal to the absolute permittivity epsilon of the dielectric times the component I of the field strength E, where epsilon is equal to epsilon naught times epsilon r. If we substitute this expression into the integrand, then we need to integrate 1 over epsilon times the component I of the vector d prime with respect to d prime. Here we could factor 1 over epsilon out from the integral even if epsilon depends on the position in the insulating material. That can be done since permittivity is a property of the material, whereas d prime is an independent quantity describing the electric field in the material. The primitive function of the integral is simply equal to the square of d prime I over 2, which is evaluated at 0 and di. As a result, the energy density U is given by 1 over epsilon, times the sum of the square of the component I of the displacement d over 2 for the index I equals x, y, and z. Now we can apply the formula expressing the components of the vector d in terms of the components of the vector E, and write the right-hand side of the equation as 1 over 2, times the sum of the component I of the vector E times the component I of the vector d for the index I running through x, y, and z. Now we conclude that under the influence of a non-uniform external electric field the energy density U of a polarized and homogeneous material is equal to 1 over 2, times the dot product of the electric field strength E and the displacement vector d, where both the energy density U and the vectors E and d depend on the position. This formula shows that we can generalize the expression derived for uniform external electric field and homogeneous dielectric to the cases involving non-uniform electric fields and inhomogeneous insulating materials. By inserting the definition of the electric displacement vector into the formula obtained here, we can see that the expression 1 over 2 times the dot product of the field strength and the polarization vector derived for the work done to polarize a dielectric in a unit volume also holds in more general cases. Now we determine the change in the energy of a charged parallel plate capacitor with a vacuum or air between its plates when a dielectric slab is inserted between its plates that fills the whole space there. As we did in the analysis on the change in the capacitance of the capacitor in such an experiment, we consider two cases here. When the electric charge stored on the plates of the capacitor is constant, and when the voltage or the potential difference between its plates is constant. Let us start with the setup where the amount of charge is stored on the plates of the capacitor does not change during the experiment. We already saw that the potential energy U0 of the capacitor with a vacuum or air between its plates is equal to 1 over 2, times the capacitance C0 of the capacitor times the square of the voltage V0 between its plates. Here the capacitance C0 depends only on the geometry and the size of the capacitor. We also saw that if we insert a slab made of a dielectric material between the plates of the charged capacitor, then both the capacitance of the capacitor and the voltage through the capacitor will change. It was shown that for a slab filling the whole space between the plates the capacitance C of the capacitor is given by the relative permittivity epsilon naught of the dielectric times the capacitance C0. Similarly, the voltage V through the capacitor is equal to the voltage V0 over the relative permittivity epsilon naught. In this case, the potential energy U of the capacitor can be written as 1 over 2 times the capacitance C of the capacitor times the square of the voltage V between its plates. If we substitute the expressions for the capacitance C and the voltage V into the right-hand side of this equation, then we obtain 1 over 2 times C0 times V0 squared over epsilon R. By comparing this result with the expression for the energy U0, we can write the energy U of the capacitor with the dielectric between its plates as the energy U0 of the same capacitor with a vacuum or air between its plates, over the relative permittivity epsilon naught of the dielectric. Now we determine the difference between the potential energies U0 and U, which is equal to U0 minus U0 over epsilon R. Then the change in the energy of the capacitor can be written as the potential energy U0 of the capacitor with a vacuum or air between its plates, times 1 minus 1 over the relative permittivity epsilon R of the dielectric material. Here the multiplication factor of U0 is always positive since the relative permittivity is greater than 1 for any material, that is, the energy of the capacitor is reduced by the dielectric slab inserted into the space between its plates. Hence, the difference in the potential energy represents the energy loss of the capacitor, which is interpreted as follows. As the dielectric slab is introduced between the plates of the capacitor, the electric field inside the capacitor exerts an attractive force on the dielectric because the polarized material lowers the electrostatic energy of the system. If the slab moves inward without acceleration, this force performs mechanical work on the slab, pulling the material inward. The decrease in the electrostatic energy stored in the capacitor is therefore converted into mechanical energy transferred to the dielectric. As the result shows, the greater the relative permittivity epsilon R of the dielectric, that is, the greater the multiplication factor of U0 on the right-hand side of the equation, the greater the energy lost by the capacitor. Now we consider the second case where the voltage through the capacitor is kept constant while the dielectric material is inserted between the plates of the capacitor. Then the voltage V0 is constant, that is, V0 of the capacitor without dielectric is equal to the voltage V of the capacitor with dielectric. The relationship between the capacitance still holds, that is, the capacitance C is given by the relative permittivity epsilon naught of the dielectric, times the capacitance C0 of the capacitor without dielectric. In this case, the potential energy U of the capacitor is still given by 1 over 2 times the capacitance C times the square of the voltage V. The substitution of the expression for the capacitance and the voltage into this equation gives 1 over 2 times epsilon R times C times the square of V0, or the relative permittivity epsilon R times the potential energy U0. If we calculate the difference between the potential energy U and U0, that is the difference between epsilon R times U0 and U0, then we find that the change in the energy stored in the capacitor is equal to the potential energy U0 of the capacitor with a vacuum or air between its plates, times the relative permittivity epsilon R of the dielectric inserted between the plates minus 1. Here the multiplication factor of U0 is positive, showing that there is an increase in the energy stored by the capacitor. The energy gain produced in this way is supplied by a power source, for example a battery, that maintains a constant potential difference between the plates of the capacitor. Some amount of this supplied energy becomes additional electrostatic energy while the rest is converted into mechanical work, pulling the dielectric inward. As the result shows, the greater the relative permittivity epsilon R of the dielectric, that is, the greater the multiplication factor of U0 on the right-hand side of the equation, the greater the energy gained by the capacitor. This effect indicates that a dielectric always tends to move into the region of stronger electric field because polarization lowers the energy of the system. Whether the energy stored by the capacitor decreases or increases depends on whether charge or voltage is constrained externally. The conversion of electrostatic energy into mechanical work in this way have many important practical implications in electronics and electrical engineering. Examples of the application of this effect include micro-electromechanical systems, electrostatic motors, precision pointing devices, and micro-switches. We start the discussion on electrostatic forces acting on electric charge in dielectrics with the simplest case. When we studied electric fields in insulating materials, we considered the problem of a charged conducting sphere of radius R surrounded by a homogeneous dielectric medium of relative permittivity epsilon R. We saw that the electric field E due to the electric charge Q distributed over the conducting sphere is spherically symmetric outside its surface, and its magnitude is epsilon R times less than the magnitude of the electric field produced by the same charge distribution in a vacuum. The symmetry of the problem does not change if the radius R of the charged sphere tends to 0, and we obtain a point charge Q1 surrounded by the same medium. Hence, in an infinitely extended homogeneous dielectric medium of relative permittivity epsilon R, the electromagnetic field E of the point charge Q1 has a radial symmetry about the point charge, and its magnitude at any point P is given by 1 over 4 pi times the vacuum permittivity epsilon naught times the relative permittivity epsilon R, times the charge q1 over the square of the distance r of the point P from the point charge q1. As the form of the equation shows, it still holds that the magnitude of the electric field E in the dielectric is epsilon r times less than the magnitude of the spherically symmetric electric field E naught produced by the same point charge q1 in a vacuum. Now we can state that the magnitude of the force F acting between the point charges q1 and q2 surrounded by an infinitely extended homogeneous dielectric medium, is equal to the product of the charge q2 and the magnitude of the field strength E due to the point charge q1 that is evaluated at the position of the point charge q2. Then we have 1 over 4 pi times the vacuum permittivity epsilon naught times the relative permittivity epsilon r, times the product of the charge q1 and the charge q2 over the square of the distance r between the 2 point charges. This formula expressing Coulomb's law for dielectrics is only valid for liquid dielectrics. If the point charges are surrounded by a solid dielectric medium, then the problem of calculating the interaction forces is usually an extremely complicated task due to the various pressures and voltages that occur in such a situation. In the next example, let us consider an experiment where a metal sphere and a pith ball are suspended close to each other. The metal sphere is suspended through a metal wire which allows us to bring electric charge to the sphere, whereas the pith ball is hung by an insulating string such as silk or nylon. If we bring some electric charge Q to the metal sphere, then the lighter pith ball will move towards the metal sphere, which indicates that the two suspended bodies attract each other. However, if we repeat the experiment with the metal sphere and the pith ball immersed in turpentine, then we will find that the pith ball moves away from the charged metal sphere, indicating that there is a repulsive electrostatic force between the two bodies. This phenomenon can be interpreted by a greater degree of polarization in a substance with a greater dielectric constant. In the figure epsilon1 denotes the absolute dielectric constant of the medium surrounding the bodies, and the absolute dielectric constant of the pith ball is denoted by epsilon2. If epsilon1 is less than epsilon2, the excess charge built up on the boundary surface of the pith ball closer to the charged metal sphere is negative. If epsilon1 is greater than epsilon2, this excess charge is positive. In the first case, the positively charged metal sphere attract the pith ball, whereas the charged body will repel the pith ball in the second case. By comparing the electrostatic forces at the boundary surface of the pith ball closer and farther from the charged metal sphere, we can see that they act in opposite directions, but the forces at the side closer to the sphere have greater magnitudes. As a result, the net force acting between the two bodies is attractive in the first case, that is when the absolute dielectric constant of the medium is smaller than the one of the pith ball, and repulsive in the second case where the pith ball has a greater permittivity. The electrically insulating pith ball behaves like a dipole in the electric field produced by the charged metal sphere. Now we will give a quantitative description of the result of this experiment in several consecutive steps. First, we note that if a homogeneous charged body is placed into the non-uniform electric field E in a vacuum and the body is assumed to be small enough that the electric field is uniform inside the body, then the force F acting on the charged body is given by the charge Q of the body times the electric field strength E at the position of the body. In order to introduce a body with the charge Q into an electric field E in a dielectric medium, we need to make a cavity in the material. In a liquid dielectric, the body forms a cavity around itself in such a way that it displaces the liquid from the volume it is to occupy. The field strength EC inside the cavity will be different from the field strength in the dielectric medium. Hence, the force acting on the charged body in the cavity cannot be equal to the product of the charge Q and the field strength E in the dielectric. If we want to calculate the force acting on a charged body in a liquid dielectric, we must also take into account the fact that a mechanical pressure acts on the dielectric at the boundary of the body, which corresponds to a mechanical force Fm exerted on the body. As a result, the force acting on the charged body in the dielectric cannot be determined by the equation seen above, and its calculation is usually very complicated. In the case of liquid dielectrics, however, these calculations provided a very interesting result, according to which the resultant force F of electrostatic and mechanical forces is equal to the product of the charge Q and the electric field strength E. In the next step, we introduce electrostatic force density representing the electrostatic force exerted per unit volume on a medium by an electric field, which is measured in Newton per cubic meter. This figure showing the force vectors over the boundary surface of a dielectric in an electrostatic field E illustrates how the electrostatic force density F describes the spatial distribution of electrostatic forces across a continuous volume. We can express the electrostatic force per unit volume from the equation stating that the force acting on a small charged body is equal to the charge Q of the body times the electric field strength E at the position of the body. As a result, the electrostatic force density F at a given point is equal to the free charge density ρ times the external electric field strength E acting on the charges, where both quantities are evaluated at that point. The total electrostatic force F acting on a charged body is given by the volume integral of the electrostatic force density F over the volume V of the body. By substituting the expression obtained for the force density into this integral, the force F can be written as the volume integral of the volume density ρ of the free charges times the external electric field strength E. As already stated, the total force given by the volume integral of the force density has a more complicated form in the general case due to mechanical forces such as structural stresses and pressure gradients. Now we will study the electrostatic forces present in a charged parallel plate capacitor with a dielectric medium between its plates in two different experiments. In the first one we consider two charged parallel plates immersed in a homogeneous liquid dielectric. We assume that the distance between the plates is very small compared with the dimensions of the plates, that is the electric field due to the charges on the plate is uniform between the plates and effectively zero outside the plates. Hence, the dielectric fluid will be polarized only within the spatial volume between the plates. Due to the polarization, opposite bound charges with the uniform surface charge density sigma prime appear on the boundary of the liquid adjacent to the internal surface of the plates. As a result, the electric field change within the dielectric medium and the net electric field has no effect on the charged plates. In other words, the polarization of the dielectric does not modify the force exerted by the plates on each other, that is the force of interaction between the plates is supposed to be the same in a vacuum and in a liquid dielectric. In reality, however, this is not the case. Experiments show that the force acting between the plates immersed in a liquid dielectric of relative permittivity epsilon r is epsilon r times less than the force exerted in a vacuum. We have the same findings in the experiments conducted with dielectric media in gaseous state. In the case of solid dielectric materials, such experiments are difficult to perform in practice. The change in the force acting between the plates cannot be explained by the presence of the bound charges, but it is due to mechanical stresses produced in the dielectric media. The result of such experiments can also be interpreted as follows. For the same amount but opposite charges on the plates, the energy U of the electrostatic field produced by the charges is given by 1/2 times the square of the amount Q of charges on each plate, over the capacitance C of the plates immersed in the dielectric fluid. We already saw that the capacitance C of a parallel plate capacitor with a dielectric material of relative permittivity epsilon r between its plates, is epsilon r times greater than the capacitance C naught of the same capacitor in a vacuum. If we substitute this expression into the right-hand side of the equation describing the energy U of the electrostatic field between the charged plates immersed in the liquid dielectric, we find that it is epsilon r times less than the energy U naught of the charged plates in a vacuum. Now we apply the principle of virtual work, where the distance x between the plates is changed by an infinitesimal amount. The principle states that the infinitesimal virtual work W done by the electrostatic force moving one of the plates is the product of the force Fx and the infinitesimal distance x covered by the moving plate. Since the virtual work done by the electric field reduces the energy of the field with the equivalent amount of energy, we can formally divide the virtual work or the negative change in the energy U by the infinitesimal distance. Then we can write the force F acting in the x direction perpendicular to the plates as the negative partial derivative of the energy U of the field with respect to the distance x. By substituting the expression for the energy U of the electric field into this equation, we obtain the equation stating that the force F acting in the x direction between the plates is epsilon r times less than the force F naught acting in the x direction between them in a vacuum. This explanation only holds for liquid dielectrics. Any infinitesimal motion of conducting materials surrounded by solid dielectrics can modify the state of the insulating medium related to the mechanical stresses, and hence its electric properties. In such a case we even need to take into account the change in the mechanical energy stored in the materials in the system of conductors and dielectrics. In the second experiment, we insert a dielectric slab of relative permittivity epsilon r into the space between the plates of a charged parallel plate capacitor, where the dimensions of the plates are given by the lengths Lx and Ly, and d denotes the distance between the plates. If the space between the plates is completely filled with a dielectric medium, then the capacitance of the capacitor will be epsilon r times greater than its capacitance in a vacuum. Let us consider the situation where the dielectric slab is not fully inserted into the space between the two charged plates, and its position is described by the distance x measured along the motion of the slab. As a result, there is a free volume between the plates with a vacuum or air beside a volume occupied by some part of the dielectric slab. In such a situation, a force F is exerted on the dielectric pointing inward the capacitor, which is related to the non-uniform electric field at the edge of the plates of the capacitor, and its quantitative analysis is complicated. If we do not want to examine this effect in great detail, then we can calculate the force F by applying the law of conservation of energy in a similar way as it was derived from the principle of virtual work in the first experiment. We already saw that the energy U of the electric field of a charged capacitor is equal to 1/2 times the capacitance C of the capacitor times the square of the voltage V between its plates. The law of conservation of energy states that the change in the energy of the capacitor is equal to the work done on the slab by the electrostatic force F in the x direction. Then this force can be written as the negative partial derivative of the energy U of the electric field with respect to the distance x along which the work is done by the electrostatic field. If we substitute the expression describing the energy U into the right-hand side of this equation, then we obtain negative 1/2 times the square of the voltage V times the derivative of the capacitance C with respect to x. As the formula shows, we need to know the explicit dependence of the capacitance of the capacitor on the distance x describing the position of the dielectric slab between its plates. By examining the geometry of this setup, we can see that it is equivalent to two charged capacitors in parallel connection where the first one has a vacuum or air between its plates and the second one has the dielectric medium of relative permittivity epsilon r between its plates. The capacitance C1 of the first capacitor is equal to the vacuum permittivity epsilon naught times the ratio of the area A1 of its plates over the distance d between its plates. Similarly, the capacitance C2 of the second capacitor is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon r, times the ratio of the area A2 of its plates over the distance d between its plates. As the figure shows, the area A1 over the plate of the capacitor is equal to the difference between the length Lx and the distance x times the length Ly, whereas the area A2 is simply equal to x times Ly. We already proved that the total capacitance of capacitors connected in parallel is given by the sum of the individual capacitances, that is the capacitance C of the capacitor in the experiment is equal to the sum of the capacitances C1 and C2 of the capacitors in the equivalent circuit. If we substitute the expressions for the capacitances into the right-hand side of the equation where the areas can be expressed by the linear dimensions Lx, Ly, and x, then the capacitance C can be written as the vacuum permittivity epsilon naught times the ratio of the length Ly of the plates to the distance b between them, times the quantity of the length Lx minus the distance x plus the relative permittivity epsilon r times the distance x. If we substitute this expression into the force equation and calculate the derivative, then the force Fx acting on the dielectric slab can be written as negative 1/2 times the square of the voltage V through the capacitor, times the ratio of the vacuum permittivity epsilon naught times the length Ly of the plates in the direction perpendicular to the motion of the slab to the distance d between the plates, times the relative permittivity epsilon r of the dielectric minus 1. We note that the force acting on the polarized dielectric slab is proportional to the square of the potential difference between the plates, where the constant of proportionality depends on the geometry of the capacitor and the relative permittivity of the dielectric material. We can also interpret other well-known phenomena in electrostatics based on the polarization of dielectrics. When a charged object attracts small bodies made of insulating material, for example when a piece of amber rubbed by wool or a glass rod rubbed by leather attracts small bits of paper, we can talk about an effect caused by polarization charges. A glass rod with positive electric charge will attract the negative polarization charges on the bits of paper and repel the positive polarization charges on it. The net force will be attractive since the field strength closer to the rod is greater than the field strength farther away. The very nature of the mechanism of attraction is the spatial non-uniformity of the electrostatic field around the charged body. The attractive force always points from the place where the field strength is smaller to the place where the field strength is greater. If the electrically neutral bodies made of dielectric material are small, like the bits of paper, then the polarized dielectrics can be approximated as electric dipoles, and the electrostatic force attracting them is relatively easy to determine. By considering the polarized small bodies as induced dipoles, we can describe them with the electric dipole moment P given by the polarization charge q times the distance vector d pointing from the negative charge to the positive one at the two ends of the dipole. In the case of a point charge q, the force F acting on the charge in an electric field is equal to the amount of charge q times the electric field strength E evaluated at the position of the point charge. In the case of the electric dipole, the net force F acting on the dipole is the vector sum of the forces acting on the charges at the opposite ends of the dipole. Thus F is given by the charge q times the electric field strength E evaluated at the position vector r pointing from an arbitrary reference point O to the midpoint of the dipole, plus 1/2 times the distance vector d, plus the charge q times the electric field strength E evaluated at the position vector or minus 1/2 times the distance vector d. If we factor out the charge q, then we only need to determine the vector sum of the field strength evaluated at the opposite ends of the dipole. For a small polarized dielectric, the distance d is also small, and we can expand the electric field strength about the opposite ends of the dipole at the distance of 1/2 times d from its midpoint. Then the field strength E evaluated at r plus 1/2 times d has the Taylor expansion of the zeroth order term E evaluated at the midpoint r, plus the first order term 1/2 times the directional derivative of E in the direction of the vector d, plus the higher order terms. Similarly, we can expand the field strength E evaluated at r minus 1/2 times d as E evaluated at the midpoint r, minus 1/2 times the directional derivative of E in the direction of d, plus the higher order terms. Here 1/2 is factored out from the directional derivative, which is a linear operator. Hence, the electrostatic force F acting on the dipole can be approximated by the charge q times the vector sum of 1/2 times the directional derivative of the field strength E in the direction of the vector d with itself. This sum gives the directional derivative of the field strength E in the direction of the charge q times the vector d. Since q times d is the dipole moment p, we can express the force F exerted on the induced dipole by the electrostatic field E as the directional derivative of the field strength E in the direction of the dipole moment p of the dipole. We already saw that the dipole moment p of a molecule is equal to the molecular polarizability alpha of the molecule, times the field strength E of the local electric field polarizing the molecule. In fact, this relationship can also be applied for a single induced dipole representing a small polarized body, where we can write the dipole moment in terms of the external field E applied on the body if we replace the polarizability alpha with the effective polarizability alpha E including the local field correction. Then the force F is given by alpha E times the directional derivative of the field strength E in its own direction. Now we transform the derivative by using the vector identity for the gradient of the dot product of two vectors, let us say v and w, stating that the gradient of their dot product is equal to the derivative of w in the direction of v, plus the derivative of v in the direction of w, plus the cross product of v with the curl of w, plus the cross product of w with the curl of v. For v and w equal E, this identity can be reduced to the equation stating that the gradient of E squared is given by 2 times the derivative of E in the direction of E, plus 2 times the cross product of E and the curl of E. The second term in the right-hand side vanishes due to the fact that the electrostatic field E is curl-free. If we substitute this result into the force equation, then we conclude that the force F acting on a small dielectric body polarized in an electrostatic field E is equal to 1/2 times the effective polarizability alpha E of the dielectric, times the gradient of the square of the magnitude of the field strength E. Unlike the previous example with the parallel plate capacitor, we have proven that the electrostatic force acting on a small polarized body is proportional to the gradient of the square of the electric field strength, instead of the square of the potential difference measured in the direction of the gradient of the field. At the same time, it can still be shown that the effective polarizability representing the constant of proportionality can also be expressed in terms of the permittivity of the given dielectric, and it depends on the shape and size of the body. In order to examine more general cases, we will introduce the Maxwell stress tensor describing the interaction between an electrostatic field and a charged insulating material. Firstly, we consider a homogeneous liquid dielectric medium of relative permittivity epsilon r. In electrostatic, the two Maxwell equations tell us that the divergence of the electric displacement field D in the medium is equal to the free charge density ρ, and the electrostatic field E is curl-free. In a linear dielectric, the displacement vector D is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon r of the dielectric, times the electric field strength E in the dielectric, where epsilon r is constant due to the homogeneity of the medium. The product of epsilon naught and epsilon defines the absolute permittivity epsilon of the dielectric. If we insert this expression into the first Maxwell equation, then we can write the volume charge density ρ of free charges as the divergence of the product of the absolute permittivity epsilon and the electric field strength E. Since epsilon is a constant, it can be factored out, that is ρ is equal to epsilon times the divergence of the field strength E. Now we assume that the electrostatic force density F in the medium is given by the charge density ρ times the field strength E for dielectric fluids. By applying the expression obtained for ρ, the force density can be written as epsilon times the divergence of E, times E. In order to transform the right-hand side into a more convenient form, we use the vector identity for the tensor divergence of the tensor products of two arbitrary vector fields, let us say V and W, stating that the divergence is equal to the divergence of the vector V times the vector W, plus the directional derivative of the vector W with respect to the vector V. If both the vectors are equal to the electric field strength E, then the divergence of the tensor product of E with itself is given by the divergence of E times E, plus the directional derivative of E with respect to itself. Here the second term can also be written as nabla sub E, indicating that the derivative of the vector field E is taken in the direction of E. We also apply another vector identity for the gradient of the dot products of the vector fields V and W, stating that it is equal to the derivative of W in the direction of V, plus the derivative of V in the direction of W, plus the cross product of V with the curl of W, plus the cross product of W with the curl of V. For V and W equal E, this identity can be reduced to the equation stating that the gradient of E squared is given by 2 times the derivative of E in the direction of E, plus 2 times the cross product of E and the curl of E. The second term in the right-hand side vanishes due to the fact that the electrostatic field E is curl-free, as stated in the second Maxwell equation. If we combine the two identities applied for the field strength E by eliminating its directional derivative with respect to itself, then we can write the divergence of E times E as the divergence of the tensor product of E with itself, minus the gradient of 1 over 2 times E squared. This result can be substituted into the equation for the force density F, where we can factor out the nabla operator and write F as the absolute dielectric constant epsilon times the divergence of the difference between the tensor product of the field strength E with itself, and 1 over 2 times the square of the magnitude of the field strength E times the unit tensor I. Now we introduce the Maxwell stress tensor T of the electrostatic field E in a homogeneous dielectric medium of absolute permittivity epsilon in the form epsilon times the difference between the tensor product of the field strength E with itself, and 1 over 2 times the square of the magnitude of the field strength E times the unit tensor I. This quantity is a tensor of rank 2, which can be represented by a matrix with the tensor components in a given coordinate system. If we attach a Cartesian coordinate system to the insulating material of dielectric constant epsilon placed in the electric field E, then the components ij of the stress tensor T are given by epsilon times the difference between the I component of the vector E times the j component of the vector E, and 1 over 2 times E squared times the Kronecker delta sub ij, where the indices I and j denote the Cartesian coordinates x, y, and z. As a result, we can express the electrostatic force density F exerted on a dielectric medium by an electrostatic field as the divergence of the Maxwell stress tensor of the field in that medium. Then the electrostatic force F acting on the insulating material given by the volume integral of the force density over the volume V occupied by the material, is equal to the volume integral of the divergence of the Maxwell stress tensor of the field in the material. By applying the divergence theorem, the electrostatic force F can be written as the surface integral of the stress tensor T over the boundary surface S of the volume V. Now we provide the physical interpretation of the Maxwell stress tensor. Firstly, we note that since the relative permittivity of a vacuum is exactly 1, the absolute dielectric constant epsilon appearing in the definition of the stress tensor is equal to the dielectric constant epsilon not in a vacuum. In many cases this tensor is defined by applying vacuum permittivity, that is for an electrostatic field in a vacuum. If we expand the stress tensor in a Cartesian coordinate system, then we can represent its components the following matrix. By definition, the Maxwell stress tensor is symmetric and represented by a symmetric matrix. We already saw that the surface integral of the stress tensor of an electrostatic field over the surface of a body in the field gives the total electrostatic force acting on the body. This fact indicates that the components of the tensor represent a force per unit area exerted by the electrostatic field. Indeed, we can consider the SI unit of the absolute dielectric constant that is equal to the unit of the vacuum permittivity epsilon naught, which is given by farad per meter, or Newton per volt squared. Since the SI unit of the electric field strength E is equal to volt per meter, the matrix elements show that the SI unit of the components of the stress tensor is given by the product of Newton per volt squared and the square of volt per meter. This expression gives Newton per square meter, indicating that the components of the Maxwell stress tensor represent either pressure or shear stresses exerted on the body by the electric field. If we examine the elements of the matrix representing the tensor, we can see that its diagonal components describe either the pressure or the pulling tension exerted on planes perpendicular to the respective direction. We can talk about pressure or tension depending on the sign of the difference between the two terms in the diagonal components. If the first term describing the longitudinal tension of the electric field is less than the second term representing the isotropic pressure, that is the component is negative, then we can talk about the pressure exerted on the planes by the electric field. If the second term is less than the first one, that is the diagonal component is positive, then it describes the tension produced by the field. For example, let us consider the XX component of the stress tensor given by the absolute permittivity epsilon, times the difference between the square of the X component of the electric field strength E and 1 over 2, times the square of the magnitude of the vector E. This component describes the force per unit area in the x direction acting on a planar surface element perpendicular to the x-axis. In the figure, this component is represented by the blue arrow pointing outward from the blue face of the rectangular volume element with faces parallel with the Cartesian coordinate axes. The blue arrow representing the positive component T sub xx is interpreted as the pulling tension exerted in the x direction on the blue face of the volume element perpendicular to the x direction. If the component T sub xx is negative, then the blue arrow points inward and represents the pressure exerted on the blue face of the volume element in the x direction. The same interpretation holds for the other two diagonal components T sub yy and T sub zz, indicated by the directions and the orientations of the yellow and red arrows pointing outward from the yellow and red faces of the volume element. The off-diagonal components of the Maxwell stress tensor represent the shear stresses on planes that are parallel with the respective direction. For example, the component T sub xy of the stress tensor is given by the absolute permittivity epsilon times the product of the x and y components of the electric field strength E. This component is represented by the yellow arrow lying in the plane of the blue face of the volume element and pointing in the y direction. This quantity is interpreted as the shear stress acting on the blue area element perpendicular to the x-axis acting in the direction of the y-axis. Similarly, the component T sub xz describes the shear stress exerted on the blue area element in the z direction, indicated by the red arrow. The same interpretation can be made for the other off-diagonal components represented by the arrows lying in the yellow and red faces of the volume element. As in the case of the dielectric tensor or the susceptibility tensor of insulating materials, the Maxwell stress tensor T of rank 2 can also be interpreted as a linear map between vector spaces. That is, it maps an arbitrary vector v into another vector which is given by the contraction of the tensor T and the vector v. The later can simply be computed by a matrix vector multiplication of the matrix of the tensor T and the column vector of the vector v expanded in some coordinate basis. If the vector v is a unit vector, its contraction with the stress tensor T gives the traction produced by the electric field in the direction of the unit vector. Since the stress tensor is a tensor of rank 2, it can also be interpreted as a multilinear map from the Cartesian product of two vectors to scalars. The tensor T can be evaluated at two arbitrary vectors v and w, which is simply the composition of the contraction of the tensor T with the vector w, and the dot product of the result of the contraction and the vector v. This operation has also a simple representation when the vectors and the tensor are expanded in some coordinate basis. Then the result of the matrix vector multiplication of T and W gives a column vector that can be contracted by the row vector of the components of V. We also saw that the Maxwell stress tensor is symmetric, that is, if we exchange the vectors V and W then we obtain the same result. This symmetry has a deep physical meaning as we will see when we evaluate this second-rank tensor at unit vectors pointing into arbitrary directions. If we evaluate the stress tensor T at a normal vector n to an area element, then we obtain the normal electrostatic stress or traction acting on that area element. Its explicit term is given by the absolute permittivity epsilon of the medium surrounding the area element, times the difference between the square of the normal component of the electric field strength E to the area element, and 1/2, times the square of the field strength E. Again, by expanding the parentheses we obtain two terms describing the longitudinal tension and the isotropic pressure exerted on the area element by the field. We can also evaluate the Maxwell stress tensor at two unit vectors n and m, which gives the projection of the electrostatic traction in a given direction. This is equal to epsilon times the product of the components of the field strength E in the directions of the vectors n and m, describing the traction in the direction of the unit vector m across the area element oriented in the direction of the unit vector n. If we consider two area elements with the normal vectors n and m, then the symmetry of the tensor just means that the traction or the shear force acting in the direction of the normal to the first area element across a second surface element is equal to the shear force acting in the direction of the normal to the second area element across the first area element. This force balance prevents area elements from spontaneously spinning, that is, electrostatic fields do not exert a net internal torque density on infinitesimal volume elements. Consequently, the symmetry of the stress tensor guarantees the conservation of angular momentum within electrostatic fields and ensures that the field do not exert a net self-torque on a closed system. As an illustration of the application of the Maxwell stress tensor in electrostatics, we revisit the problem of a homogeneous dielectric sphere immersed in a liquid dielectric, where the sphere is charged and the whole system is polarized by a uniform electric field. Here the uniformly charged sphere of radius R has the charge q, and the external electric field E0 points in the z direction. epsilon 1 and epsilon 2 denote the absolute permittivities of the liquid dielectric and the dielectric sphere, respectively. At a given point P outside the sphere described by the position vector or pointing from the center of the sphere to the point P, we can express the total electric field E as the superposition of three different fields. The Coulomb field EQ due to the electric charge Q of the dielectric sphere, the induced dipole field E' of the polarized sphere, and the external field E not applied on the liquid dielectric. In order to describe these fields we use a spherical coordinate system adapted to the position of the dielectric sphere and the direction of the external electric field, that is with the origin at the center of the sphere and the polar axis pointing in the z direction. Then the coordinate components of the physical fields in the problem have no azimuthal dependence, and the unit vector pointing in the z direction can be decomposed as the cosine of the polar angle theta times the unit vector ER pointing in the radial direction, minus sine theta times the unit vector E theta pointing in the polar direction. As a result, the magnitude of the Coulomb field EQ is simply equal to 1 over 4 pi times the absolute permittivity epsilon 1 of the dielectric fluid, times the charge Q of the sphere over the square of the distance or between the center of the sphere and the point P. The unit vector ER determines the radial direction of the field pointing outward. For the sake of brevity we denote the magnitude of the Coulomb field by E sub Q1, which is a function of the distance r. The index 1 indicates that the expression of the magnitude contains the dielectric constant epsilon 1. For the induced field E' around the small polarized sphere we can apply the electric dipole approximation and assume that this field is produced by an induced dipole of electric dipole moment P. We already derived the formula describing a dipole field in a vacuum. Then the field strength E' of such a field in a dielectric medium at the point P determined by the position vector R can be written as 1 over 4 pi times the absolute permittivity epsilon 1 of the medium, times the difference between 3 times the dot product of the vectors P and R times R, and R squared times the vector P, over R to the 5th power. Since the dipole moment P of the uniformly polarized sphere points in the direction of the external electric field E0, that is in the z direction, it can be expressed in terms of the radial unit vector ER and the polar unit vector E theta. If we substitute this decomposition into the numerator of the fraction in the expression describing E', and write the dot product of the vectors P and R as the product of their magnitudes times cosine theta, then the numerator can be written as the difference between 2 times P times R squared times cosine theta times the unit vector ER, and R squared times P times sine theta times the unit vector E theta. By inserting this expression into the right-hand side of the equation describing the polarization field, it can be expressed as the dipole moment P over 4 pi times the permittivity epsilon 1 times the distance R cubed, times the sum of 2 times cosine theta times the unit vector ER and sine theta times the unit vector E theta. Here we also introduce the shorthand notation EP for the multiplication factor P over 4 pi times epsilon 1 times R cubed. The last electric field that has a contribution to the field outside the sphere is the external field E0 written as its magnitude E0 times the unit vector pointing in the z direction, where we decompose the unit vector in the radial and polar directions as well. Now we can write the radial and polar components of the electric field outside the charged and polarized dielectric sphere as follows. Its component in the radial direction is equal to E sub q1 plus 2 times EP times cosine theta plus E0 cosine theta, whereas its polar component is given by EP times sine theta minus E0 times sine theta. The electric field inside the sphere is the superposition of two fields, the Coulomb field due to the charge Q and the cavity field EC due to the polarized dielectric fluid surrounding the sphere modified by the polarization field in the dielectric sphere. Since we assume that the sphere has a uniform charge distribution, the magnitude of the electric field EQ at any point within the sphere can be written as 1 over 4 pi times the absolute dielectric constant epsilon 2 of the sphere, times the charge Q over the cube of the radius capital R, times the distance R between the point and the center of the sphere. The direction of the spherically symmetric field is given by the radial unit vector ER. Here we also introduce the notation E sub Q2 for the magnitude of the field. The cavity field EC modified by the polarized sphere has the same direction as the external electric field polarizing the whole system, and it is given by the magnitude of EC times the unit vector EZ pointing in the z direction. The later can be decomposed into the radial and polar directions as well. As a result, the radial component of the internal electric field is equal to E sub Q2 plus EC times cosine theta, whereas its polar component is given by negative EC times sine theta. In the next step we apply the boundary conditions of the quantities describing the electric field inside and outside the sphere. We already studied the behavior of the field strength and the displacement field across a boundary interface between two dissimilar dielectrics. We found that the tangential component of the field strength E is continuous across the interface, that is, the tangential component of the field strength outside the sphere is equal to the tangential component of the field strength inside the sphere over the boundary surface of the sphere. We also established that the normal component of the displacement field D is discontinuous across the interface, that is, the difference between the normal component of the displacement field outside the sphere and the normal component of the displacement field inside the sphere is equal to the surface charge density sigma of the free charges over the boundary surface of the sphere. The boundary condition for the normal component of the field is represented by the condition for the polar components of the fields outside and inside the sphere, as the azimuthal component of the field vanishes due to its symmetry about the z-axis passing through the center of the sphere. That is, the polar components of the electric field strengths outside and inside the sphere must be equal to each other at the boundary interface of the radius R of the sphere. If we substitute the expressions obtained for the polar components of the electric field strengths outside and inside the sphere into this condition, then we can write the equation stating that EP evaluated at R times sine theta minus E naught times sine theta is equal to negative EC times sine theta. This condition must hold for an arbitrary polar angle. Therefore, we reduce this equation to the condition stating that EP evaluated at R minus E naught is equal to negative EC. We follow the same procedure for the boundary condition describing the jump of the displacement field across the interface. Because the displacement vector D is given by the absolute dielectric constant of the given medium times the field strength E, the condition for the normal component of the displacement field across the interface at the boundary of the sphere states that the difference between epsilon 1 times the radial component of the electric field strength E outside the sphere and the epsilon 2 times the radial component of the electric field strength E inside the sphere is equal to the surface density sigma of the free charges over the interface. We assume that the free charge Q is distributed uniformly throughout a volume of the sphere, which drops to zero over the infinitely thin shell representing the boundary interface. That is, the surface charge density sigma of free charges vanishes over the interface. Now we use the expressions obtained for the radial components of the electric field strength outside and inside the sphere evaluated at the radius R, and substitute them into the equation of the boundary condition. We also insert the definitions of the shorthand notations E sub q1, E sub q2, and EP into this equation, where each of them is evaluated at the radius R. If we expand the parentheses, we can see that the terms containing the charge Q cancel out each other and the equation can be reduced to the form, stating that the quantity of P over 4 pi times R cubed plus epsilon 1 times E naught minus epsilon 2 times EC multiplied by cosine theta, is equal to 0. This equation must hold true across all angles theta around the sphere, that is, the quantity in the parentheses must vanish. We also substitute the definition of E sub q1 into the first boundary condition and we obtain two equations that can be used to eliminate the variable EC by multiplying the second one by epsilon 2 and adding the result to the first equation. Then we can express East P evaluated at R, that is P over 4 pi times epsilon 1 times R cubed, as the difference between the dielectric constants epsilon 2 and epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times the magnitude of the external field E naught. Now we can evaluate the radial and polar components of the electric field outside the sphere over the boundary interface between the dielectric fluid and the sphere, by inserting the expression of EP evaluated at the radius R into the component equations. For the radial component we obtain E sub q1 evaluated at R, plus 2 times the ratio of epsilon 2 minus epsilon 1 to epsilon 2 plus 2 times epsilon 1, times E naught times cosine theta, plus E naught times cosine theta. The second and the third terms in the right-hand side can be reduced to the term 3 times epsilon 2 over epsilon 2 plus 2 times epsilon 1, times E naught times cosine theta. Here we introduce the notation AN for E sub q1, and the notation B for 3 times epsilon 2 over epsilon 2 plus 2 times epsilon 1, times E naught. Then the radial component of the electric field strength E evaluated at the radius R can be written as A plus B times cosine theta. Similarly, for the polar component of the field strength E evaluated at R we obtain the ratio of epsilon 2 minus epsilon 1 to epsilon 2 plus 2 times epsilon 1, times E naught times sine theta, minus E naught times sine theta. The right-hand side can be written as negative 3 times epsilon 1 over epsilon 2 plus 2 times epsilon 1, times E naught times sine theta, where we introduce the notation C for negative 3 times epsilon 1 over epsilon 2 plus 2 times epsilon 1, times E naught. Then the polar component of the field strength E at the radius R can be expressed by C times sine theta. Now we are able to determine the Maxwell stress tensor of the net electric field on the boundary interface between the dielectric sphere and the liquid dielectric surrounding the sphere by evaluating the field over the interface and the fluid side. Outside the sphere, the stress tensor T is defined by the absolute permittivity epsilon1 of the liquid dielectric, times the difference between the tensor product of the electric field strength E outside the sphere with itself, and 1/2 times the square of the magnitude of the field strength E times the unit tensor I. For the sake of brevity, we drop the subscript of the field strength E, indicating that it describes the field outside the sphere. We will determine the components of the stress tensor in the spherical coordinate system that are relevant to the calculation of the force exerted on the sphere by the electric field. Firstly, we evaluate the stress tensor T in both of its arguments at the radial unit vector, which gives epsilon1 times the difference between the dot product of the field strength E with the radial unit vector ER times the same dot product, and 1/2 times E squared times the dot product of the radial unit vector ER with itself. This gives epsilon1 times the difference between the square of the radial component of the field strength E, minus 1/2 times epsilon1 times the square of the magnitude of the field strength E. Since the azimuthal component of the electric field E vanishes due to its symmetry about the z-axis, the square of its magnitude is equal to the sum of the square of its radial component and the square of its polar component. As a result, we obtain 1/2 times epsilon1, times the difference between ER squared and E theta squared. Now we can substitute the expressions obtained for the radial and polar components of the field strength E outside the sphere into the right-hand side of this equation. By expanding the terms in the parentheses, we can write the pure radial component of the Maxwell stress tensor T as 1/2 times epsilon1 times the quantity of A squared plus 2 times A times B times cosine theta, plus B squared times the square of cosine theta, minus C squared times the square of sine theta. We also determine the mixed component theta r of the stress tensor T by evaluating it at the polar and radial unit vectors, which gives epsilon1 times the difference between the dot product of the field strength E with the polar unit vector E theta times the dot product of the field strength E with the radial unit vector ER, and 1/2 times the square of the magnitude of the field strength E times the dot product of the polar and radial unit vectors E theta and ER. Since the basis vectors of the spherical coordinate system are mutually orthogonal, the second term in the bracket vanishes and we obtain epsilon1 times the product of the radial and the polar components of the field strength E. If we substitute the expressions obtained for the radial and polar components of the field strength E into the right-hand side of the equation, then the theta r component of the stress tensor T can be written as epsilon1 times the sum of A times C times sine theta and B times C times cosine theta times sine theta. These tensor components can be used to evaluate the stress tensor at the unit vector Ez pointing in the direction of the external electric field E0 and at the radial unit vector Er. We already decomposed the unit vector Ez as the difference between cosine theta times the radial unit vector Er and sine theta times the polar unit vector E theta. If we insert this decomposition into the stress tensor T evaluated at the vectors Ez and Er, we can split it into the difference between the stress tensor T evaluated in its both arguments at the radial unit vector Er times cosine theta, and the stress tensor T evaluated at the polar unit vector E theta and the radial unit vector Er times sine theta. The expressions derived for the tensor components in the right-hand side can be substituted here, and we can express the stress tensor evaluated at the vector Ez and Er over the boundary interface between the liquid and the sphere in terms of the constants A, B, and C, and the polar angle theta. In the last step we determine the total force acting on the charged dielectric sphere submerged in the liquid dielectric under the influence of an external uniform electric field. We already established that the force F acting on a body in an electric field can be expressed by the surface integral of the Maxwell stress tensor T of the field over the boundary surface S of the body. In the case of a sphere, this surface integral can be written as the integral of the contraction of the tensor T with the radial unit vector Er pointing the normal to the surface of the sphere. Now the force exerted on the dielectric sphere can be decomposed in the z direction of the external electric field and its transversal component, where the later is cancelled due to the symmetry of the problem. Then it is enough to determine the z component of the force F given by the dot product of the force vector F and the unit vector Ez pointing in the z direction. If we substitute the surface integral into the force vector F, then we obtain a surface integral of the Maxwell stress tensor T evaluated at the unit vector Ez and the radial unit vector Er over the boundary surface S of the sphere. By inserting the expression that we derived for the stress tensor evaluated at the vectors Ez and Er into the right-hand side, we can split the surface integral into two terms. The first term is equal to 1/2 times epsilon1, times the surface integral of the terms in the parentheses times cosine theta, where we have a squared plus 2 times a times b times cosine theta, plus b squared times the square of cosine theta, minus c squared times the square of sine theta in the parentheses. Similarly, the second term is given by negative epsilon 1 times the surface integral of the terms in the parentheses times sine theta, where we have a times c times sine theta, plus b times cosine theta times sine theta in the parentheses. Then we transform the surface integrals over the boundary surface S of the sphere of radius R into the integrals over the full solid angle by substituting the surface element ds with r squared times the infinitesimal solid angle d omega. Here we also factor the constants a, b, and c out of the integrals over the full solid angle. As a result, the integrands become purely trigonometric functions of the polar angle and the products of these trigonometric functions, which are integrated over the full solid angle. For cosine theta, the cube of cosine theta, and cosine theta times the square of sine theta, these integrals vanish. The only terms integrated over the full solid angle that give non-zero results are the integral of the square of cosine theta, which is equal to 4 pi over 3, and the integral of the square of sine theta, which is equal to 8 pi over 3. Then we can write the z component of the force F as 4 pi over 3, times epsilon 1 times r squared times a, times the difference between b and 2 times c. Now we substitute the definitions of the constants a, b, and c into the right-hand side of the equation, where a is given by 1 over 4 pi times epsilon 1, times q over the square of capital R, b is equal to 3 times epsilon 2 over the sum of epsilon 2 and 2 times epsilon 1, times e naught, and c is given by negative 3 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times e naught. If we simplify the result, the multiplication factor of the terms in the parentheses reduces to q, and the terms in the parentheses can be written as the sum of epsilon 2 and 2 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times e naught. This just gives q times e naught, and we have proven that for liquid dielectrics the resultant force F of the electrostatic and mechanical forces acting on the charged sphere surrounded by a dielectric medium is given by the charge q of the sphere times the external electric field E naught acting on the liquid and the sphere. As already stated, this result holds for any charged body of arbitrary shape. The phrase mechanical forces in this statement might be somewhat misleading, since the force F acting on the charged body has a purely electrostatic origin transmitted through the polarized liquid dielectric as a stress or pressure exerted on the charged and polarized dielectric sphere. The total force acting on the sphere immersed in the dielectric fluid also includes the forces due to hydrostatic pressure, gravity and buoyancy, that is the force F is given by the charge q times the field strength E naught, plus the mass m of the body times the gravitational acceleration g, minus the density ρ of the liquid times the volume v of the body times the gravitational acceleration g, or simply q times E naught plus the difference between the mass m and the density ρ times the volume v, times the gravitational acceleration g. We also note that when we consider the electric field EC inside the sphere we interpreted it as the cavity field produced by the polarized liquid dielectric surrounding the sphere, which is modified by the polarization field of the dielectric sphere. We saw that it can be written as negative EP evaluated at capital R, plus the external electric field E naught. Because we expressed EP evaluated at capital R as the difference between epsilon 2 and epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times E naught, the field EC can be written as 3 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times E naught. But this is equal to the negative constant c, that is the later represents the uniform electric field inside the sphere. We also see that the constant B has a similar form, and it in fact describes the electric field in the liquid layer immediately surrounding the sphere. We finish the presentation about the Maxwell stress tensor of an electrostatic field with the generalization of the electrostatic force density formula by introducing the so-called Korteweg-Helmholtz force density. As already shown, the electrostatic force density F acting on a body made of dielectric material under the influence of an electrostatic field is given by the free charge density ρf in the body, times the electric field strength E of the field. Here we use the subscript F for the volume density of free charges, while the letter ρ without any subscript will denote the density of the dielectric material. We also prove that the force density F can be expressed by the tensor divergence of the Maxwell stress tensor T defined by the absolute permittivity epsilon of the dielectric, times the difference between the tensor product of the field strength E with itself, and 1 over 2 times the square of the magnitude of the field strength E times the unit tensor I. However, we derive this expression by supposing that the dielectric material polarized in the electrostatic field is homogeneous and its permittivity is constant. It is not the case for an inhomogeneous dielectric medium where the permittivity of the material depends on the position r, that is epsilon does not commute with the nabla operator. If we assume that the force density is given by the tensor divergence of the stress tensor and the form of the tensor is still the same for inhomogeneous insulating materials, then we need to generalize the formula for the force density for such cases. If we substitute the expression of the stress tensor into the divergence in the right-hand side of the force density formula, then the later can be split into two terms. The tensor divergence of the tensor product of epsilon times E, and negative 1 over 2 times the gradient of the product of epsilon and E squared. By expanding the bracket in the first term in the right-hand side, we write it as the directional derivative of epsilon in the direction of the vector E, times the vector E, plus epsilon times the divergence of the vector E, times the vector E, plus epsilon times the directional derivative of the vector E in the direction of itself. The later can be expressed by epsilon times the gradient of 1 over 2 times E squared in the case of an electrostatic field which is curl-free, as it was shown when we derived the explicit form of the stress tensor. At the same time, we also split the last term in the right-hand side into negative 1 over 2 times E squared times the gradient of epsilon, and negative 1 over 2 times epsilon times the gradient of E squared. The third and the last terms in the right-hand side cancel out each other, reducing the right-hand side of the equation to three terms. Now we apply the first Maxwell equation in electrostatics stating that the divergence of the product of the absolute permittivity epsilon and the field strength E at any point of a polarized dielectric medium is equal to the volume density ρf of the free charges at that point. This equation can be written in the form stating that the dot product of the vector E times the gradient of epsilon, plus epsilon times the divergence of the vector E, is equal to the free charge density ρf. If we express epsilon times the divergence of E by ρf minus the dot product of E and the gradient of epsilon, then we can substitute it into the second term in the right-hand side of the force density formula, which gives us four terms. Because the first and the third terms cancel each other out, we conclude that the force density F produced by an electrostatic field E in a charged and homogeneous dielectric medium of absolute permittivity epsilon is equal to the difference between the volume density ρf of free charges in the medium times the field strength E, and 1 over 2 times the square of the magnitude of the field strength E times the gradient of the absolute permittivity epsilon of the insulating material. However, this is not the most general formula for the electrostatic force density acting on charged dielectric materials placed in an electrostatic field. We can assume that the dielectric medium is homogeneous, but it can still be the case for liquid dielectrics that its permittivity depends on the density ρ of the fluid. We note that the absolute permittivity of a fluid can be a function of its temperature as well, which makes its behavior even more complicated in electrostatic fields. As a result, a liquid dielectric of a fixed mass m given by the product of its density ρ and its volume v, any modification in the density or temperature causes a change in its electrostatic properties. For example, if we perform a quasi-static infinitesimal isothermal compression on the liquid, the compression changes both its density and volume. Then we can determine the variation of these quantities stating that the vanishing variation of the fixed mass m is equal to the infinitesimal change d ρ in the density times the volume v, plus the density ρ times the infinitesimal change dv in the volume. Hence, the differential of ρ can be written as negative ρ times the differential of v over v. We already established that the energy density U of an electric field E in a dielectric medium is given by 1 over 2 times the absolute permittivity epsilon of the dielectric, times the square of the magnitude of the field strength E. If we keep the electric field fixed during the isothermal compression of the dielectric fluid, we can write the differential du of the energy density as 1 over 2 times E squared, times the differential of its absolute permittivity epsilon. Since the compression of the liquid is performed at a constant temperature, the differential of the permittivity is given by the partial derivative of the permittivity epsilon of the fluid with respect to the density ρ of the liquid at a constant temperature T, times the differential of the density ρ. The latter can be expressed in terms of the differential of the volume of the liquid, and we obtain an equation stating that the differential of the energy density U is equal to negative 1 over 2 times E squared, times the partial derivative of epsilon with respect to ρ at constant T, times ρ times dv over v. At the same time, the energy capital U of the electric field at a volume v of the dielectric medium is given by the energy density U as a function of the volume v of the liquid, times the volume v. Then the variation of the energy capital U of the electric field under the isothermal compression of the dielectric fluid can be written as the volume v of the liquid times the differential of the energy density U of the field, plus the energy density U times the differential of the volume v. If we insert the expression obtained for the differential of the energy density and the explicit form of the energy density into the right-hand side, We can write the differential of the energy capital U as 1 over 2, times the difference between epsilon and rho times the partial derivative of epsilon with respect to rho at constant T, times E squared times dV. In the case of the isothermal compression of the dielectric fluid at a constant field strength E, the pressure P of the liquid is given by the negative partial derivative of the energy capital U of the field stored in the fluid with respect to the volume V of the fluid, while the temperature T and the field strength E are kept constant. Then the derivative of the formula obtained for d capital U with respect to the volume V gives two terms for pressure. The first term is equal to 1 over 2 times epsilon times E squared, which is the Maxwell stress contribution already included in the stress tensor. The second term, however, represents a pressure correction that arises naturally from the dependence of the dielectric constant on density. This gives the Korteweg-Helmholtz force density describing the force acting per unit volume in a dielectric medium of absolute permittivity epsilon and density rho due to an electrostatic field E, where the free charges in the medium are given by the volume charge density rho F. As the formula shows, the force density F is equal to the volume density rho F of free charges times the field strength E, minus 1 over 2 times the square of the magnitude of the field strength E, times the gradient of the absolute permittivity epsilon, plus the negative gradient of the correction pressure given by 1 over 2 times the density rho times the partial derivative of the absolute permittivity epsilon with respect to the density rho, times the square of the magnitude of the field strength E. Although this equation is the combination of the two results derived for inhomogeneous dielectrics and homogeneous dielectrics with density-dependent permittivity, it still holds true for the general case with inhomogeneous dielectric media with density-dependent permittivity. Now we discuss a physical property of a class of insulating materials called ferroelectricity. Materials that can be polarized under certain temperature or in a certain range of temperature without the presence of an external electric field are known as ferroelectric materials. Such materials exhibiting spontaneous electric polarization include Rochelle salt or potassium sodium tartrate, barium titanate, and potassium niobate. The distinguishing properties of ferroelectric materials can be summarized as follows. Ferroelectric materials exhibit exceptionally high permittivity and their dielectric constants can be in the range from thousands to over 100,000, whereas the values of relative permittivity are typically below 10 for common dielectrics. In this table we compare the baseline values of the relative permittivity epsilon R of common dielectric materials from silicon dioxide to titanium dioxide with those of some ferroelectric materials starting with barium titanate. It can be seen that the permittivities of the former group remain in the range under 100, whereas the lowest values of epsilon R is in the order of magnitude of thousands for the ferroelectric materials, and its baseline value is 80,000 for calcium copper titanate shown in the last line. In the third column of the table we display the Curie temperatures of the different ferroelectric materials which we will discuss later. In the case of ferroelectric materials the dependence of the polarization vector on the electric field strength is not linear. Unlike to the majority of dielectric materials, their relative permittivity and electric susceptibility are not constant but functions of the electric field strength. If we change the magnitude of the electric field strength, then the degree of polarization and hence the value of the electric displacement at a given moment in time is influenced not only by the instantaneous value of the field strength but also its previous values, that is the polarization and the electric displacement in a ferroelectric material depend on its history. This phenomenon is known as ferroelectric hysteresis. The plot describes the dependence of the magnitude of the electric polarization vector P of a ferroelectric material on the magnitude of the electric field strength E applied to the material. It shows the lat of the polarization behind the electric field forming a hysteresis loop in the P versus E diagram. The red curve in the plot depicts the behavior of ferroelectric materials when we increase the magnitude of the field strength from 0 at the origin O to the value EA, achieving a maximum value of polarization at the point A in the plot. PS is the saturation value of the polarization of the material at the point A. By reducing the magnitude of the field strength from EA to 0, we follow the blue curve where the value of the polarization decreases, but it does not vanish even if the electric field applied to the ferroelectric material vanishes. Instead, a finite remanent polarization PR remains in the material, indicating its ability to store stable memory states. A reverse electric field EC called coercive field is required to bring the polarization back to 0 at the point B on the blue curve, and only a further increase in the reverse field can achieve a saturation value of the polarization vector pointing in the opposite direction at the point C. If we decrease the reverse field applied to the material so that it vanishes and then increase in its initial direction again, then we obtain the yellow curve from between the points C and A. The hysteresis loop is formed by the blue and the yellow curves in the polarization versus field strength plot. The microscopic origin of ferroelectricity is related to the special crystal structure of ferroelectric materials. We already saw that in the molecular structure of a non-polar dielectric material, the center of the positive charge of the nuclei coincides with the center of the negative charge of the electron cloud, producing electrically neutral atoms without an external field in the crystal. Ferroelectric materials are a specific subcategory of polar dielectrics, that is, they have a crystal structure in which the equilibrium positions of the ions are such that the centers of positive and negative charge do not coincide. As a result, ions behave like electric dipoles, producing spontaneous polarization even if no external electric field is applied to the material. In thermal equilibrium, the molecular orientations in common polar dielectrics are random, so the average polarization in the matter is zero. Under the influence of an external electric field, the electric dipole moments of the molecules tend to align in the direction of the field. When the field is removed, thermal motion randomizes the orientations of the dipoles again. Ferroelectric materials are different since a macroscopic crystal in them is usually not polarized uniformly, but it breaks into ferroelectric domains. In the absence of an electric field, the macroscopic material can be considered as a disordered set of domains with permanent polarization pointing in different directions, so that the net polarization may be small or even zero. The electric dipoles act cooperatively within a ferroelectric domain, whereas the orientation of each dipole is aligned individually by the external field in common polar dielectrics. We can illustrate the situation of the disordered set of domains at the point O in the polarization versus electric field strength diagram if we depict some of the domains in the ferroelectric material. We draw a red isosceles triangle inside each domain with its vertex pointing in the direction of the collective orientation of the dipoles inside the given domain. When an external electric field is applied, the dipole moments and the polarization vectors of the individual domains are arranged in the direction of the field, which is characterized by the red curve on the graph. Reaching the saturation polarization PS at the point A in the diagram, the entire macroscopic material can be considered as a single domain of a polarization pointing in the direction of the field. In this saturation state represented by the point A, the electric dipoles in all domains point in the direction of the external field. When the field is reduced back to zero along the blue curve, the polarization does not return to zero, but the remanent polarization PR remains because many domains stay aligned. To reduce the polarization to zero, the coercive electric field EC in the opposite direction must be applied, producing completely disoriented domains in the material at the point B, as shown in the figure of the ferroelectric domains. By further increasing the reverse field, the dipole moments and the polarization vectors of the disordered domains can be arranged in the direction of the reverse field till they form a single domain at the saturation point C. If we decrease the reverse field to zero and increase the electric field in its original direction, we can reorient the domains the direction of the field again, moving from the point C to the point A along the yellow curve. The displacement vector D for ferroelectric materials can be written as the vector sum of the vacuum permittivity epsilon naught times the electric field strength E, and the polarization vector P, where the later depends on the field strength. Now we define the differential permittivity epsilon D by the derivative of the magnitude of the displacement D with respect to the magnitude of the field strength E. If we substitute the expression for the displacement into the derivative, the differential dielectric constant can be written as epsilon naught plus the derivative of the magnitude of the polarization P with respect to the magnitude of the field strength E. This result shows that the differential permittivity epsilon D of a ferroelectric material gives the tangent of its hysteresis loop at a given point, as indicated by its graph drawn for the yellow curve between the points A and C. Its maximum is at the point of inflection of the curve, and the differential permittivity drops from the maximum to the value of the vacuum permittivity as we approach the saturation range of the polarization. The differential relative permittivity epsilon sub RD of a ferroelectric material can also be defined such that its product with the vacuum permittivity epsilon naught is equal to the differential permittivity epsilon D of the material. That is, epsilon sub dr is just equal to the ratio of epsilon D to epsilon naught. Similarly, the differential susceptibility chi d of a ferroelectric material is given by 1 over the vacuum permittivity epsilon naught, times the derivative of the magnitude of the polarization P of the material with respect to the magnitude of the field strength E applied to the material. Then the differential relative permittivity epsilon sub RD is equal to 1 plus the differential susceptibility chi d, that is, they have the same relationship as the one between the relative permittivity and the electric susceptibility for standard dielectrics. As already mentioned, in the table where we have shown the relative permittivities of ferroelectric materials, their baseline values are used, that is, the initial slope of the displacement as a function of the electric field strength, determined by the tangent to the red curve at the point O in the polarization versus field strength diagram, where the electric field vanishes. In the table comparing the relative permittivities of common dielectrics with the baseline values of the dielectric constants for some ferroelectric materials, a critical temperature Tc called Curie temperature was also shown for ferroelectrics. In 1895 Pierre Curie first recognized the existence of a critical temperature above which ferromagnetism disappears, and this phenomenon was later extended to ferroelectricity. Above the Curie temperature, ferroelectric materials lose their spontaneous polarization and transition into a perielectric state, where they behave as standard dielectrics. Rochelle salt, the oldest known ferroelectric material, exhibits two Curie points, upper and lower critical temperatures at -18 Celsius and 24 Celsius, and only acts as a ferroelectric material within the temperature range between them. The Curie temperature of pure barium titanate, one of the frequently applied ferroelectric material, is typically around 120 degrees Celsius to 130 degrees Celsius as seen in the table. Calcium copper titanate shown in the last line of the table is an incipient ferroelectric material and has no classic Curie temperature, because its polarization does not originate from the crystal lattice itself, but from the accumulation of charges at interfaces inside the material. In a perielectric state above the Curie temperature, the centers of positive and negative charge coincide in the crystal and the spontaneous polarization of the material is zero. Then we cannot talk about any preferred direction for the polarization field in the material, that is, the ferroelectric crystal possesses inversion symmetry. Below the Curie temperature, the material is in a ferroelectric state where a slight displacement of ions in the crystal breaks this inversion symmetry, creating a non-zero spontaneous polarization which defines a preferred direction in the crystal. This phenomenon is considered as a ferroelectric phase transition in which the crystal changes both its symmetry and its electrical properties. The reduction in symmetry from the high-temperature disordered phase to the low-temperature ordered phase is the key idea of the theory of continuous phase transitions developed by Lev Landau in 1937. Because a thermodynamic system at constant temperature and volume reaches equilibrium by minimizing its free energy, Landau assumed that near the phase transition free energy can be expanded as a power series with respect to a quantity called the order parameter of the system. In the case of ferroelectric materials, the order parameter of the phase transition is the polarization P, for which the free energy is an even function of the small values of the polarization near the critical temperature of the phase transition. That is, the free energy F evaluated at the polarization P is equal to F evaluated at negative P. As a result, the expansion of the free energy F of the ferroelectric material near the Curie temperature have terms with even powers of P, and is given by the temperature-dependent value F naught of the free energy at zero polarization, plus a material constant alpha over 2, times the difference between the temperature T and the Curie temperature Tc, times the square of the magnitude of the polarization P, plus another material constant beta over 4, times the magnitude of the polarization P raised to the fourth power, and so on. This form of the expansion is the lowest order approximation of the free energy at its stationary point that is near the Curie temperature, since only the term quadratic in P has a temperature-dependent coefficient. In the standard expansion of free energy, all the coefficients are temperature-dependent and they have to be expanded with respect to the temperature. However, the leading term in such an expansion of the coefficient of the quadratic term must vanish at the stationary point, and the lowest order term in the expansion with respect to the temperature is proportional to the difference between the temperature T and the Curie temperature Tc. This is not the case for the coefficient of the quartic term, where the leading term of its expansion with respect to the temperature is a non-zero but dominant term for vanishing polarization. Then the dominant coefficients of the higher order terms can be approximated by constants. At the same time, for temperatures slightly higher than the Curie temperature, the equilibrium polarization is small, so the higher order terms can be neglected in the expansion with respect to the polarization. Consequently, the magnitude of the electric field strength E applied to the ferroelectric material given by the partial derivative of the free energy F with respect to the order parameter, that is the magnitude of the polarization P at a constant temperature T, is equal to alpha times the difference between T and Tc, times P. Then the magnitude of the polarization P can be written as the magnitude of the field strength E over the physical constant alpha times the difference between the temperatures T and Tc. However, the magnitude of the polarization P is also given by the vacuum permittivity epsilon naught times the electric susceptibility chi-E of the ferroelectric matter, times the magnitude of the field strength E. By comparing the two equations with each other, we can see that chi-E is equal to 1 over epsilon naught times alpha times the difference between the temperatures T and Tc. Then we conclude that the electric susceptibility chi-E of a ferroelectric material in a perielectric state is inversely proportional to the difference between the temperature of the material and the Curie temperature Tc, where the constant of proportionality C is the Curie constant defined by 1 over the vacuum permittivity epsilon naught times the constant alpha. This equation is called Curie-Weiss law, and it was introduced for ferromagnetic materials by Pierre Weiss, a French physicist. It is an improved version of Curie's law stating that the magnetic susceptibility is inversely proportional to the temperature, and he derived this formula by determining the contribution of the magnetic dipoles having random orientations in ferromagnetic materials to the magnetization of these materials. In fact, he applied calculations based on statistical mechanics that are similar to those already presented here for determining the contribution of randomly oriented electric dipoles to the polarization of dielectrics. We note that this special class of polar dielectric materials are called ferroelectric purely by analogy to ferromagnetism. Despite the prefix ferro, which means iron, most of these materials do not contain iron at all. Like iron magnets that have a permanent magnetic field, these materials have a permanent, built-in electric polarization. In many crystals, electric polarization occurs when they are compressed or expanded in a specific direction and electric charges of opposite signs appear on the surface of the crystal. The phenomenon in which certain solid materials develop an electric polarization when they are mechanically deformed is called the direct piezoelectric effect. Piezoelectricity is the electric charge that accumulates in them as a response to mechanical stresses. Besides crystals, this effect has been observed in certain types of ceramics and biological matter like bone, for example human femur and weight-bearing bones. The typical examples for crystals and ceramics that can produce piezoelectricity are quartz, Rochelle salt, barium titanate, and sphalerite. Ionic crystals consisting of positive and negative ions arranged in a repeating, highly ordered three-dimensional lattice can have piezoelectric properties. If such a crystal lattice is deformed under the influence of external forces, then opposite charges will appear on the opposite faces of the crystal. The most controlled way to produce mechanical stresses in a crystal is a homogeneous or uniform deformation, where mechanical stress or strain is applied uniformly across the entire crystal structure. Under uniform stress, the electrical response depends entirely on the intrinsic symmetry of the crystal lattice. In the case of homogeneous deformation, the piezoelectric effect can be observed in crystals that has a lack of a center of inversion symmetry. The only exception is the cubic point group 432 of crystals, which is non-centrosymmetric but not piezoelectric due to its high rotational symmetry. If a crystal has a center of inversion symmetry, any internal charge separation caused by a uniform deformation is exactly cancelled by an equal and opposite charge separation elsewhere in the unit cell, and no net electric polarization is produced. Therefore, a lack of inversion symmetry is a strict requirement for a net macroscopic electric polarization to develop in a crystal. To observe the piezoelectric effect in quartz, we can perform a simple experiment. We already saw in the discussion on anisotropic dielectrics that alpha quartz crystals have one threefold axis in the z direction called c-axis or optical axis, and three equivalent twofold symmetry axes called a-axes or electrical axes, which are perpendicular to the c-axis. Between the three a-axes, other three symmetry axes called y-axes or mechanical axes of the crystal can also be defined. Here we depict one of the y-axes between the axes A2 and A3. In preparing the quartz crystal for the experiment, a thin plate is typically cut so that its faces are perpendicular to one of the crystallographic axes. In the figure we show a cut with the large faces normal to the A1 axis, that is in the plane spanned by the y-axis and the c-axis, where metal electrodes are deposited on the two large faces of the thin plate and crystal is connected to a high impedance electrometer. If the crystal is compressed along the A1 or the y direction by applying some mechanical force, then a voltage pulse can be measured by the electrometer. The transient voltage generated in this effect is proportional to the duration and the rate of applied mechanical stress. Even under a constant, fixed mechanical load, the measured signal will not remain constant, as electric charges flows through the external circuit connected to the crystal and quickly leak away due to the surface contamination of the crystal or the ionization of the air surrounding the crystal. As a result, the voltage drops to zero. Switching from compressing to expanding the thin plate along the appropriate crystallographic direction, the polarity of the voltage pulse reverses. When the quartz crystal is compressed or expanded, its lattice deforms elastically, causing the centers of positive and negative charges in each unit cell to shift relative to one another because the crystal lacks inversion symmetry. This displacement induces a macroscopic polarization that causes equal and opposite bound charges to appear on the electrode-covered surfaces, creating a measurable voltage between the electrodes. A converse piezoelectric effect also exists where materials can undergo physical deformation when exposed to electric field. That is, an electric field applied to a crystal produces mechanical strain and the crystal changes its dimensions. The converse piezoelectric effect has some resemblance to electrostriction since both describe deformation of a material under an applied electric field. However, They differ fundamentally in their symmetry requirements, dependence on the electric field, and the materials in which they occur. The converse piezoelectric effect occurs when an applied electric field produces a mechanical deformation that is directly proportional in its magnitude and direction to the field strength. Because the strain changes sign when the electric field is reversed, the deformation depends on the polarity of the applied voltage, and this effect is possible only in crystals that lack a center of inversion symmetry. In contrast, electrostriction produces a strain that is proportional to the square of the electric field, which is the same for both positive and negative electric fields. The deformation is independent of the field polarity and occurs in the same direction regardless of the sign of the voltage. Consequently, electrostriction is a universal property of all dielectric materials, whereas the converse piezoelectric effect is restricted to non-centrosymmetric crystals whose symmetry permits a linear coupling between electric field and mechanical strain. In practice, piezoelectric materials intended for industrial or laboratory applications should possess several desirable properties. They should exhibit a large piezoelectric response generating a significant electrical signal from a given mechanical stress or a substantial mechanical deformation under an applied electric field. In addition, they should have high electrical resistivity to prevent the charges generated by the piezoelectric effect from leaking away. Finally, they should possess high mechanical strength and elasticity, as well as good thermal, chemical, and environmental stability to ensure reliable long-term performance. Examples for such materials are quartz, which is widely used for frequency standards and precision sensors, lead zirconate titanate, which is the most widely used industrial piezoelectric material, and lithium niobate, which is valued in high-frequency acoustic and the manufacturing of optical devices. One of the most typical applications of this effect is the piezoelectric pressure sensor or manometer designed to measure fast variations in pressure. When the pressure of a gas in a vessel acts on the diaphragm of the manometer, the diaphragm transmits a force to the crystal installed as a sensor, which is quartz or tourmaline crystal or a piezoelectric ceramic such as lead zirconate titanate. The applied force compresses the crystal producing an electric polarization and, as a result, equal and opposite charges appear on the electrode-covered faces of the crystal. Another area of applications of piezoelectric materials is modern electronics and radio communication. For example, piezoelectric transformers used in LCD monitor backlights or in AC adapters convert electrical energy at one voltage into electrical energy at another voltage using mechanical vibrations through the converse piezoelectric effect. Piezoelectric crystals or ceramics are also built in electronic oscillators, frequency filters, and ultrasonic transducers, where they act as a mechanical resonator with an extremely well-defined resonant frequency. Quartz filters provide extremely stable frequency selection because quartz has a very high mechanical quality factor, and crystal oscillators apply piezoelectric crystals to stabilize the frequency of an oscillator. Piezoelectric sensors are also used in automatics for vibration monitoring, dynamic force sensing, tactile sensing of robotic grippers, measuring rapid pressure fluctuations as seen in the first example and so on. In acoustics, the piezoelectric effect is widely used for sound recording and playback in piezoelectric phonograph pickups, microphones, telephones, and hydrophones. Among the earliest and most important applications of piezoelectricity and are widely used in medicine, industry, and scientific research, we need to mention piezoelectric quartz ultrasound generators. These devices use the converse piezoelectric effect to convert high-frequency electrical oscillations into ultrasonic mechanical vibrations. When an alternating voltage is applied, the piezoelectric crystal expands and contracts periodically due to the converse piezoelectric effect. If the applied frequency matches one of the crystal's mechanical resonance frequencies, the vibration amplitude increases dramatically, producing intense ultrasonic waves. We finish the presentation on ferroelectricity and piezoelectricity with the discussion on pyroelectric effect and electrets. In certain piezoelectric crystals, the sublattices of positive and negative ions are displaced relative to one another in thermodynamic equilibrium, resulting in an electric polarization even in the absence of an external electric field. Piezoelectric crystals that exhibit such spontaneous polarization are called pyroelectric crystals. In other words, a pyroelectric crystal is a crystal that possesses a spontaneous electric polarization in thermodynamic equilibrium and whose polarization changes when its temperature changes. The spontaneous polarization is screened by surface charges and ions adsorbed from the surrounding air onto the crystal surface. However, when the crystal is heated or cooled, its spontaneous polarization changes, producing new surface charges that can be detected until they are compensated by charges from the surrounding environment. As a result, heating or cooling the crystal produces a temporary accumulation of electric charges on its surfaces, a phenomenon known as the pyroelectric effect. The pyroelectric current generated during a temperature change is proportional to the rate of change of temperature and materials properties of the crystal for a given electrode area. All pyroelectric crystals are piezoelectric because every polar crystal lacks inversion symmetry. However, the converse is not true. Most piezoelectric crystals are not pyroelectric because they do not possess a spontaneous polarization. Examples of pyroelectric materials include tourmaline, lithium tantalate, and many ferroelectric crystals such as barium titanate below its Curie temperature. Pyroelectric crystals are widely used in infrared detectors, where changes in the incident infrared radiation produce temperature variations that alter the crystal's spontaneous polarization, generating an electrical signal proportional to the radiation intensity. They are also applied in passive infrared motion sensors, where changes in the infrared radiation emitted by moving objects produce temperature variations in the crystal, generating electrical signals that indicate motion. Pyroelectric crystals are valuable in the manufacturing of thermal imaging devices as well, where they detect spatial variations in infrared radiation by converting temperature-induced changes in spontaneous polarization into electrical signals that form a thermal image. Another important application of pyroelectric crystals is in flame detectors, where they detect the characteristic fluctuations in the infrared radiation emitted by a flame and convert them into electrical signals for reliable fire detection. Pyroelectric crystals are also employed in laser energy meters, where the temperature rise produced by absorbed laser radiation is converted into an electrical signal proportional to the energy of the laser pulse. Besides the direct pyroelectric effect, pyroelectric crystals also exhibit the converse pyroelectric effect, whereby a change in the applied electric field results in a change in the crystal's temperature under adiabatic conditions. It is a thermodynamic phenomenon where a material experiences a change in temperature or entropy in response to an applied electric field. The converse pyroelectric effect, also known as the electrocaloric effect, is the exact thermodynamic reverse of the pyroelectric effect, and it can be shown that this effect is a necessary consequence of the direct pyroelectric effect and the laws of thermodynamics. The first law of thermodynamics tells us that an infinitesimal change in the internal energy U of a crystal is equal to the infinitesimal amount of heat delta Q exchanged between the crystal and its surroundings, plus the infinitesimal amount of work delta W done on the crystal by the electric field. By applying the second law, delta Q can be written as the entropy S of the crystal times the infinitesimal change dt in its temperature. We already saw that the infinitesimal work done on a dielectric material by an electric field is given by the magnitude of the electric field E times the infinitesimal change dP and the magnitude of the polarization field in the material. We also saw that Helmholtz free energy defines the thermodynamic stability of a system at constant volume and temperature, and it has a critical role in the interpretation of the behavior of ferroelectric materials. The Helmholtz free energy F of the pyroelectric crystal is defined by its internal energy U minus the product of its temperature T and entropy S. Then the differential of the free energy F is equal to du minus T times ds minus S times dt. If we substitute the expression obtained for the differential of the internal energy U into the right-hand side of this equation, dF can be written as E times dP minus S times dt. In experiments, one usually controls the electric field applied to the crystal rather than the polarization produced by the field. Therefore, we introduce another thermodynamic potential phi defined by the difference between the free energy F and the product of the electric field E and the polarization P. The differential of the potential phi is given by dF minus E times dP, minus P times dE. By inserting the expression obtained for dF into the right-hand side of this equation, d phi can be written as negative S times dt, minus P times dE. Since the differential of phi is expressed in the terms of the differentials of the temperature T and the magnitude of the electric field E, these quantities represent the two independent variables of the potential phi. Consequently, its differential can also be expressed by the sum of the partial derivative of phi with respect to T at constant E times dt, and the partial derivative of phi with respect to E at constant T times dE. By comparing the two equations derived for the differential of the potential phi, we can identify the entropy S of the crystal as the negative partial derivative of the potential phi with respect to the temperature T of the crystal at a constant field strength E applied to the crystal. Similarly, we can see that the magnitude of the polarization P of the crystal is equal to the negative partial derivative of the potential phi with respect to the magnitude of the field strength E at a constant temperature T. Then the partial derivative of the entropy S with respect to the magnitude of the field strength E is given by the negative second-order partial derivative of phi with respect to E and T. If we interchange the order of the partial differentiation, we can write the right-hand side as the partial derivative of the magnitude of the polarization P with respect to the temperature T at a constant field strength E. This result is a Maxwell relation between the entropy and the polarization of the pyroelectric crystal, where the partial derivative of the polarization P with respect to the temperature T at a constant field strength E in the right-hand side of the relation is defined as the pyroelectric coefficient P of the crystal. The later describes the pyroelectric effect in the crystal since P is the constant of proportionality for the pyroelectric current through a given electrode area generated by the change in the temperature of the crystal. For a non-zero pyroelectric coefficient, the Maxwell relation shows that an electric field applied to the crystal will change its entropy. Under adiabatic conditions where the differential of the entropy S vanishes, any variation in entropy must be compensated by a change in temperature. Consequently, modifying the electric field produces a temperature change, which is the converse pyroelectric effect. Dielectrics with permanent polarization is known as electrodes by analogy with permanent magnets. In other words, an electrode is a dielectric material that retains its electric charge or polarization after being subjected to a strong electric field. Electrodes occur naturally in certain crystals, such as quartz, tourmaline and zinc oxide, but can also be produced artificially. We can produce an electrode, for example, by cooling a molten mixture of wax and resin in the presence of an electric field. In this way, the molecular dipoles which become aligned with the applied electric field in the liquid state, are effectively frozen in place during solidification, allowing the material to retain its polarization even after the electric field is removed. An electrode can retain its polarization for many years if it is protected by a suitable metal coating that prevents stray ions from the surrounding air from reaching the surface and neutralizing the surface charges. Electrodes are widely used in electret microphones, electrostatic air filters, loudspeakers, radiation dosimeters, and energy harvesting devices because their permanent polarization provides a stable electric field without the need for an external power supply. Let us summarize the content of this presentation on electrostatics in dielectric materials. We began by examining the electrostatic field in a charged parallel plate capacitor filled with a dielectric and explained the fundamental difference between conductors and dielectrics based on their atomic and molecular structure. Through two experiments, one performed at constant charge and the other at constant voltage, we showed that inserting a dielectric between the capacitor plates increases its capacitance by a factor equal to the relative permittivity of the material. Consequently, for a given charge, the electric field strength is reduced by the same factor, whereas for a given voltage, the charge stored on the capacitor increases by the relative permittivity compared with a capacitor containing vacuum or air. We then examined electric polarization in dielectric materials by distinguishing between nonpolar and polar dielectrics according to the presence of permanent electric dipole moments. We showed that, although a dielectric placed in the electric field of a capacitor remains electrically neutral overall, the field aligns or induces dipoles within the material, giving rise to polarization charges on its surface that reduce the electric field strength inside the dielectric. We introduced the polarization vector as the local dipole moment per unit volume and showed that its normal component equals the surface polarization charge density, while its negative divergence gives the volume polarization charge density. We introduced the electric displacement vector or electric flux density, which enabled us to generalize Gauss's law for dielectric materials. The electric displacement flux through a closed surface equals the total free charge enclosed, or, in differential form, the divergence of the displacement field equals the free volume charge density. We also define the electric susceptibility of homogeneous, isotropic dielectrics as the constant of proportionality relating the polarization vector to the electric field strength. For anisotropic dielectric materials, this proportionality was generalized by replacing the scalar susceptibility with a second-rank susceptibility tensor, which accounts for the dependence of the polarization on the direction of the applied electric field. Next, we analyzed polarization in homogeneous, isotropic dielectrics by considering infinite parallel plates and charged conducting spheres. We showed that polarization reduces the electric field inside the dielectric by a factor equal to its relative permittivity, while the electric displacement remains unchanged and is determined solely by the free charge. We extended these results to thick spherical dielectric shells, where the electric field and displacement obey Coulomb's law modified by the permittivities of the media. Finally, we discussed the phenomenon of depolarization, in which the polarization field opposes the applied electric field and reduces its strength within the dielectric. Applying Gauss's law, we studied the behavior of the electric field and electric displacement at the interface between two dissimilar dielectric media and derived the corresponding boundary conditions. We showed that the tangential component of the electric field is continuous across the interface, whereas the tangential component of the electric displacement is generally discontinuous. In contrast, the normal component of the electric displacement is continuous in the absence of free surface charge. We also derived the law of refraction of electric field lines at the interface, showing that the ratio of the tangents of the angles made by the field vectors with the interface normal is equal to the ratio of the permittivities of the two dielectric media. We distinguish the macroscopic electric field in a dielectric from the local field acting on an individual atom or molecule. Using the Lorentz cavity model, we showed that the local field equals the sum of the external electric field and the polarization divided by 3 times the vacuum permittivity. We then introduced atomic and molecular polarizability and classified dielectric polarization into electronic, ionic, and orientational mechanisms. Next, we examined the polarization of gases and showed that the electric susceptibility of a nonpolar gas is proportional to its atomic concentration and polarizability, while for polar gases an additional temperature-dependent term arises from the permanent molecular dipole moment. We derived the Clausius-Masodi equation relating the relative permittivity of a gas to its atomic polarizability and extended it to the Clausius-Masodi-Debye equation for polar gases. We also derived the energy density of the electric field in a dielectric as 1/2 of the dot product of the electric field strength and the electric displacement vector, and generalized this result to non-uniform fields and inhomogeneous dielectric materials. We proved that the work required to polarize a homogeneous, isotropic dielectric per unit volume is equal to 1/2 of the dot product of the electric field strength and the polarization vector. We demonstrated that inserting a dielectric into a capacitor decreases its stored energy when the charge is kept constant, whereas for constant voltage the capacitor gains energy supplied by the voltage source while the electric field performs mechanical work on the dielectric. We showed that the force acting on a charged body embedded in a dielectric cannot usually be expressed simply as the product of its charge and the electric field, because the field inside the cavity differs from that in the surrounding medium. For liquid dielectrics, however, the combined electrostatic and mechanical forces reduce to this familiar form. We then introduced the electrostatic force density and showed that it equals the product of the free charge density and the electric field strength in a homogeneous dielectric, while the force between charged parallel plates is reduced by the relative permittivity of the dielectric. Next, we explained how charged bodies attract electrically neutral dielectrics through polarization in a non-uniform electric field and, using the electric dipole approximation, showed that the resulting force is proportional to the gradient of the square of the electric field strength. We introduced the Maxwell stress tensor, expressed the electrostatic force density as its divergence, and applied this formalism to a charged dielectric sphere immersed in a dielectric fluid, demonstrating that the net force acting on the sphere indeed equals the product of the charge of the sphere and the field strength. We derived the Korteweg-Helmholtz force density for inhomogeneous dielectrics with density-dependent permittivity as well. In the last topic, we discussed ferroelectricity, introducing materials that exhibit spontaneous polarization below the Curie temperature in the absence of an external electric field. We showed that these materials are characterized by a very high relative permittivity and polarization hysteresis, and that above the Curie temperature they lose their spontaneous polarization and behave as ordinary dielectrics. We also derived the Curie-Weiss law, which states that the electric susceptibility of a ferroelectric is inversely proportional to the difference between its temperature and the Curie temperature. Next, we examine the piezoelectric effect, in which non-centrosymmetric crystals develop an electric polarization when mechanically deformed, as well as the converse piezoelectric effect, where an applied electric field produces mechanical deformation, and contrasted it with electrostriction. We then discussed the pyroelectric effect, showing that pyroelectric crystals possess spontaneous polarization in thermodynamic equilibrium and develop temporary surface charges when heated or cooled. We also introduced the converse pyroelectric or electrocaloric effect, in which an applied electric field changes the temperature of a crystal under adiabatic conditions, and showed that it follows from the direct pyroelectric effect and the laws of thermodynamics. Finally, we introduced electrets, dielectric materials that retain a permanent electric charge or polarization after exposure to a strong electric field.